So we'll go ahead and kick off the workshop. Welcome everyone to the workshop on strategic multi-agent interactions. We're focusing the workshop today on methods that kind of bring together ideas in game theory and machine learning for particularly robotics related problems and decision problems. So welcome everyone, and thanks for your attendance and for your engagement today. We're really excited. Next slide. Okay, so the overview for today is just on this slide. So we're gonna just get things started with a few remarks and then having several invited talks. Our first round of paper talks from our contributed papers and so forth until lunch. At each of these sessions of paper talks, what we're going to do is have the authors who are present in the room kind of line up and sort of all be at the same place with laptops ready to kind of share slides and so forth. You'll have 10 minutes to present, and then we'll also have kind of a shared RSS style Q&A session following all presenters. So you'll kind of all sit at the table up here, or if you're on Zoom, hang around the Zoom session, and folks online and in person can ask questions, and we'll try to moderate as best we can. So that's how things are going to work. And then after lunch, we'll continue the same sort of schedule as you see. Perfect. Just to kind of get us all thinking about this topic, I want to, no? Okay, so just a quick word on kind of who we are and why we're running this workshop. So the, four organizers here. I'm David. Forrest and Zach are here in the room. Nagar unfortunately couldn't be with us in person today, but is on Zoom and will also be kind of helping to run some of the sessions. So you'll hear from all of us today, and all of us are very interested in game theory as a whole, both static and dynamic problems that you'll hear about today, building efficient algorithms, kind of accounting for informational complexities, and a variety of different applications. So we kind of come to this workshop really trying to bring together people in all of these different areas to kind of learn and talk with one another. Next slide. And we hope that kind of all of you are here with us today because we're all trying to learn more about how to kind of model interactive problems as different types of games with kind of interesting different properties and equilibria and so forth. Next bullet. To learn more about the mathematical foundations that underlie those types of models and problems, and specifically to deal with some of the really interesting computational and theoretical challenges that emerge when there's high dimensionality, nested sorts of decision problems, complex information structures, etc. And in particular also to discuss kind of the role of all of these algorithms and theoretical ideas in real life multi-agent planning and decision-making problems. So we'll talk about all of these issues today. We'll have 5 invited speakers, as you saw on the schedule, and you'll hear about this. I think we've kind of randomly assigned orders, but so not exactly in this order. But we have 5 wonderful speakers that you'll hear from in addition to the contributed talks. And the contributed talks are going to focus on several different areas. So I've kind of grouped them, and each session is going to focus on those topics. So you'll hear from a lot of different areas today. With that, I want to introduce our first invited speaker. So Jakob is here in the Zoom session. So Jakob, while you're setting up and sharing screen, just to introduce you, Jakob Foerster received his PhD in AI at Oxford and is currently an associate professor in engineering science there as well. He uses a variety of deep reinforcement learning methods and studies decision-making and interaction in multi-agent problems, ranging from the emergence of communication to non-stationarity, reciprocity, and credit assignment in multi-agent problems. Jakob's papers have been recognized by many awards at top machine learning conferences and have really helped to push these types of methods to the forefront of AI research. So we're really excited to hear what you have to say today, Jakob, and thank you so much for being with us. The floor is all yours.
Wonderful. Thank you so much for having me. I will start out with a brief request.
Yes.
As you know, being on the computer can be kind of tiring. So if you don't mind, if you could please make this talk as interactive as possible. And so that what that means is if you are online, if you can turn your camera on so I can see some humans, that'd be fantastic. And if you're in the room, feel free to ask questions and interact, because it just makes it so much more fun. And I'm sorry that I can't be in New Zealand on the ground with all of you. But I am really excited to be here. I had a long day of interviewing people for undergraduate admissions at Oxford. And so I need a few human interactions to energize me again. So my name is Jakob Foerster. Thanks a lot for having me. I lead the Foerster Lab for AI Research, which is a small but quickly growing group at the University of Oxford. And as David so kindly mentioned, we study sort of the question of what does it mean to do machine learning in an environment that contains other learning agents, and how can we think about methods and develop methods that are actually suitable for the multi-agent setting in the broader sense. I have this motivational slide, but I don't think I need this. Obviously, we all know that the world consists of a variety of different agents that have a broad range of different interests and can lead to all sorts of chaos if we're not careful. There are these very obvious multi-agent problems, such as self-driving cars or interaction with humans. But I think what's interesting is that sometimes multi-agent problems are a little bit less obvious. So for example, when we study machine translation, we commonly just think of this being a supervised learning problem, where we have static data that exists independent of our own decision-making. But in reality, obviously they're users, and something that these users might want to do is to translate their websites from one language into another language. And voila, suddenly we're going to scrape the internet to get more training data, and immediately we're in this interactive loop whereby our own decisions change our training data. So my claim is that once we have deployed machine learning systems, we're almost universally in the interactive loop between agents, decision-making, and future data. And this real big question is, how do we do machine learning in the presence of other learning agents? Are there any questions on this? Can everyone hear me clearly? I don't know how the acoustics are. Trying to create some common knowledge here between everyone. Thank you so much. I see a thumbs up there.
I'll be up here to moderate questions in the room. So if you see me up in here, that's fine.
Perfect. Yes. So please speak up if you have anything that seems at all confusing or controversial. I sometimes build in little confusing parts to my talks just to make sure that people are paying attention. There will also be some mistakes. And if you don't speak up, I will just hang up on you, just so you know. This is called the grim trigger strategy. So if you're not cooperating, I'm just going to give up immediately. Joking aside, so what is the most stereotypical example of general sum learning? It's the prisoner's dilemma. So let's practice interactivity. Can I have a show of hands on Zoom for anyone who knows the prisoner's dilemma? Okay, fantastic. For those of you who don't know the prisoner's dilemma, it's basically Alice and Bob robbing a bank, getting caught, and being interrogated separately by the police about whether or not the other party robbed the bank. And the two options are that I can either say, no, they didn't do it. I'm Alice. I say, no, Bob didn't do it. That means I cooperate with Bob. Or I can say, oh, yes, he did it. It's totally Bob's fault. He robbed the bank, in which case I defect against Bob. And the police is smart. They've set up the incentives such that I'm incentivized to defect against Bob. So no matter what the action is, and that's because this is game theory people. So cooperation is dominated by defection. Okay, no matter what Bob is deciding, Alice is always better off defecting. So why is that? Because if I cooperate and Bob defects, I spend 3 years in prison. Versus if I defect, I'm now going to spend only 2 years in prison. What happened if Bob was cooperating? If I cooperate, I spend 1 year in prison. But if I now defect against Bob, although they're cooperating, I spend 0 years in prison. I've explained this prisoner's dilemma about 1 million times and still confused the heck out of me. So apologies if that was confusing. Let's clarify things a little bit by playing around of PD online. We're going to do the following. Who is brave enough to play the round of a single shot prisoner's dilemma? Who is brave? Please unmute you. If you don't to unmute you, you can just, we do thumbs up, thumbs down. Thumbs up means cooperation, thumbs down means defection. Zachary, you seem like somebody who wants to play the prisoner's dilemma.
Okay.
Okay, cool, let's do it. On three, okay? 1, 2, 3. Wonderful. So here's what happened. Let's go through this. So I defected and Zach defected. We spent 2 years in prison. What does that mean? This is obviously the globally worst case outcome because we're spending 4 years in total in prison. And that's why it's called the prisoner's dilemma. Okay. So this is basically, as a sensible rational agent, we really should be defecting in the single shot prisoner's dilemma. And this is also something when I think about learning, as I put it as a litmus test, because there's a lot of papers on general sum learning. And the first question I ask when people say, I've solved reciprocity, I have a method that works in general sum settings, I ask them, what does your method do in this single shot prisoner's dilemma? And you would be surprised how many papers cooperate. Reinforcement methods cooperate in the single shot prisoner's dilemma. Okay? We're not doing this, we just defected. But this is obviously a bad outcome because we're spending worst case amount in prison. So what humans typically do is we design systems whereby we have iteration. We're playing these games over and over again. And that completely changes the possible outcomes in this game. Is anyone willing to play the iterated game with me? Quick show of hands. I need a volunteer again to go through the dynamics. If not, I'm gonna, Zachary, you did so well. Okay, now we're gonna play an infinite number of games together. So 3, 2, 1, go. Yep. 3, 2, 1, go. 3, 2, 1, go. 3, 2, 1, go. Okay, so here's what's happening, right? Suddenly, all sorts of different outcomes become possible, and we're no longer just blindly defecting this game. And this seems fairly obvious as something that we should be able to do with machine learning methods. But in this talk, I will show you why this is indeed hard and show you some very, very brand new methods that address this challenge of accounting for other agents in the environment. In particular, I talk about this paper called Model Free Opponent Shaping, which we published this year at ICML. So this is brand new. So how has the IPD been treated over the decades? Historically, there were tournaments where people have hand-coded heuristics that take in the past actions of both players and produce a state. And now we can obviously evaluate these heuristics. Tens of thousands of lines of code written, who won tit for tat back in 1980s, the big Axelrod tournament. So for example, there's tit for tat, there's always cooperate, there's a broad range of strategies we can be evaluating. But we can obviously also parameterize these policies by some weights theta. And then we can imagine that there is a function now which assigns an update. So we have some type of interactions between agents. There's an episode of games being played in the inner loop. And then there's an outer loop function that updates the policies based on the experience of the agents in the inner loop, in the trajectory. And voila, a fairly obvious answer is we can do reinforcement learning. So in particular, what I can do is I can learn approximate best responses to a player by updating the policies of the other player using reinforcement learning between episodes. So I'm assuming you and I play a game of Prisoner's Dilemma. I get the data. You're playing some type of hard-coded policy at the moment. You're going to learn a policy and approximate best response. Okay. So if you're all on board with this, obviously we can do multi-agent learning, where both agent I, me, the AI agent, and minus I, the other agents, are now updating their policies based on the data that's coming from the episodic nature in the environment. Okay, so we play an episode, we get data, we update using reinforcement learning. Are there any questions so far? I'm going through this quite quickly because I assume most people are familiar with this, even though the pictures might be a little bit unusual. And what does this mean? It means we have a reinforcement learning algorithm that, in the extreme case, is an update function based on the policies of both players in the environment. So for now, I'm assuming that we really have access to these policies in the extreme case. And the simplest way we can do this is by something called naive learning, where each player just updates their policy as a gradient step to maximize their own value function. One step in the direction of the gradient of my value with respect to my own parameters. And this is called naive learning, independent learning. It's basically what you're doing when you ignore the presence of other agents in the environment. It's probably the single most popular scalable multi-agent learning method. Now, it is extremely simple, but it has a huge downside. And the downside is that if you do this in the IPD, you get this policy. I'm showing an entire policy at the end of training for 30 different training runs, so 30 different seats. And what I'm visualizing is the probability of cooperation for player 1 and player 2 in all of the 5 possible states in the IPD. 5 states because the cooperation defection, 4 states, and the initial state as 0. And if you look at this carefully, you will see that when we defect in the first state, both players, because we have 100% cooperation of defection, 0% probability of cooperation, and that means we only end up in DD, and then we defect forever after. Okay. So it turns out that if you do independent learning, the most popular method for multi-agent learning in complex environments, you end up learning a blind defection policy in almost all cases. And this was known and has been analyzed for a few years now. And one of the papers that we did on this work was called Lola, where rather than modeling the other agent as non-existent, ignoring the presence of other agents, we model the presence of other agents and differentiate through their learning step. Okay, so this now is saying I have a Lola agent that models the learning of the other players. What does this look like mathematically? We simply differentiate through the dependency of the reinforcement learning update of the other players in the environment. Okay, are there any questions on this? Hopefully this is all quite vanilla, so we're just shaping the learning of other players. I know one step ahead what they will update, how they will update the policy. Your next steps, your next episode's policy changes my return in the next policy, so I can differentiate with that.
So it sounds like we might have a question in the room. Give a quick second here.
Should I do this?
Please,
Yeah.
please go over and make an interaction. I don't care if I get through all the slides. You can read the papers.
Does this work? Oh, whoa. Jakob, can you hear this?
Yes, I can hear you.
Okay. Okay. Hopefully it's not going through 2 microphones to get to you, but so my question is, when you do this Lola update, are you changing the resulting equilibrium? Like, this seems like there's some kind of Stackelberg equilibrium happening at this point, right? Because you're reasoning about the response of the opponent to your own change in strategy.
Yeah. So in this line of work, we're mostly for stable fixed points, and there's a whole line of work that we might have another talk on just after about stable fixed points versus equilibrium of the game. We will even get rid of stable fixed points with Lola updates, because you can see I can be at a place where my gradient is 0 for both players, but the high order derivatives are non-zero. Okay. And there's a follow-up work it's called SOS, but it's a little bit too hard to explain this point, that then makes sure you actually converge to stable fixed points. So you do absolutely change the equilibria, but empirically speaking, we found that you do still converge to equilibria in the games that we've tested. But there's no theoretical results, and actually there's a different line of work that tries to disambiguate between stable fixed points in the sort of like large function box matrix setting and Nash equilibria. Fantastic question. The best theory you have on this work is called SOS, stable point shaping. It was published about a couple of years ago. Great question. And obviously, when we're asking for equilibria, we're assuming that both players are now doing something like Lola, right? So then we're in this setting where actually both players trying to shape the other agent with this inconsistent view of assuming you're a naive learner. And the good news is that at least in the IPD, we're now suddenly converging to very different policies. Can anyone guess what this policy is shown on my screen? Any guesses? We can also interpret it if you want. So remember, red was we both defected, green is I defected, you cooperated, yellow is I cooperated, you defected. This is tit for tat. So just by changing from naive learning tit for tat, you no longer get unconditional defection, but you get instead tit for tat coming out of mutual learning, synchronous learning of 2 players in the environment. This is nice, but there's 3 major issues. The first one is that we're only myopically shaping the opponent's next learning update. And we're really inconsistent because I model everybody else as a naive learner. So if Lola agents coexist in the same environment, that's an inconsistent assumption, which seems theoretically flawed. And it's also highly unstable because it requires high order derivatives. And you can imagine in a subsample-based environment where I have to interact with the world to estimate gradients, estimating high order derivatives is a huge pain. So let's see if we can make progress on this. What if instead of having reinforcement learning as my update in the outer loop, I had a function that's parameterized by some phi? So now I'm saying I have an update function that isn't Lola, isn't reinforcement learning, isn't anything, but it's instead just parameterized by some vector file. Okay. And now in particular, I can imagine that I have an outer loop, so I have the episodes, I have the learning, the update of the policy between episodes. And now I can imagine that I have an outer loop that is about how to update file. Okay. And in particular, I can use reinforcement learning to learn the update rule. Okay. And what does this mean? This means I'm simply playing the meta game. I can now, for whatever update rule the other agents are using the environment between episodes, I can now learn an update function that's the best response in the meta game, where the game states are policies of both players. And the action is to choose my next policy for the next episode. The transition dynamics are induced by the update rule of the opponent between policies. And I can simply learn long-term shaping in this environment. The reward for my meta episode is now the sum of discounted returns across all the episodes across the entire learning horizon. Okay, so to actually meta learn this, I have an episode where the initial state is a randomly initialized policy from my opponent. I pick a policy, they update, I get a return, a reward, which is the return of the inner game, and so on and so forth, until my opponent has converged, for an infinite time horizon. Does that make sense? So this is now playing the meta game of opponent shaping. And it turns out this is doable and it's extraordinarily powerful. So what I'm showing here is the results for this MFOS agent, model free opponent shaping, when being paired with a set of different learning strategies in the IPD. So here's naive learning, here's Lola, and here's a meta learning version for multi-agent learning from the literature. And as you can see, the MFOS agent spends less than a year in prison when being paired with any other learning algorithm. Okay. It also means that we're no longer socially optimal, because remember, Lola manages to play tit for tat, which then leads to 1 year in prison for each player, 2 years in aggregate. Instead, if we're looking at the MFOS agent being paired with a naive learner, the naive learner spends 2.14 years in prison, while the MFOS agent spends only half a year. But that means in aggregate, we're spending over 2 years in prison. Okay. So what does this mean? This means the MFOS agent has learned to extort other players, completely take advantage of their learning dynamics. And this comes with a big warning. And learning algorithms can actually learn to extort other learners, right? Lola wasn't very powerful. To that extent, it was socially beneficial to do opponent shaping because it resulted in better results than effect effect. But if you actually have a very powerful opponent shaper, you can extort other learners. And we can visualize this in these 4 different plots, where I'm showing at the beginning of the time step, this is when at the first episode, when the inner agent was randomly initialized. I'm showing the policy that MFOS plays. So the resulting rewards for the inner agent, so the opponent, and the MFOS agent and on the X and Y axis for the current policy pair, and for all possible policies that the opponent could be playing. So in blue, you see all possible payouts that are achievable by a unilateral update of the inner agent. Okay. And in red, you see the current policy that the inner agent is playing. And the interpretation of this is that now if the red agent moves towards high rewards, they're going to move along the to the right on the X direction, because that's where they increase their reward. They'll pick a policy, they'll move towards policies that appear. And that means the MFOS agent has set up a gradient field such that learning for the inner agent leads to higher rewards for the MFOS agent. Okay? And indeed, this is what happens over the first learning steps. So the time steps here, obviously, meta steps. And that means that gradually we can see the red policy drifting to the right. And the MFOS agent is getting much higher rewards, up to a point where now the inner agent has started to cooperate largely, at which point the MFOS agent switches to a very different strategy that is full-on extortion. It now starts to defect against this naive learner. Obviously, at this point, the naive learner is going to start to learn to defect against the MFOS agent because it's no longer tit for tat policy. But only once the naive learner starts to defect, the MFOS agent is going to switch around again. Does that make sense? So this is the first time, as far as we know, that learning algorithm has discovered what's called zero-determinant extortion. This method in the IPD was only discovered by humans in the last decade. Are there any questions on this? Or is everyone on board and slightly scared? Good. Because I do have good news. Because obviously we can't just have papers that say here's a method that extorts everyone and leads to socially bad outcomes. So it turns out we have also solved this problem to an extent, and that is simply by shaping the shaper. Okay, so previously we had assumed that the other algorithms are fixed learning algorithms. So what if instead everyone is playing the metagame? What if all agents in the environment are jointly learning to play the metagame? That's what's shown here. So here we're both playing the metagame. And now you might complain, we started out with the fact that general sum learning is hard and unstable, you can converge to defect effect unconditionally. Now who prevents us from just converging to defect effect in this metagame, right? Who says we've gained anything by playing the metagame rather than the game? And the good news is that for this metagame, we've also developed a tracing procedure based on Hassani et al.'s work from 1960. And that is by initializing each MFOS agent to play a best response to a naive learner, and then gradually anneal the probability with which they play with a naive learner versus with the best response to a naive learner at that same mixture level. So you have a parameter lambda that we can slowly anneal from 1 to 0. And as we're tracing this results in a unique equilibrium at the end of training. This is a standard sort of equilibrium selection technique that comes off game theory that we've now scaled and applied to this meta self-play, which is a high-dimensional general sum game of picking policies based on past policies. And it turns out if you dare to do all of this, yes, please.
This FRL is this the same for both players, or?
In the studies we did, so this is basically the optimization algorithm for the meta self-play. And in our work, we assume the same. But you can, in principle, do any type of optimization. It might be interesting to check what happens if you play different optimization algorithms. But it shouldn't really matter because due to the tracing procedure, there's now a well-defined unique equilibrium, right? So as long as your optimization procedure is powerful enough to give you a near optimal solution at every point for this tracing procedure, it shouldn't matter how you optimize. Use reinforcement learning or evolution strategies or other gradient optimization methods. And remember, this is a pure sort of optimization process. The inner loop RL game is gone now, right? This has all been replaced. The updates in the inner game have been replaced by learned update functions. This is the meta self-play now that we're optimizing here.
So phi I naught, right? This is kind of this phi on the top right that you're, no, to the other one on the right.
So this is the phi for the other players. So we're talking about the ego agent I, and then other players minus I.
Right. So where does phi minus I show up in the low level game?
This is the phi here is that phi minus. That should be you've spotted a typo in my slides. Thank you very much. This is fun. Of course, I told you I built typos in my slides to make sure people are paying attention. I was about to hang up on everyone. Thank you. You just saved the call. Everyone should be very grateful. Yes, this is the phi minus I, and this is the phi I here.
I see. Okay, great. Thank you.
Great. So I was about to quit. Okay, any other questions?
I have one sort of high-level question. Sorry for interrupting.
Please.
But this is actually very interesting. You talk about this sort of reasoning about influencing other agents in this meta game. So, and the question that I have, when you have this type of reasoning, I have my belief over what the other agent is doing, and they have their belief over what I'm doing, and this can be like this K-level reasoning of I have my belief over the other agent's belief on my belief. So what are your thoughts on how to dealing with that, and how can we stop this like infinite level of reasoning about these meta games?
So we did a lot of work in trying to get out of that infinite loop for Lola agents, because Lola plays with like naive learner, and that's level 1, and then you want to do like level 2 with a level 1 agent. And We have a paper called Consistent Learning with Opponent Learning Awareness that was published at, forget, New York last year, maybe, something like that, COLA. It's a cool acronym. If you're interested in this, there's something called COLA, where we basically rediscover pins, physics-inspired neural networks. And we use those to solve for the consistent parameter update, such that under opponent shaping, our update functions are consistent. And we learn that using deep neural networks. So Lola sets up a sort of gradient constraint where the derivative of my update function anticipated yada is consistent with your update function, and we solve for that consistent update function. But it's really, really confusing. It turns out you don't need that if you're doing MFOS, because in MFOS, we can go model free. We can optimize all of this as mutual best responses without doing infinite reasoning. And as long as we're playing in approximate mutual best responses, we have a well-defined equilibrium process, which doesn't require infinite order reasoning. We could argue it's implicit. To what extent this is true is a matter of, beliefs and capacity of the neural networks, but we can break the infinite loop, which is one of the beauties of the MFOS algorithm. Because in meta self-play, I don't have to explicitly reason over things anymore. It's implicit through the shared learning in the shared environment. But it's a great question, thank you. And it's really inspired us to work on this because the CoRL algorithm seemed even harder to scale than MFOS. Any other questions? And thank you, by the way, for engaging. This is makes it much more fun. Awesome.
Just a reminder before you start back, just a reminder for people in the room, some new folks have come in. We have these boxes, these like your microphone RSS file boxes. So if you have a question, just raise your hand and we can walk it over.
Cool. So what happens if we dare doing meta self-play? This is the result. So MFOS, we're finally back to 1 year in prison per person. Okay, so this thing then in its own like meta, yada, whatever equilibrium discovers something that looks like tit for tat with a bit of more noise. And we also test this in iterated matching pennies. So we're playing, what is it called? Up and down. And here it turns out MFOS can again terribly extort all other learning algorithms, even in a zero-sum game. But then if you pair it with itself, it converges to a Nash equilibrium of getting 0 points quite stably. Okay, so the question is, how do we scale this up? Well, this is obviously really hard because we took policies as input and put out entire policies. So instead, we had this method that takes in trajectories and outputs conditioning vectors. So it's sort of like a partially observable metagame now, POMDP, or partially observable stochastic game if you want. And then the inner agent uses that conditioning vector to change the policy. And we scale this all the way up to deep reinforcement learning, i.e. a high-dimensional state action space, this coin game. Agents. Yeah, this was not even that easy, but it's sort of like if you once you go into trajectories and recurrence, then life does get much harder. This is also a game where the original Lola algorithm struggled. We have another algorithm on that Lola line of work called Polar, proximal learning with opponent awareness, that actually works much better. So there's work to do. In the last 2 minutes, I'd like to give you a quick preview of some work that is brand new, so that's currently under review, and that's called adversarial cheap talk. And here we're relaxing the assumptions further. We're asking, what if I don't even have access to an agent in the same environment, but I can change useless data? So imagine you're trying to learn an algorithm that does stock trading. You're going to train on the order book data, but the orders far away from the mid price are really free. So often in your data set, there's some data that somebody else can control because you don't care about it. And we're doing end-to-end learning, so we throw all the data in. And we're formulating this as a single agent setting where we have an adversary that can't delete any of the true state information ST, but it can concatenate useless features, phi of S. And the question is, how bad can it be if I train an adversary to append features phi of S, noise features phi of S, that are under control of the adversary? Does that make sense? So the agent can still observe the true state. And all I can do is I can append 2 bits of continuous numbers during the training process. And what we show in this paper called adversarial cheap talk, that this really minimum viable adversary that can't alter environment dynamics or rewards or anything, can't induce non-stationarity because it's a feed-forward function, can indeed do all sorts of really, really terrible things. And because I'm running out of time, I'll give you the high-level overview of this, which is in bold the red line by appending these meta-learn sheepdog features. And we can also go in and remote control the agent to do things that the agent didn't want to do. So this is the zero exploitation result here, which I'll show you quickly, which is we trained an agent during learning to go for the blue dot, but the adversary was setting these noise features in a clever way whereby then at test time, it can remote control the trained agent to reach for the yellow dots instead. So as far as the agent is concerned, it's still maximizing reward by going for blue, but in reality, just because I can control completely useless features in this world, I can now make the agent go to any goal location I want, in particular these yellow features on the screen, the yellow dots on the screen. This is a brief preview. As I said, this is work currently being done under review, and I should give a huge shout out to my lab. This wouldn't be possible without fantastic collaborators and without people really who've made a lot of progress on JAX. We can run all of these experiments on a few GPUs, and we can now train 8.4 million individual PPO agents in 2 hours on 4v100 GPUs on Catpole. Okay, so if this isn't mind-boggling, then I don't know what is, but this is really something whereby progress on the software side has enabled academic labs like mine to now do work that industry labs are still using entire compute farms for, right? So this is something you have to realize now. You're now competitive in academia with a few GPUs to huge CPU farms in industry labs, because students often are much better at utilizing resources. And with this preview, I'd like to thank you all for listening and open the floor to any sort of very last minute questions.
Thanks so much, Jakob. Really, really wonderful talk. I'd love to open the floor for questions as well. And anybody? Perfect.
I just had a quick question. You tested out the paper that you presented earlier on the prisoner's dilemma. I was kind of curious to know how it would work on like more complex environments like Hanabi or something.
Yeah, so this is the MFOS paper, I assume, the model for opponent shaping. We're currently working on scaling this. So we've scaled it to grid worlds, and we're seeing so where the limits are. You can imagine that the meta-learning process obviously requires a lot of samples. I believe as long as the environment is cheap to model, so you're not modeling StarCraft or something, this would be fine. On Hanabi, now it's fully cooperative, so I don't think we need model for opponent shaping because everyone's aligned, right? There's no misaligned incentives. So in that sense, I think Hanabi wouldn't be my first goal, but scaling it to something like a rich general sum environment would be really interesting. And if you have any ideas or interested, please reach out. I should say all of the code is open source as well. So if you want to do some follow-up work, I don't have my website here, but it's foersterlab.com. All the work is linked out there as well. Great question. Thank you very much.
Thank you.
Any other questions? I guess I've got one while folks are still thinking. So even in, prisoner's dilemma, pretty clear that the strategy space is, fairly large, especially with the histories, and when all the policies are being parameterized and so forth, I can imagine that there might be kind of some complexities to, multiple equilibria and so forth. And so you described a technique for kind of annealing. It sounded almost like a homotopy method or something to kind of stabilize the learning here. But I'm kind of wondering how, if you encounter difficulties in kind of multiplicity of equilibria and maybe even locality of equilibria.
Yeah, so this touches on a lot because ultimately the question is if you're going to deploy these algorithms. So maybe one step back. What do we like about meta self-plane MFOS? While others are doing naive learning, it's quite easy to be naive learners. And I think that's a good thing because that incentivizes others to switch away from naive learning. Because truth be told, we shouldn't be doing naive learning, right? Because we know the naive learning has a lot of pathologies when it gets to multi-agent settings. So it's disincentivizing naive learning is a good step. The second question is, as more people start doing MFOS, start shaping each other, to what extent can we guarantee that we'll get to a socially beneficial outcome or to a good equilibrium in this game, right? And there we're at the very early days. So far, we have found that doing this tracing procedure, we get repeatable, reliable equilibria. But this is something that where we're just starting to think about how to model this from a theoretical point of view, both in terms of sample complexities, how long does it take in principle to converge to a meta equilibrium here, and in terms of which equilibrium this will be in a complex game, right? And clearly in the IPD, as you correctly said, there's an explosion of possible strategies as I increase the history length. So keep in mind, all the results I've shown you were for one step prisoner's dilemma, where we just have one step of history, right? And even how to sort of start formalizing this and get theoretical bounds in an infinite long history prisoner's dilemma might be quite challenging. So it's early days. I think it's an interesting approach that gets around all the challenges of opponent shaping in derivative-based methods, shaping methods. But there's obviously huge scaling challenges here ahead. So I think it's an exciting area for both empirical and theoretical work, if anyone is interested. Great question. Thank you.
Gotcha. Thank you. And thanks again for a really wonderful talk. I think our schedule is probably we should start to switch to the next speaker, but thanks again for a wonderful talk.
Great. Thanks for interacting. This was really fun. Much appreciated.
Yeah. You good? Okay. Cool. It's okay.
All right. Great. Yeah, thanks a bunch, Jakob. So I'm going to introduce our next speaker. Next, we have Eric Mazumdar. I think he's online. So Eric.
Hi, how are you?
Okay, great. Start sharing. Yeah, so Eric is an assistant professor in computing and mathematical sciences and economics at Caltech. So before joining Caltech, he received his PhD in electrical engineering and computer science at the University of California, Berkeley, advised by Shankar Sastry and Michael Jordan, the engineer, not the basketball player. And he received his undergraduate degree at the Massachusetts Institute of Technology. So his work bridges the fields of machine learning, economics, and multi-agent systems, and he brings optimization, controlling game theory to bear on challenges ranging widely from developing intelligent infrastructure, facilitating online markets and e-commerce, and even delivery of healthcare. So Eric kind of stepped in at the last minute to fill a gap that came up in our schedule. So we really appreciate that. And with that, Eric, you can take it away.
Great, thank you. Hopefully everyone can see the slides, the proper presenter view.
Yeah, we can see him.
Okay, great. So yeah, thank you so much for having me. And I think the talk I'm going to give today is actually, somewhat related to some of the topics that Jakob just covered. So I'm going to talk this title is very broad, and I think that the actual work that I'm going to talk about today is a little bit more focused. But I'm going to focus on the problem of machine learning when your data is being strategically manipulated. And I'm going to talk about the importance of understanding the underlying dynamics in these problems and kind of the implications for algorithm design. So I'm going to start with a very, very obvious observation, especially nowadays, that we're increasingly interacting with learning algorithms, either unknowingly or knowingly, every single day. So if we're ordering something on Uber Eats or reading a news article on the internet, running in the background is some form of a learning algorithm, and I think this just goes to show how these algorithms have really been deployed across everyday life. But as these algorithms are deployed into situations in which they increasingly interact with people, we're seeing more and more problems pop up. So this is one of my favorite examples. It's coming from Uber and Lyft, where Uber drivers have actually started gaming the surge pricing algorithm in this phenomenon known as Surge Club. And so what happens in a Surge Club is that groups of drivers will go to a certain part of the city. So in this case, it's Beverly Hills. They'll turn off their Uber apps at the exact same time. The surge pricing algorithm notices it's lost a huge supply of drivers. And so to get more drivers in that location, it starts surging the price of the location. And then in response, the drivers who are already there just turn on their app again and collect the higher surge price. So as the person who designed the search pricing algorithm, this is something that this is not something I really wanted to happen, because these drivers are effectively just gaming the search pricing algorithm. But I think this just goes to show the kind of complex behaviors that algorithms actually have to deal with on the part of people when the algorithms are actually deployed into the real world. The second kind of example I want to show is really how the data itself can be strategically manipulated in kind of important ways. So this is an example from this study that was done in Colombia, where they wanted to give subsidies based off of these poverty index scores that they had calculated. And so basically they calculate these poverty index scores for this population. If you were slightly above this red threshold, even above this red threshold, you'd get some subsidy. If you were below, you wouldn't get anything. If you were below the threshold, you would get something, and if you were above, you wouldn't get anything. So in 1994, when they first came up with this program, you could see the distribution of these scores is, nice and Gaussian. Same thing in 1997. Then in 1998, something a little bit strange happened. The explicit algorithm for how they calculate this poverty index score and and the actual threshold for which they gave these subsidies was released, basically. And then you see that people immediately start gaming and kind of misreporting their data to get basically just on the the lower side of this threshold to get the subsidies. And by 2003, this poverty index score that they had come up with, this metric, was essentially totally useless. And I think this just goes to show how if people have some have skin in the game, they will go to some lengths to misreport data. And I think that for the most part, our algorithms are not really constructed to deal with these type of issues. So I could go on with these types of negative examples, but I think the takeaway is that our learning algorithms will inevitably be faced with strategic agents, and we need to adapt our algorithms to deal with these types of situations. So any questions? And feel free to jump in whenever you want. It's kind of more fun if these are more interactive or something like this. So, but to understand how these problems all pop up, I want to go back to what I think of as the traditional machine learning paradigm. And that's a situation where you have a decision-making algorithm taking in data and making decisions in basically static environments. So the distribution of our data isn't changing, the environment is essentially stationary, and so on. And I think this is really not the types of situations in which our algorithms are being deployed. Our algorithms are being deployed in environments that look a lot more like this, where we have algorithms that take in data and make decisions in uncertain dynamic environments that are evolving over time. And these algorithms have to interact not just with other people, but with populations of human decision makers who might have their own objectives. And so dealing with these types of situations is really the core of my work. And I think in today's talk, I'm going to focus on one problem in this kind of regime. And that's about how you might learn from strategically manipulated data. And the overarching question I kind of want you to keep in mind here is that if agents can adapt to deployed models over time, what types of solutions can decision makers hope to achieve? And this is joint work with Tiana Zernick at Berkeley, Shankar Shastri at Berkeley, and Mike Jordan at Berkeley. So this work kind of lives in this regime of strategic classification in which we have a decision maker or a machine learner who wants to minimize some kind of prediction loss or some kind of classification accuracy. And so they deploy a predictive model into an environment. And strategic agents who want favorable predictions out of this decision maker will strategically manipulate their data to get their outcome. And so you basically get this kind of feedback loop between a decision maker and a population of strategic agents. So the important thing in this model of strategic classification is that both sides are adapting to each other's actions. So strategic agents and the decision maker both adapt to each other's actions. And for those of you who come from more of a machine learning or deep learning background, this is really basically a way of studying a form of distribution shift, but a very structured form of distribution shift, which is distribution shift that's arising due to strategic manipulations of data. And the overarching question in strategic classification is, how do we what equilibrium solutions are natural for these types of interactions, and how do we actually achieve them? So, yep, was there a question? No. So to just introduce a little bit of notation to this problem, we're going to have the decision maker who's going to optimize over the parameters of our machine learning model. So you could think of this as being neural network weights or linear regression parameters or anything like this. And the strategic agents are going to optimize over this parameter mu, which might be a summary statistic of their data. So we're going to summarize the entire population of strategic agents by just one parameter. And then the decision maker wants to minimize, as I mentioned, their prediction loss or their classification accuracy, which depends both on the distribution of data and their current model. And strategic agents will also want to maximize their utility or minimize their loss. That depends both on the current model deployed by the decision maker and their own action. So existing work in strategic classification, and this goes back to around 2016, has basically exclusively modeled this type of interaction as some form of a Stackelberg game. And a Stackelberg game is this kind of strategic interaction in game theory where one player, the leader, has kind of commitment power, and so they can move first and commit to a strategy. And the other player, the follower, moves second and can respond, given the leader moves first. And importantly, in all of the past work in strategic classification, the decision maker or the machine learning model was always assumed to be the leader, so to have commitment power. So what this actually means is that the interaction kind of goes like this. You have a decision maker who gets to announce their predictive model or commit to a machine learning model, theta. And then a set of strategic agents who get to observe this machine learning model and then choose their data to respond. And this was basically motivated from the study of how you should come up with credit scoring systems or admission systems, where a decision maker might announce a credit scoring system to give loans. And then agents would take actions to improve their credit scores, or decision makers might announce an admission system, and then agents would take actions to improve their chances to get admissions to colleges. So given the setup, the right thing to do, or in the kind of game theoretic framework, or what basically rational agents should do in this kind of Stackelberg interaction, is kind of to work backwards. So the strategic agents, given the deployed model theta, will basically best respond by solving this problem here. So they'll choose this mu as the best response to the given theta. And then the decision maker basically has to optimize their Stackelberg risk, which is this loss, but where mu is constrained to be along this best response curve. And if they can actually solve this optimization problem here, they'll get to what's known as a Stackelberg equilibrium, where the decision maker is leading in the game. So the main problem in strategic classification is that this best response curve is not known a priori, because there's no reason why the decision maker should know the utility of the population of strategic agents. And so there's a question about how the decision maker should optimize this loss here. So the solution in a lot of the strategic classification literature has been to basically learn through repeated interaction with an environment. So the decision maker gets to repeatedly interact with a set of strategic agents to find a Stackelberg equilibrium. So at each time, the decision maker gets to output a machine learning model theta, the population best responds, and through this kind of interaction, they get to the decision maker gets to optimize. And so the goal in basically a lot of the past work in strategic classification was basically to optimize through these interactions with the environment using, let's say, like gradient algorithms or something like this. So one of the problems with this model is that it's a little bit too simplistic, and that agents are assumed to instantaneously know how to best respond to deployed models, which I think is a little bit strong. And this might be an okay model for slow processes like loans or college admissions, where you're not going to change the criteria for getting a loan very often. But I don't think this is a very good model for online interactions like e-commerce or social media platforms, where the underlying algorithm can, really adapt to small changes in populations. So, in the work I'm going to talk about today, we generalize this model of strategic classification to allow basically both players to gradually learn on their own timescale. So in particular, we're going to have the population of strategic agents operate on this timescale, S, the decision maker operate on this timescale T, and in particular, they'll be kind of on, they'll be on different timescales, and mu won't always be your best responding. So to bring a little bit of structure to this problem, we're going to assume that the agents in this problem are no regret learners. No regret meaning that they'll optimize whatever sequence of functions basically that they're presented with in this no regret sense, or equivalently, if the machine learning model is fixed for long periods of time, they'll basically learn how to optimize it. In kind of in an asymptotic sense. So we'll focus on two kind of relevant modes, or two relevant modes of relative timescales. The first is where the decision maker is much slower relative to the agents. And we'll call these decision makers proactive. And this is going to be the case where the decision maker makes very few model updates for how fast the distributions of strategic agents changes. And so basically what you could think of is this lets us recover the original strategic classification context, because strategic agents basically get to see the model as fixed. And this is, again, a good model for college admissions or credit scoring. But maybe the more interesting case is when decision makers are really fast relative to the agents. So they get to make a lot more updates of their models and basically track change in the distributions in real time. And this is a much better model for like online platforms like YouTube or Instagram, or even the surge parsing algorithm at Uber that I mentioned, because there can be very reactive to small changes in the distributions. And because of that, we're going to call these decision makers reactive. And something I really want to point out here is that oftentimes, especially nowadays, decision makers actually have the choice of which of these situations to be in. They can update their model very frequently or very infrequently. So they get to essentially choose which of these two extremes they are in. And what we can actually show is that both of these extremes end up in vastly different game theoretic equilibrium. So what we show in this paper is that by tuning their update frequency appropriately, the decision maker can use really simple learning rules to basically drive no regret strategic agents to a Stackelberg equilibrium with either order of play. So at equilibrium, it's actually possible for the agents to lead and the decision maker to follow with their best response, which is, the flipped equilibrium compared to a lot of the strategic classification literature. And we can even go slightly further, and we could actually show that in several standard, simple learning settings like linear regression or logistic regression with strategic manipulations to the data, both sides of this game actually prefer the equilibrium where the strategic agents lead and the decision maker follows. So actually, both sides of this game have higher utility or lower loss at this this new Stackelberg equilibrium for this types of interaction. So I'll give you a little bit of insight into the actual theorems, but any questions about the actual results so far?
Any questions? Online?
Cool. So I'll dive into a little bit more of the details. So basically our results just assume that we have sufficient, regularity on the loss functions, and that the agents are no regret learners. And then we can show that basically if these epochs, which are the amount of time that elapse for the strategic agents between updates to the machine learning model, are large enough, then if the decision maker uses these black box online optimization algorithms, then they can actually learn to lead the strategic agents to a Stackelberg equilibrium where the decision maker leads. And this is kind of important that they use these black box, online optimization algorithms, because they're the only way that they can actually learn to optimize through the best response of the agents. And so the underlying assumptions for this theorem is that the decision maker doesn't know the utility of the strategic agents, or in fact, this best response function, which, as I mentioned, is why they have to use these black box algorithms. And we have to assume that, these epochs are large enough, essentially. And we can actually give finite time convergence rates by assuming certain no regret algorithms on the agents. And we can even give lower bounds on the length of the epochs for all these results to go through. And the ideas behind the proofs are really just ideas from 2 timescale stochastic approximations in online learning. So the case for reactive decision-making is essentially very similar. We're going to assume sufficient regularity on the loss functions and that the agents are no regret learners. And then this time, if the decision maker just does online gradient descent at a much faster rate than the population is, updating, then the distribution is changing, then this game will actually converge to a stackable equilibrium where the agents lead. So the order of play is flipped. So as I mentioned, this was the new equilibrium for the strategic classification literature. And in the remaining part of my talk, I'll actually show that this equilibrium actually is better off, or all the players are better off at this equilibrium. So any question on kind of the first part of the talk, which is really saying that the update frequency in these strategic interactions, or the relative update frequency of the 2 sides in the strategic interactions, is actually very important because it lets you select for different types of game theoretically meaningful equilibria.
Yeah, quick question, Eric. So can you give some insight into, is there some land in between, like if the frequency difference is not so great, what happens?
Yeah, that's a very good question. So if the frequency difference is let's say we're kind of exactly in between, and so they're updating at the same rate, then you would be in kind of more of a Nash regime. It's not exactly a Nash regime. The problem there is you might not get convergence in general, even if you have convexity of the player's loss functions. And so this kind of timescale separation is really important because it allows you to get convergence results. Because one player gets to see, or one side gets to see the other one is essentially fixed and equilibrate to them. And then the other ones can basically, learn to lead those people to equilibrium. So in between, you would think that maybe you could get to a Nash equilibrium if the structure is right. But, as we know really well, you don't really have any guarantees of convergence in those regimes.
Thanks.
Does that make sense?
I have a question too.
Yep.
Hi, Eric, by the way.
Hi.
Anyways, so I haven't really parsed this like no regret assumption that you're making, but it seems like, are you assuming that the kind of best response is unique valued and that both players are playing the kind of global optimal of the best response?
Yeah, that's a very good question. So that's one of the main assumptions here, and I was actually going to get to it at the end. One of the assumptions here is that the best response is kind of always unique and it's smooth in the leader's decision variable. And so without those assumptions, the problems become kind of very hard to solve, as I'm sure you're aware. You could have kind of discontinuities in the best response function, and things like that. So you need basically smoothness and not necessarily uniqueness, but really smoothness and kind of global optimality.
Sure. Yeah. Okay. Cool. Thanks.
Actually, I have a follow-up question, maybe on Forrest's question. Thanks, Eric, for the interesting talk. So I was wondering, what are your thoughts on like the level of rationality that you're assuming for the population? So you're assuming that the population is playing best response in the sense that they're perfectly rational, but what do you see would happen if like the agents are like boundedly rational, or they're approximately playing Nash equilibria or like best responses?
Yeah, that's a really good question. So here we're assuming that they're no regret, but that, in the end, they'll converge to a best response. So they're rational in that sense. But actually, the takeaways will go through even if they're not playing a best response, but they're kind of playing some kind of smooth response. So you don't actually need, none of this really requires, or, the convergence results in the first case really require the agents to be best responding. They could just have some kind of response map that's like unique
Mhm.
value, that's uniquely given, and smoothly varies with the decision of the outer player, and those results will all go through. So I think in that case, kind of approximate best response models or bounded rationality might actually be, help you in certain cases, and it would all go through in these types of results.
Yeah, exactly. I feel like maybe those actually, help you get around some of these issues that you're having with something like best responses.
Yeah, exactly. So, when the best response is discontinuous, assuming that the agents are, approximately best responding or doing some kind of, bounded rational thing might smooth out the best response curve. And so a lot of these results might go through.
Exactly.
Yeah, so I think that, that should go through, is at least my guess. In this case of reactive decision making, it's a little bit harder to make that claim, because what we get out of this no regret assumption is that because no regret agents learn to optimize through whatever sequence of functions they see in the kind of a black box way, they will actually learn to optimize through the best response of the machine learning model. And that's actually a very powerful thing that we get from no regret agents. So I'm not sure how assuming they approximately best respond or something like that would go through in this case. But it's an interesting question.
Thank you.
Cool. Thank you. So yeah, as I mentioned, in general, any order of play can be preferred by any player. But what's well known is that leading is no worse than the best Nash equilibrium in most of these cases, especially under our uniqueness assumptions. But oftentimes, by assuming some more structure on the player's losses, we could actually say something a little bit stronger. So an example of that is in zero-sum games, where just by the basic max-min inequality, we can actually say that following is never worse than leading. You always prefer kind of being the inner player in a zero-sum game if there's no Nash equilibrium. And so we were curious about, what can we say in these more machine learning contexts? And so, this is going to be a slightly toy problem, but I think it's pretty illustrative. So we'll have, two populations of agents, these green agents and these red agents. You could think of them as being kind of news sources. So these green ones might be legit news sources. These red ones might be fake news sources. And you'd like to design a classifier to basically tell one from the other. The problem is that, the people who do fake news all have an incentive to not be classified as fake news. So maybe, they will manipulate the features of their news article to be properly classified. So, so in this case, all of these red agents are going to be our strategic agents, and they want to basically maximize their classification, get on the positive side of the classification boundary here, subject to a constraint over how much they can move. And we're going to assume that all of these red dots will move by the exact same amount. And what we can say in this game actually is that both players actually prefer the Stackberg equilibrium where the agents lead. So both of these players have a lower loss at the Stackberg equilibrium where the agents lead than the Stackberg equilibrium where the agents follow. And we can actually show that these inequalities are all strict in certain cases. And this is true even in other kind of linear learning settings. And so just to give you some intuition, we could actually, vary the proportion of strategic agents. And we see that there's sometimes quite kind of a big gap between these two Stackelberg solutions. So, these dotted lines are the two Stackelberg solutions, and their associated losses for both of these players, so the decision maker and the agents. And we can see that there's, a big gap that depends on the proportion of strategic agents in this problem. And that when we, actually implement the algorithms that we said, the agents are no regret, the leader does some kind of gradient descent without a gradient type approach, we see convergence to these Stackelberg solutions, depending on the update frequencies. So to wrap up, I we basically showed that if agents are no regret, a decision maker can lead the game to a stackable equilibrium with either order of play. So if the decision maker updates really slowly, they can actually learn to lead at equilibrium. If they update very quickly, they can actually follow equilibrium. And choosing between the two of these is actually oftentimes a design choice. So at least to me, the really high level takeaway here is that classic machine learning assumptions can stop holding in strategic settings. So, in particular, in this case, learning faster might not always be better. And so it might not always lead to better outcomes because of the strategic interactions that underlie the interactions in these games. So again, I kind of just want to do a plug for some upcoming work where we have generalized some of these insights to come up with a first order algorithm for bi-level optimization problems, or just Stackelberg problems of this form here, where you'd like to minimize some function subject to this best response. If this is smooth and single valued, or if the best response is basically sufficiently smooth and single valued, we can get finite time rates to the local optima of this loss here without assuming there's any kind of convexity here. And even better, we could actually show that the loss at this lower level, you don't actually have to know it. You just have to, or even have an oracle to differentiate through this best response function. You just need basically a convergent algorithm on the lower level. And you could even kind of replace this argument on the inner problem to just a solution to a variational equality problem, which lets you extend this to incentive design problems where you don't even have to know the utilities of the inner of the agents. So with that, I just want to wrap up and say, we've only really scratched the surface of this kind of interesting area at the intersection of economics, control, and algorithms. And so I'm happy to answer any questions. And yeah, thank you for listening. Any questions?
Right. Well, thank you for the excellent talk, Eric. Do we have any questions from the audience, either online or in the room? Okay, I guess I have one question. So it was really interesting, this result that it's preferred for the agents to lead. Can you interpret that in I guess kind of like a practical way? Does that mean companies should kind of spur the agents to react, in some ways? Is there some does that mean that companies or governments or whatever should be actively trying to information gather and get responses from people or something?
Yeah, so actually the fact that the agent should lead is actually interesting from the company side, because it basically says that oftentimes it might be better to allow people to get more information over your algorithm. So you should keep your algorithm essentially fixed for periods of time to allow people to actually understand how the algorithm works. And at least in that logistic regression example, one of the reasons why it was better off for everyone is because we saw the amount of strategic manipulations that occur at that stackable equilibrium where the agents are leading is actually lower than at the other stackable equilibrium. And so since they're basically manipulating less and getting kind of about the same amount of outcome, kind of everyone's better off.
Interesting. So would it even mean that you might want to publish your algorithm open source in some way?
Yeah, I mean, maybe that's one of the takeaways. But I also think something pretty important is that these relationships really depend on the underlying structure of the utilities of the two players. So if agents, in a way here, the strategic agents, it wasn't exactly a zero-sum game, but it had kind of flavors of an adversarial interaction. If it's not like an adversarial interaction, and they're misaligned in a different way, this preference might change completely. And so I think it just means you have to be very careful in how fast you update your algorithm and things like this, even in these real world scenarios.
Interesting. Cool. Any other questions before we move on to the?
So actually, I wanted to ask if, Eric, can you elaborate more? I think you kind of pointed to this in your response to Zach, but I was actually curious about your thoughts on the importance of this update rate or the update of the models in different kinds of equilibria. You talked about a Stackelberg equilibria, but I was wondering if in a non-cooperative setting, agents are reaching a Nash equilibrium. Do you see these type of sort of scenarios coming up in other types of equilibria, or do you see this as mostly being relevant to Stackelberg equilibrium when one agent is leading, the other is following?
Yeah, that's a good question. So we've seen this type of like the importance of these kind of timescale separation type arguments in zero-sum contexts when you're just trying to optimize for Nash. Basically, if you don't have sufficient timescale separation in a non-convex, non-concave game, you could converge to equilibria that are not, Nash or Stackelberg and just spurious equilibria. But if you have sufficient timescale separation, you could actually show that you only converge to, local Stackelberg equilibria or local Nash. So we have seen the importance of these different rates just in that setting for Nash. But in general, I think it makes a lot of sense in the Stackelberg regime because, if one person updates much slower, they look essentially fixed. So that essentially gives them some kind of commitment to a strategy for a certain amount of time. And so you kind of recover the underlying Stackelberg structure.
I see. Thanks.
But, some of Lily and Ratliff at UW has had a lot of success on kind of understanding the importance of these timescale separations, even for different types of, maybe not Stackelberg, but these conjectural variations type equilibria, where your opponent might not be, optimally best responding, but might be following some kind of other map. And again, timescale separation really helps you there because they can, respond given that you're fixed or something like this.
Very interesting. Thanks, Eric.
Great, thank you.
All right. Well, it looks like it's about time to move on to the next thing. So thanks again, Eric. Really appreciate awesome talk.
Thank you so much.
And, we'll move on to the first series of speakers or contributed talks. So I think Nagar, I think you're in charge of this session. So
yes. But I need help from you, Zach, because I don't know how many of our speakers are in person. So if you see questions from the audience or if you have in-person speakers, please let me know.
And so the first speaker is in person here. So we'll have you can just share on Zoom.
So just to reiterate the logistics that David mentioned, each speaker is going to speak for 10 minutes. And then we have the joint question and answering for about 10 minutes for all the speakers in each of the talk sessions. Our first talk is titled Robust Forecasting for Robotic Control, a Game Theoretic Approach by Shubhankar Agarwal. So we are excited to hear from you.
Thank you. Can everyone hear me?
Right. Hello, everyone. I'm Shubhankar. I'm a third-year PhD student at UT Austin, and I work with David Fedrovich Keel and Sandeep Chinchili. And this is our work on robust forecasting for robotic control, a game theoretic approach. And using recent developments in game theory, we solved the problem of robust forecasting in robotic control applications. Let's start with motivations. So robots deployed in real world need to generate accurate forecasts and make decisions under uncertainty. So for example, a self-driving car here, which needs to complete a lane change maneuver with this blue car, only observes, let's say, this bold yellow line in the training data set. But in real world, this blue car can take multiple trajectories, as shown in the highlighted yellow lines, where it can complete the lane change earlier or complete the lane change later. So in real world, our robots deployed robots need to be robust against these different distribution shifts, which we might not observe in the real world data. Current methods we use rely heavily on using historical time series to predict the future, but completely relying on history can be problematic. It could be corrupted due to like noise in sensor, have outliers, and like I showed in the previous slides, it might not completely represent all the possible outcomes. In the case of self-driving cars, you can have sensor noise in the sensors like LiDAR, or there could be human labeling errors. And current methods which we employ to to help with these things are like we add noise to our data, or we like try to collect more targeted data, which might be either expensive in the case of collecting more data, or it might not scale or help us with auto distribution scenarios. So in this work, we consider a parameterized forecaster and a model-based control policy. The forecaster takes in time series waypoints, SH, and predicts future waypoints, S hat F, and the controller tracks these forecasted waypoints and generates optimal controls U hat. And it also assesses the quality of these waypoints by the control cost JC. And we aim to find a forecaster which is able to generate robust forecasts for these all possible histories, SH. In this work, we introduced an hypothetical adversary to model measurement noise we might have in our sensors, or like observed history, or like account for different unobserved histories which might not be in our data set. So in this, our adversary takes in the history we might have observed SH and outputs an adversarially perturbed version of it SH-AD. So we formulate this as a saddle point problem, and our objective consists of 4 parts. The first 2 parts account for the change in the cost of using corrupted forecast instead of uncorrupted forecast. So in the first term in our objective, this is the cost of generating controls U hat for a given predicted forecast S hat F, which I showed in the previous slide. And we see what would be our controls if we would have used the ground truth forecast, which is the second term. And this models the change in difference in states and controls if we use different forecasts. Third term is just the error in our forecasting, which is the difference between ground truth forecast and the predicted forecast. And the last term, we control the power of our adversary by penalizing large deviations from the original history. And at the bottom, I show the problem we solve, which is a saddle point problem. The adversary tries to find parameters which maximizes this cost by adversarially perturbing the history such that the forecast generated by the forecaster incurs a higher cost, and the forecaster generates forecasts which leads to lower cost, given the adversarially perturbed history. So as such, they play a game. As such, like the forecaster needs to be robust to these different histories and learn to minimize its cost. So we see that this could be formulated as a 2-player zero-sum game, where a forecaster chooses actions theta F, which are the parameters of the forecaster, to minimize the cost, and the adversary chooses actions theta A to maximize the cost. So the forecaster's goal is to predict relevant future states despite the perturbations of the adversary. And the adversary's goal is to generate adversarial perturbations to the history such that the forecasts generated by the forecaster incur a higher overall cost. Some preliminaries, so we define the notion of global Nash and local Nash, which are very common definitions in game theory. Intuitively, global Nash is a point in the space of player strategies where both players cannot change their strategies without achieving a less favorable outcome. And similar to that, local Nash, this is only true in a small set of player strategies for local Nash. So it's like locally relevant only. And the way we characterize the local Nash equilibrium has two conditions. First order condition says that the gradients of our objective need to be zero with respect to both the player parameters, in this case theta f and theta a. And second order says that our Hessian of our objective with respect to the min player needs to be positive semi-definite, and with respect to the max player it needs to be negative semi-definite. So in order to train our method, in order to train our forecaster and adversary and find the saddle point, we use gradient descent, and this is some of the good work done by Eric and Lillian we use for this. So both the players take alternative gradient steps. Forecaster uses gradient descent to minimize the loss. Adversary uses gradient ascent to maximize the objective. And like I said, we use recent developments to show that this game will reach a local Nash equilibrium. And what this means is within a small neighborhood of the forecaster and adversary parameters, we have the strongest forecaster, we have the most robust forecaster for the strongest adversary. So for our experiment setup, we used real-world lane-changing scenarios. This was collected when two players were playing a game to complete a lane change maneuver on a driving simulator. We use two-layer linear networks for both forecaster and adversary with real activations. Our control policy is a differential map of a model predictive controller, which we implemented in CVX layers. We played this game with forecaster and adversary and low speed trajectories. And in order to demonstrate that our forecaster is robust and is able to generalize to auto distribution scenarios, we tested this on high speed trajectories. So we compared 4 different forecaster shown in different colors. So on the top, we have original, which is just training all the forecasters on low speed, training the forecaster on low speed trajectory to simply supervised learning. Second, we see that if I add more data, which is very similar to my train distribution, does it help? So that's a data added model. What if I double my training data? Third is if I just add random noise to my history instead of adding like this adversarial noise, that's a green model. And lastly, our robust model is in red. We have different test data types in the x-axis and the objective and y-axis. So in the first, in original set, we're just testing different forecasters on low speed trajectories. They all perform similarly, which is as expected. Second, we test if how do different forecasters perform with random noise to the history, where the green model, which is the random forecaster, performs the best, which is expected because it was trained on that. But our robust forecaster in red is able to perform very similarly as well. Third, we test that instead of what if we perturb the history with our most adversarial, like with our learned adversary, and what happens then? And you can see here that all the models perform, all the forecasters don't perform as well. That means that our adversary has learned perturbations which are adversarial for other forecasters. And our forecaster in red performs the best because it was trained on these adversarial histories. Lastly, this is the key result of our paper, where we show that what happens when we test our robust forecaster on high-speed trajectories. And here we show our forecaster in red achieves 30% better cost than random forecaster, showing that it has learned to account for high-speed lane change maneuvers in this case. So some takeaways. So our game formulation allows the adversary to add targeted perturbations, which are most adversarial for the forecaster. And we show that just adding random perturbations might be benign for the end controller. Thank you. This is the QR code to the paper.
Thank you so much, Shubhankar. Please stay around because we will be asking questions and have like a Q&A. But for now, we move on to the next speaker and Sarah Lee, who's going to talk about collision risk-based congestion game for air traffic management.
Hi, can you hear me?
Yes, we're good.
Okay, great. Yeah, thanks for having me here virtually. I'm excited to participate. So my name is Sarah, and I'd like to present some of this paper we have on collision risk-based congestion game for air traffic management. This is with my collaborators, Avi Mattel, Pierre-Louis Garroche, and Betche de Chikmesse, and we're from the University of Washington and the School of Civil Aviation from France. So I want to introduce air traffic management as a multi-agent trajectory planning problem. And essentially the problem is how to get a massive number of aircraft from a predetermined set of point A's to point B's in this shared operation space. So there's a couple features that characterize this specific setting. One is collision risk. Aircraft do not want to crash, so they will sacrifice optimal routes for suboptimal ones if it's safer. The second is disruptions and uncertainty. If you've ever taken a commercial flight, you will know that they get canceled or delayed for all sorts of reasons. And sometimes it could be very bad. For example, this past summer, we had global flight delays that caused a lot of inefficiency. And lastly, this air traffic management problem is a very large problem. Every day, tens of thousands of flights take off and land in this shared space. So another thing I'd like to point out is that although we're targeting air traffic management in this problem, these features of collision, disruption, and scalability are common in a lot of industrial settings where multi-agent trajectory planning are being deployed. And some examples include robotaxis on roadways and automated warehouse logistics. So the objective in this paper is to come up with a model, a game model that trades off optimality for collision safety, handles environmental uncertainty and disruptions, and ensures that individual flights achieve the best possible landing time. To do this, we formulate and solve this air traffic management problem using an MDP or Markov decision process congestion game model. And so in the following slides, I will introduce Markov decision process using an aircraft trajectory planning example. We'll formulate the collision risk that under this MDP formulation can solve the resulting congestion game and demonstrate our algorithm on the historical flight plan over the French airspace. So to start, let me introduce the Markov decision process. So here, suppose we have a plane trying to get from point A to this green star over here. And the states would be just physical locations. So, longitude, latitude, and flight level. The actions are going to be these finite kind of next set of points you can reach in the current waypoint. And so these are typically given in standard air traffic planning. The plans are generated from a finite set of waypoints and possible transition edges. So this is like discrete set of state actions. We have transitions, which are potentially stochastic. For example, if a plane takes off or plans to take off at 1 p.m., it could still be on the ground by 1:30 because of whatever uncertainty there is. And finally, we have this cost term, which models which is how the plane would use to determine the optimal trajectory. So here we assume that there is an existing flight plan that was generated by the Air Traffic Management Authority that the plane would like to follow. And so at every time instance, there is a cost that's going to be 0 for one of the waypoints. And for every step away from this waypoint, edge away from this waypoint, the cost increases by 1. So that effectively the plane would we form this kind of potential well in cost around the plane's optimal trajectory. And because this is the trajectory will move in time, at the next time step, for example, the waypoint that has a cost of 0 will be the one following, and then the costs change accordingly. So from this, each player are then solving this MDP for the minimizing the expected cost over a finite horizon. So where we're going is we're trying to couple these individual plane or flight MDPs with each other, and we're going to couple them through their cost. And so I just want to introduce kind of like the variable we're coupling through. We're using this MDP state action density, which is the joint probability of an agent or a plane being in a state action at a certain time. And I just want to distinguish it from the policy, which is the conditional probability of taking an action if you're already at a certain state. So state action probability, we believe, is a little bit more accurate in terms of predicting where the agent is, and so also to predict collision likelihoods. So here is a demonstration, for example, the policy on the left here. Let's see if I can get a marker. So on the left here, we have the policy of the red plane, and you can see that the red plane would have 10% chance of taking this top right edge, 80% chance of taking this middle one, and 30% chance of taking the left one. So here you notice that they don't add up to 1, but they don't have to, because these are policies originating from different states. However, we can also look at the state action probability of the red plane, and we can see that the plane actually, even though it only has 10% probability of taking the top right edge, it could have a higher state action probability of being at that transition at that time. And so this means that, in fact, the collision likelihood over this top right edge will be higher than the bottom 2 edges. So with each agent or plane's state action probability, we'll now kind of add on to the initial task completion cost that originated from the flight plans. And we can actually formulate this exactly as the probability of encountering at least one other plane in any state. And so it's just, I guess, to run like the probability idea. If I take a certain state, and its state, like, if I sum over all the actions and I get like the probability of the red plane being in this state highlighted here, 1 minus that will be the likelihood that the red plane is not here. So then if I take the product of all the planes, that would give me the likelihood that none of the planes are being in the state simultaneously. And now if I take 1 minus that, that gives me the probability of at least one plane, any plane, being in this state at this time. So we can basically formulate this collision risk with at least one other plane using these state action probability distributions. And from this, we could think about adding it to the original task completion cost as a congestion cost. And it could be as simple as just taking a scaled version of this cost here. So with that, we now have this variable Markov decision process cost. So we can take a look at how this might change kind of dynamic programming, which is how we solve MDPs. So looking at just finite horizon value duration with a changing cost, we can see that this congestion cost effectively just adds to the existing kind of task cost that you incur each iteration. And because of this, that means the Q value is now dependent on all the players' strategies. So even if if I am this green plane over here, if I've chosen a certain strategy and currently it achieves the best Q value functions, if other players change their strategies, then that will cause my Q values to change, and I may no longer take the best action. So kind of from this perspective—
1 minute left, please, time your presentation accordingly. Thank you.
Okay, sorry. Okay, so yeah, so from this perspective, we can think about what is Nash equilibrium. And we can basically formulate a condition for Nash equilibrium using these Q-value functions. And the contribution in this paper is really showing that when we have these collision risk-based congestion costs, we can come up with a potential function where it reduces the original problem down to a single optimization problem. I just want to point out quickly that this potential function is going to be a non-convex function. And so this problem effectively is it's a non-monotonic game with a non-convex objective, but it's smooth and it's confined to a finite space, a compact action space. And so there will be solutions, but we don't know how many. So I guess just want to run over the results quickly then. So we can solve this for large scale problems. And even though we can't guarantee finding global Nash equilibrium, we can find the local Nash equilibrium. This is demonstrated for some historical flight data using over the French airspace from 2017. And we can see that if we run our algorithm for less than 50 iterations, we can reduce the flight risk from a high of 80% to less than 3% for all the flights, and reduce the number as well. Yeah, so that's my talk. I hope I made it on time. Thank you.
Great, thank you so much, Sarah. Very interesting talk. So now we move to our final talk for this round of contributed paper talks. Our next talk is titled Cautious Markov Games for Interaction-Aware Robotics by Rohan Sinha.
Let me just get it set up here.
Okay.
All right, can everybody see my screen? Cool. All right, so hi everyone. My name is Rohan Sinha, and today I'm presenting work with Professor Sanjay Lal at Stanford University that we're calling Cautious Markov Games for Interaction-Aware Robotics. So just to set the stage a little bit, we are motivated by a need for interaction-aware planning methods for autonomous vehicles. These are methods that intelligently reason about the effect of an autonomous vehicle's decisions on those of nearby agents. These existing game theoretic methods have become very popular in this domain, but these methods often neglect the influence of traffic rules on interactive formulations, even though in our view, rules often help us negotiate complex traffic. Therefore, we present a framework for incorporating traffic rules into multi-agent decision-making problems and show in simulation that accounting for traffic rules can reduce the need for inter-agent negotiation. Now, our intuitive hypothesis for this work is that many rules exist precisely to eliminate the need for coordination or negotiation in many situations. And we think this may benefit game theoretic approaches in various ways. For example, consider two agents walking in opposite directions in a hallway. There are two Nash equilibria in this situation. Agents can either pass each other to the left, or they can pass each other to the right. And so this can cause problems when agents make decisions online and commit to incompatible equilibria. And this results in a very familiar shuffle in a hallway where people are trying to end up bumping into each other. But in real traffic, we simply specify rules. Everybody should drive on the right-hand side of the road. Or like here in Auckland, we might say everybody should stay to the left. Still, besides this very simple example, there are some challenges to incorporate traffic rules and conventions. First off, they can be difficult to define mathematically, since they often constrain the desired order of events. For example, agent 1 should cross the road before agent 2, or an agent should stop at a traffic light until it turns green. these rules are not easily represented as a sum of stage costs as one might naturally do in a Markov decision process framework. The second reason is that rules depend on the trajectories of multiple agents, and so there can be ambiguity over who carries responsibility for breaking a rule. Finally, we may need to account for the fact that we don't always follow rules. Agents may randomly break them. Like when I arrived in Auckland, I think maybe some of you have done this as well, I ended up on the right-hand side of the road a couple of times. Now, for these reasons, we first propose to specify the rules as linear temporal logical constraints on the joint trajectories of all the agents. Linear temporal logic is a framework from the formal methods community. These allow us to build constraints from 3 parts: atomic propositions, functions of the system state that either evaluate to true or false, logical connectives like ands and ors, and temporal operators that allow us to specify the desired sequence or ordering of events. And secondly, we go back to our observation that good rules should essentially eliminate a need for strategic negotiation or coordination among agents. When we drive, the rules usually unambiguously tell us what to do, independent of the decisions of others. Therefore, we assume agents carry unilateral responsibility for satisfying their rule, independent of the decisions of others. This allows us to classify decisions as what we call prudent or imprudent actions, using robust reachability analysis. To appreciate the notion of the prudent and imprudent actions, our definitions lead to the following theorem. An agent satisfies its rules for all time under any opponent policy, if and only if the agent only takes prudent actions. Intuitively, imprudent actions may lead to rule breaking, and prudent actions do not. With these definitions in hand, in our framework, we embed the rules into a standard Markov game. To do so, we take the standard Markov game and fix the likelihood of agents taking imprudent actions as a chance constraint. In our novel formulation, novel knowledge of these chance constraints on an opponent's decision-making means that agents need to act cautiously. They need to take the likelihood of other agents taking imprudent actions into account to maximize their expected reward. In this work, we take the following approach to construct policies. First, we learn the likelihoods, PI, of opponents I taking imprudent actions, and we learn this from data. Then we apply the minimax Q learning algorithm to learn adversarial robust policies for the cautious Markov game. And why do we do this? I think in my eyes, adversarially robust policies are an ideal candidate to verify how much negotiation is needed in an interaction. If a policy that assumes that everybody conspires against you performs well, then there's probably little need to reason about an opponent's decision-making strategy and behavior in an interaction. Right. We illustrate the cautious Markov game framework with a simulation of a 4-way stop sign intersection with 2 agents. At such an intersection, the guiding convention is the first in, first out principle. Everyone needs to stop at the stop sign, and whoever arrives first should cross first. We simulate the scenario in CoRL. And just to demonstrate that we can get reasonable behavior with this framework is when I'll show a video where our ego agent in red arrives first, and it knows the opponent follows routes. And so therefore, it decides to cross the road first. I'm seeing that the video is a little jittery on Zoom, but I guess that's okay. I wanted to illustrate that to construct the rules in this example, we start defining the atomic propositions that we use to specify the rules using occupancy of the agents in the bounding boxes that are shown on the simulation here. And then we chain these atomic propositions together with the temporal connectives to specify things like first in, first out rule at an intersection. So we compare our approach along a few axes in this setting. We first off vary the likelihood P2 of the opponent taking imprudent actions. We specify a positive reward for the ego agent for reaching the goal state before the opponent on the other side of the intersection, and we have a penalty for collision. we compare against a pessimistic agent. Now, the pessimistic agent assumes that the opponent always takes imprudent actions if it's presented with the opportunity to do so. And as you'll see, the pessimistic agent is quite conservative. It basically lets the opponent cross the road first every time. Secondly, we compare against an optimistic agent. Now, this agent assumes that the opponent never takes imprudent actions. And so it can be very safe when its naive assumption is violated. When the opponent always takes imprudent actions and we assume that they never do, our agent causes a crash, which is indicated by the negative reward when in the P2 equals 1 call. Right. In contrast, our cautious agent, it estimates P2, the likelihood of taking imprudent actions. And we see that across all values of the imprudent action likelihood, our agent maximizes the expected reward. It is neither overly conservative nor naively unsafe, and it appropriately interpolates between the optimist and the pessimist based on the behavior of the agents around it. Finally, I wanted to illustrate the qualitative behavior of our approach on a T-junction with a priority rule. So here the opponent should yield for the ego agent. The ego agent is driving on a priority road, and the opponent should yield before it merges. Now, in the first setting, when the cautious ego agent estimates that the opponent is likely to take imprudent actions. So when P2 is high, the cautious agent slows down and lets the opponent cross out of turn. In the second case, when the cautious agent is confident that the opponent does not take imprudent actions, so that is when P2 is low, the ego agent confidently takes its priority and crosses the street first. So in conclusion, in this work, we developed a precise notion of what it means to break traffic rules in a stochastic game. We did some simulations that showed that incorporating rules into such a formulation can reduce the conservatism of robust min-max policies. And this showcases that traffic rules really exist to reduce the need for interagent negotiation in many situations, and that estimates of when opponents make imprudent decisions are an actionable signal to incorporate in an autonomous vehicle stack. Now, I think this work that we did is quite early stages, and I think there's a lot of exciting directions for future work, and also a lot of things that we can still improve. And so I think maybe it's good to defer the discussion of future work to the Q&A, and I think this is a great opportunity to get some feedback from me. So that's all I had. Thanks everyone, and happy to take any questions.
Great. Thank you so much, Rohan. Very interesting talk. I think now it's a good time for us to start our Q&A session. And I'm going to actually start by asking a question from Rohan, who just talked about his work on using rules for basically breaking down the need for negotiations. And just I have one question that I was wondering if you could clarify, and that is, you mentioned that you basically reason about these chance constraints, which is basically the probability of constraint violation by other agents. And I was wondering how you train your policy such that your policy is guaranteed to satisfy those constraints. In a sense, what type of algorithm do you use for policy training in your cautious Markov game?
Yeah, thank you. That's a very good question. I didn't really go into the technical details into this talk, but basically what we do is that we translate trajectories to constraints on the specific actions of agents. So at each state, we classify this, we separate this set of actions for each agent into a set of prudent and imprudent decisions. And then when you do policy optimization in a stochastic game with a finite state and action space, you usually optimize over the probability simplex of over the action set. And so if you say, well, the probability of someone taking an imprudent action is 10%, that just corresponds to a very simple linear constraint that you do use to like subset the probability simplex over actions that you specify your policy as. So it's just like you might use linear programming or something like that to do value iteration for a zero-sum Markov game. And all you need to do in our situation is add in those linear programs one single constraint on the actions to fix the policy to obey this chance constraint over actions. Does that make sense?
Yeah. Thanks for the clarification, because dealing with chance constraints is in general really hard. Satisfying chance constraints and training a policy is itself hard. So I was wondering how you manage to merge the two and train a policy which satisfies that chance constraint.
Yeah, that's definitely a very hard problem. And so because we just specified over the specific action set of an agent, it became quite easy to do so.
I see. Yeah, makes sense. Thanks for the clarification. If you have in-person audience that want to ask questions, feel free to go for the questions, or if you have audience from the Zoom, feel free to unmute yourself and ask questions. Otherwise, I have questions for the other speakers as well.
Does this microphone work? Can you guys hear us on Zoom?
Yes, we can.
Okay, great. Yeah, I had a question about the first talk. On the last slide, you said one of your conclusions was adding random noise might be benign. I wasn't sure how to interpret that. Like, what exactly did you mean by benign? Like, should I interpret that as maybe you, for the control policy, maybe you don't need to do this whole game thing and adding random noise might be good enough? Or is that like, if you train it with your game theoretic method, then in the real world, adding random noise will be okay?
Yeah, that's a good question. I should have clarified that. So what I mean by adding random noise might be benign for control is, let's say in the specific case of high-speed lane change maneuvers, you might want to add targeted adversarial noise, which is worse for your learn forecaster, and just random perturbations might not affect the output of your forecaster. That's what I mean. Like, so you don't know just adding random noise is helping you or not, but adversarially adding targeted noise is exactly affecting the points where it's worst. Does that?
Okay, I think that makes sense.
Thank you.
Okay, I have a question for Sarah actually about the work on game theory for collision avoidance and sort of air traffic management. And Sarah, if you are around, I see your name on Zoom. I was wondering if you could elaborate a little bit more on the algorithm that you used for solving your Markov potential game. You mentioned using Frank-Wolf algorithms. And I know that's a very commonly used algorithm for finding equilibria in static games. So I was wondering why you decided on using Frank-Wolf algorithm, and if you have any insight that you could share with us on that.
Yeah, so we used Frank-Wolf to solve for the Nash equilibrium. And here it's nice because the Frank-Wolf is for non-convex optimization problems, and we have this non-convex problem. So that's one reason why we chose it. The other is that so if we constrain, so the constraints on this problem are like the MDP dynamics. And so Frank-Wolf is really like you're keeping the constraints inside and you're iterating on the outside, changing the point that you're sampling the gradient at every time, and solving the linear, so in my case, a linear program on the inside. And so this linear program is basically an MDP, which you can solve with value iteration, linear, like any kind of thing that solves a typical MDP. So it has a nice interpretation that way in terms of like just being able to solve MDPs iteratively and then still getting to a Nash equilibrium.
That makes sense. Thanks, Sarah, for the clarification. That makes a lot of sense.
Thanks.
I have a question for Sarah as well.
Yes, go ahead, you.
Cool. So in your work, you showed basically equivalence that says if you want to get a Nash, is equivalent to solve a non-convex optimization problem. That's the main claim of the results, right? So my question would be, because we know we can never hope to get a global optimal solution for a non-convex optimization problem, when you get a local optimal solution for that non-convex optimization problem, does it correspond to an approximate Nash equilibrium, or what kind of quality can you say about the Nash equilibrium corresponds to the local optimal solution?
Yeah, right. So it's really a local Nash equilibrium, which I think just means that, you know, like for the near neighbors of my current strategy profile, this is my optimal, the best I can do within this kind of like neighborhood. So, but that's actually a really interesting point, because that's one thing we were wondering about, like, is this local Nash equilibrium any good? And so when we implemented it for this air traffic example, what we found is, for example, if you put in 2 flights, yeah, so what we found is, like, in the global case, we do get reduced collision risks, both in the number of possible collisions and the probability of the collision risk. So that's really nice. And when you just, let's say you run like just 2 flights and you give it the exact same waypoints and time, and then you give it to the algorithm and see what happens, it also generates a solution where the 2 flights are essentially delayed one after the other. So it so that they basically barely avoid each other, but still like they avoid each other, but still stick to the original flight plan and get to the destination on time. So at least in application, we can say the equilibrium points are pretty nice.
Okay, just a quick follow-up. When you say local Nash equilibrium, you mean each individual player cannot locally unilaterally change its policy and expect to improve the expected cost. Is that fair?
Yeah, exactly. Yeah.
Okay. Thank you.
Thanks.
Cool. All right. I think that's probably about all the time that we have for the Q&A session for this this first round of contributed talks. So thank you very much to all of our presenters and questions and so forth. So let's check. Dan, are you online? Yes, great. Okay, so I'd like to introduce our next invited speaker, Daniel Fried. So Dan's an assistant professor in Language Technologies Institute at School of Computer Science at CMU. Dan's research is in natural language processing, and he focuses on language grounding and interaction. So allowing people to communicate with computers to carry out useful real-world tasks. So Dan's excited about domains where computers can augment human abilities and kind of mediate that augmentation via language. I actually know Dan because we were PhD students together at Berkeley in the AI lab, and Dan was also a postdoc at Facebook AI Research in Seattle and UW. So thanks so much for joining us today, Dan, and the floor is yours.
Thanks. Can you all hear me okay and see my screen?
Yeah, looks great.
Awesome. Great. Yeah, thanks. Thanks for the intro. I'm super excited to be here. Like David said, so I come from an NLP background. So, game theory is a little bit new to me, but I'm excited about, trying to model language strategically and show how we can use kind of like a strategic perspective on language to try to improve the ability of NLP models to interact more successfully with people. So I'll be talking about 2 different settings, kind of just like a high-level overview. One setting is vision and language navigation, and the second is a challenging negotiation language game called Diplomacy, talking about some work that I did at Meta AI with their diplomacy team. So I'm interested in building systems that can help people do a broad range of tasks in the world, and this is going to involve using language in context. So context is sometimes the world, for example, to allow navigating around in a complex environment conditioned on guidance from a person. And to do this, we have to ground language. We have to learn what things and actions the language is referring to in the world. I'm also interested in how language allows contextual interaction with people. And a lot of times this will require reasoning about people's intents and the effects that language has. So for example, if you say my neck hurts to your smartwatch, it's not just a literal statement about your neck. It's also an indirect request for help, maybe. And the system should reason about the person to figure out that they're kind of implicitly asking in this way. So I'm interested in pragmatics, which is the field of linguistics that gives us the tools to tie language to intents and goals like this. And this talk is about both grounding and pragmatics and kind of a strategic perspective on both to help people do things with language and computers. So here's an example of both grounding and pragmatics. Grounding is kind of about the literal meaning of language in the world. So if you're a self-driving car sitting on the street, and someone says to you, stop at the second car, you should be able to figure out that they probably mean this car here. Pragmatics goes beyond this. It's about relating language to kind of intents and interpretations and the non-literal meaning of language. So if you get an ambiguous instruction like stop at the car, there's a bunch of cars here, you maybe have to think a little bit to figure out which one the person meant. But most people would choose this car here. It's some mix of a lot of things. There's salience, there's conventionalization, but part of it can be seen, and we'll see how in a minute, by reasoning about alternatives. That if the person had meant a different car, like the second one, they maybe would have been more specific. So to operationalize this view, I'll talk about a couple projects that take a game theoretic view on language production. So they see language generation and interpretation as games between agents. So I'll show these using really simple game trees. For generation, the speaker has a referent, something in the world that they need to convey to the listener. So the speaker is going to choose between things they could say, which are actions that they're taking. So I'll show two here, stop at the car or stop at the second car. They're going to hand that off to the listener, who's then going to choose how to respond. And they'll both get utility if the listener chooses the correct referent, the correct thing that the speaker could have been describing. So if the listener is kind of a simple one that just takes everything literally and ways to say stop at the car, we don't know which car they'll choose. Whereas if the speaker is more specific, the listener has a higher chance of getting it right. So that's the sort of thing that a speaker that reasons about the listener might choose to say. So we can also use reasoning for the inverse task. And if we get an ambiguous instruction like stop at the car, the listener can reason about the speaker going through the same reason and figure, they had some goal in mind in the world and they were choosing between things to say. Since they didn't choose a more specific thing, we can figure they probably meant this car here. And that could be the output of a reasoning listener. So in a couple projects, we and work by other groups that I can point to if people are interested, show that this kind of joint reasoning between speakers and listeners helps improve performance on a range of language grounding tasks. So we'll build speaker models that generate language and listener models that interpret it, and we'll train these models on data from people so that they roughly model human behavior. And we'll show that we can use each type of model in simulation to help improve the other type of model so that speakers help listeners and listeners help speakers. So sort of planning against a simulated person helps the models do better when collaborating with actual people. So the first set of projects that I'll talk about are on grounded instructions. And the setting that I'll use to kind of present the approaches is vision and language navigation. So it involves generating and following instructions through scans of real world buildings. So people were shown a path like this one and asked to produce an instruction, turn left and take a right at the table. The table's coming up here. And then take a left at the painting. And then take your first right. Wait next to the exercise equipment. So the data set here, it's called Room to Room. It's built on the Matterport 3D data set, which is basically an indoor street view, sort of scans of very nice homes for real estate purposes. There's a graph of connected points within these indoor scenes. Each point has an associated panoramic image with it. And the task is for a virtual agent to navigate around in this environment, conditioning on the panoramic images that it sees along the way. So the interpretation task is what I just described. We get an instruction like go forward between the kitchen counters and so on. And we output a route, which is a sequence of discrete actions which move us around inside this navigation graph. And at each point in time, we're getting visual input too. So we'll move forward between these kitchen counters, then predict turn right, which updates our view, and predict move forward. And at any point in time, you can predict to stop. And if you get to the end location that the person who wrote this instruction was trying to describe, then it's a success. So that's the interpretation task. I'm also going to talk about a generation task, where we have in a route, the sequence of images and actions that we take through the environment, and we want to produce an instruction that a person could carry out correctly to get to this destination that we had in mind, sort of a visually grounded version of navigation directions. So 2 tasks, interpretation and generation. And I'll talk very briefly about the building blocks that we use for these tasks, which we'll then employ in a sort of reasoning procedure inspired by the game tree sketch that I had at the beginning. But the building blocks are basically just sequence to sequence neural models. They're probabilistic. And the first model is the listener model, which takes in an instruction, produces a distribution over sequences of actions, which constitute routes through the environments. The speaker model performs the inverse task, so produce a distribution over instructions that describe a sequence of actions in visual context. And it's important that we use probabilistic models because we want to represent uncertainty in how someone might carry out an instruction. And this will let us reason about alternative routes and alternative instructions. I won't talk much at all about the details of these models unless people are interested, partly because the procedure we use aims to be model agnostic, but also partly because the base models we use here are old. We did the work several years ago, but they're sequence to sequence models that encode the instruction and then produce actions one at a time, conditioning on an attended representation of the instruction and the visual context summarized with a pre-trained convnet. That's the base listener model. The base speaker model is basically symmetric, takes a sequence of actions and visual inputs, encodes them, and then outputs instructions one word at a time. But if we have these 2 base model architectures, we can train them using imitation learning on data from people. So the data sets consist of routes through these environments. For example, the room-to-room vision and language navigation environment that all the examples have been so far, the route's shown to a person and they write an instruction that someone else should be able to carry out. And the data sets we use have between 2,000 and 15,000 pairs of routes and instructions. We'll use these to train both our speaker models and our listener models, just to maximize probability of instructions given routes or routes given in instructions. And we train the models independently. But although we'll use the same data to train both listener and speaker models, we'll find that even though they're trained to imitate people's behavior, they still make some mistakes that sort of game theoretic pragmatic reasoning procedure that combines the 2 models can fix. So to sketch out how this procedure works, I'll talk about what we do for generating instructions pragmatically by modeling how they might be interpreted. We have a route that we want to produce an instruction for, and we're going to consider different possible ways that we could describe it. And to do that, we'll rely on our speaker model to produce candidates conditioned on this route. There's a bunch of ways you can get candidates, for example, by sampling from your model or doing beam search. We use between 10 and 40 candidates. I'm just showing 2 here to make things simpler. But these are all, pretty good instructions generally. They're all generally true and consistent, but some are more informative than others. Like this one on the left doesn't specify where to stop, whereas the one on the right correctly specifies stop once you're on the rug. But we'll we'll use our listener model that we've trained on data from people to roughly simulate what's the chance that a person could carry out this instruction in the environment. We'll go through each instruction in turn and we'll plug it in to our listener model as input with the route we want to describe as output and see what's the probability that it would make our model of the listener do the right thing. So this first one that doesn't specify where to stop has a somewhat low probability, 0.4, of making our model of the listener do the right thing. While this other one that's more specific about where to stop on the rug has a higher probability, 0.8. And so that's the instruction after we go through all of them that we choose, the one that has highest probability. And that's the one that we output from this pragmatic generation procedure. So we'll evaluate instructions by seeing how easy they are for people to follow correctly. So we'll put a person in the simulator, we'll give them an instruction, allow them to act and see if they get it right. And I'll first show how good are human-written instructions from this data set, the data set that we use to train. It's actually kind of tricky. Across the domains that we look at, these human instruction followers, looking at human written instructions, mechanical Turkers in both cases, their accuracies vary from 66 to 83%. So it's a combination of a hard task and noisy data. And we train our base speaker model, a state-of-the-art sequence-to-sequence model, on this data, but it's actually even harder for the model to generate good instructions. And that's because language generation in contextual settings is hard. But if we add in this pragmatic procedure, which uses our listener model trained on exactly the same data with the symmetric architecture, we see really big improvements so that the instructions produced by the systems are comparable to, or in some cases, even better than those produced by people. And I think this improvement's interesting because the pragmatic speaker doesn't extra data or special architecture. It just adds in this reasoning procedure with the listener model that's symmetric to the base speaker model. So we had this pretty simple procedure that simulates how language might be interpreted by people or our models of people. And we found that it makes generated language more informative in context, so that reasoning strengthened our models and allowed them to sometimes outperform the data that they were trained on. And if folks are interested, I can talk more about the intuitions for outperforming the training data if we have time. Okay, so that's pragmatically generating language. We can also invert this process to do the interpretation task, instruction following pragmatically. And here we're having a listener that reasons about what might have made a speaker say what they did rather than something else. So to do this, we'll use the same base speaker and listener models that we used before, and essentially the same generate and re-rank procedure that we used before. But the way that it works is we have an instruction that we want to follow, and we want to consider different possible routes that a speaker might have been considering that made them produce this instruction that we're trying to carry out. So we have this observed instruction, and it contrasts with other possible instructions that the speaker could have produced. And we're going to evaluate different possible routes. So we'll propose routes through the environment by using our listener to propose them. So again, you can produce these by sampling from your model or doing beam search. This one's, I think, this version is a lot less realistic to apply with an actual robot because we require, being able to start from your initial location and then produce multiple trajectories and reset through the environment. But you can consider different possible search procedures in these simulators to do it. We get different possible routes, and then we go through each of the routes in turn, plug them into the speaker model, and see what's the probability that our speaker assigns to this observed route. So this first route that stops on the rug has a lower probability of producing this underspecified instruction, 0.1, versus the more specific instruction, 0.3, that specifies stop on the rug. But we associate that probability with this route and then move on to the next one, which has a higher probability, 0.2, of the instruction we saw, because other alternative, more specific instructions are just inconsistent with it. But after we go through all of the routes, we choose the route that has the highest probability under our speaker as the output of our reasoning procedure.
Does this work?
Yeah.
Go back one slide.
Sure.
Yeah, so here, the input to the listener and the high probability output from the speaker are identical as far as I can tell, right? So is this, to me, that seems kind of unlikely that it identifies the exact same wording. Is this coming from a discrete set of possible instructions, or is that just because these are trained kind of jointly that the correlation is so high?
Yeah, it's a great question. So there could potentially be other instructions which have argmax probability under our speaker model. We don't require the speaker model. We don't generate freely from the speaker model and require it to produce the observed instruction. Since the models produce tokens autoregressively, you can plug in a single instruction and just evaluate what's the probability of it. In the same way that you would use a language model to evaluate the probability of some piece of text that you see. So kind of the intuition here is that there's, this model has the capability to generate anything with some probability. And so we're implicitly contrasting those other alternatives against this observed one. And the way I presented this is a little confusing because I'm showing just 2 here, but really there's, an infinite number and they all have some probability, but these are just maybe 2 of the more likely ones.
Gotcha. Okay, thank you.
Sure. Yeah, it's a great question. So let's take a look at the results of this procedure. So numbers are now higher on this data set. There are other more challenging vision and language navigation data sets, but at the time we did this work, so human performance at following instructions around 85%. At the time we did this work, the state-of-the-art system got around 25% accuracy. We made some improvements to their base follower model, base listener model that got us to 36. But when we add in this reasoning procedure that uses the speaker model that's symmetric and trained on the same data, we get an even larger improvement. And just to give you a quick sense of what this looks like, here's an example of a bad output from our base listener where walk past the hall table, it's kind of ambiguous, chooses to go this direction, walk into the bedroom. These houses are all kind of nice, so there's actually 3 bedrooms here. The model chooses to go into this one, make a left at the table clock. There's no table clock here, but the model kind of does the best that it can, waiting at the bathroom door threshold. So our pragmatic procedure considers that route, but also considers and chooses this other route that goes this other direction past the hall table, walks into this other bedroom, makes a left at, you can see the table clock there, and then waits at the bathroom door threshold correctly. So I think the quick takeaway for this is that simulating why a speaker said what they did can help you to resolve ambiguity in their instructions. And that ambiguity can partly come just through grounding language into vision being a hard problem to solve with limited data. Okay, so this is going to be a little bit of a bird's eye view of this project, but I want to talk, because I think the project's super cool, about showing how reasoning can help in dialogue where speakers and listeners interact. And I'll be describing work with the Fair Diplomacy team where I was a postdoc last year. So we made a strategy and dialogue agent called Cicero, which played the negotiation game diplomacy at a human level in games with people. So this was a big project. I contributed a small part to it, but I'm excited to tell you about portions of it and how they relate to strategic use of language. And I encourage you to check out the paper if you're interested, particularly for the game theoretic planning parts. So what's diplomacy? It's a strategy board game from the 50s. It was actually John F. Kennedy's favorite game, where you play one of 7 different European powers that are all kind of vying for territory in World War I. And the game has like 2 parts to each turn. So first, there's private natural language negotiation. Players have private conversations with each other. They form alliances. They negotiate how they'll work together. They coordinate what actions they're going to take. And then at the end of the turn, every player secretly enters their moves, which is moving sort of their pieces from one country to another. And these moves are revealed simultaneously. So players may have made private agreements with each other as they've been negotiating, but those agreements are non-binding. So they need to build trust and they have to account for the fact that other players might be lying or they might not follow through on their agreements. And the game is totally deterministic. There's no luck like there is in Risk. So it's all about these negotiations and the actions you take. And to win, you need to be able to persuade and cooperate with others. There's been a lot of work on diplomacy, but this is the first work to operate in the unrestricted language version. So what are some challenges for language in this game? Well, one is to hold human-like dialogue, send hundreds of messages to multiple parties. Each party can't see the other messages. The messages need to be grounded. They need to be consistent with the game state and the past dialogue that you've had. And obviously, a second challenge is to try to win the game or do as well as you can, which is going to require strategic negotiation. For us, that involved interfacing with an external reasoning game planning system and using language intentionally to carry out your goals. So I think it's interesting to point out that there's a tension between these, which leads to some approaches like, self-play RL not being applicable in this language version. You want to choose language that's effective in achieving your goals, but you also want your language to be understandable and cooperative with other people. So you need to be human-like in some ways. But like in the first part of the talk, we're going to see how far we can get with just imitation learning. So we're going to take a large data set of human-human dialogues where people play diplomacy on this online website, webdiplomacy.net, 50,000 human games. And we're going to fine-tune language models to generate language that looks a lot like this language from people. And the language is actually pretty human-like. So here's one of my favorite examples from the project where we were playing the system against real people. The people at the time didn't know it was a system. We told them after the experiment was over. But England is a person here, and France is our system, the Cicero agent. So the system actually went down in this game, and there was a while where it didn't send messages to its partner, but we conditioned the system on the amount of time since the last message was sent. And so it said, I was on the phone with my girlfriend because, there was some similar messages in the training data that came after a long gap. So the language looks pretty human-like, but there's definitely limits to imitation learning here where, oh, sorry, was there a question?
No, we're just laughing.
Okay. So there's definitely limits to imitation learning here because there was a wide range of players in our data set. Some are very good, some are less good. And a model trained on the combination of all of these is going to effectively model the average player, at least in expectation, right? If you kind of take everything from this distribution that you're modeling. And it's important for our messages to describe it's important for the messages to be good, just like good language, but also for the messages to describe good actions, because you build up trust with other people in this game by, proposing good actions that are mutually beneficial to you and the other person in this semi-cooperative game. And more than this, we want to, if we can, be better at other people, both at strategy and coordination. And to outperform the best people, we can't just imitate all people. So as you might anticipate, the way that we try to address this is by decoupling the actions that we choose and the language that we generate. Don't worry about the details of the system diagram. It's mostly just to convey that there were a lot of components to this in this factored approach that we took. I refer you to the paper for details, but at a high level, we have a language-informed planner that chooses mutually beneficial actions for the agent and each partner in the game, conditioning on the language and the game state. There's other talks by other people on the team about the multi-agent RL and planning that they did for this. But the part that I want to focus on is using the plans generated by the system to inform the language. So we both want to condition the agent language on plans chosen for the agent, actions chosen for the agent, but we also want to reason about the effects that the agent's language has on other players' plans, which is sort of, the same approach that we took in this pragmatic generation in the first part. So to sketch out how we do this, decoupling planning actions and generating language, we take our training corpus of dialogues and context, and we assume that underlying each message that's sent in the game are some joint actions that each player intends to play at the point where that message is generated. So these, you can think of these as like maybe latent variables in our training data, but I've kind of shown the important parts of the actions for each message. So like this message from England, do you want Netherlands to support Belgium? That's underlined by a joint action for France and England. Don't worry about what France is intending to do, but England is going to be supporting Belgium from the Netherlands. Similarly, for this next message from France, no, Belgium is moving to Holland. That's represented in the joint action. England agrees, and so now we have good information about what both of those actions should be. So if we assume that these latents are here at each point in the dialogue, sort of the intended actions of both players in this dyad, communicative dyad, we can train a model to annotate our training data with these, where we'll have an intent predictor model that predicts these joint actions for every message. And there's details about that also in the paper. But once we have those, we can train a conditional dialogue model that takes in these joint actions and then produces the messages. So we have a pipeline system now. We can choose the actions in some way. And to do this, we'll use a pretty sophisticated language condition planner that other folks worked on. But it'll propose mutually beneficial and also human-like actions for the agent to take. And then we can hand those off to a dialogue model to produce language that conveys them or asks questions about them or tries to convince the other player to take these actions. Just to give you an intuition for how this works, so in one situation, there's two plausible things that the agent Cicero might want to propose playing. So one, Cicero is England, the human partner we're talking to is France. So in one situation, France is going to help us, it's called support us to move into Belgium. And another one, Cicero is going to support France to move into Belgium, so kind of the opposite. And if we plug in these intents to our dialogue model, it does do the right thing. So for the first one, the agent asks if the partner will do the support, whereas in the other one, the agent says it offers support to its partner. So we have this decoupled dialogue system, and we can do different things with it, both in how we choose the actions and how we choose the language. And one that I want to focus on that I think is really cool about this game, because this game kind of has a reputation as being one that's, competitive, but at a high level, players who play it actually are pretty honest almost all the time in the dealings that they have. And the reasons for this are that it's hard to account for the impact of lying. It just kind of destabilizes the game. Here's an example of this from a human-human game where at some point in time, Turkey lied to Russia, Russia finds out, and their relationship is just over. Russia's out for revenge over the rest of the game. So conversations after deceit are difficult. We also didn't want to mess with strategically trying to model lying in the game. And strong players use lying very sparingly, if at all. So we made the agent honestly describe the actions that it intended to take as much as we could. So the way that we did this was when we have, it looks a lot like the pragmatic thing that I sketched in the beginning of the talk. So we have plans, joint actions that we want to describe in language. We're going to propose different candidate messages from our dialogue model, the conditions on them to describe them. And we're going to evaluate each message for a couple different factors. So the first factor is kind of evaluating, is this an honest message? Does it correspond to the actions that the agent intends to play at the end of the turn? So we'll use our intent predictor for this. We'll again just kind of round trip the probability of getting this intended action back and see, does the message not make that probability go down? That's kind of a proxy for what impression it would give our partner. But we also want to be strategic in the information that we give. So it wouldn't be good to say everything that the agent plans to do, and it might also overwhelm the partner. So for example, we might not want to say that we're allied with Russia, that the agent is allied with Russia. So we'll use a planner, we'll use the same planning procedure, which conditions on the language, compute likely policies for ourselves and for the partner, and see, does this message make our expected value under these policies higher or lower? So this kind of accounts for using language strategically. And finally, we'll just filter messages that are inconsistent with the game's trained models. So that's basically all I want to say about the approach, all that we have time to cover. But to give you a quick example of dialogue that shows how this kind of factoring and strategy helps, here's an example where the agent is playing as France and its human partner is Turkey. And France, our agent has proposed this joint action that needs it to kind of occupy this country, or take this country, this piece of territory. But Turkey pushes back and says, no, you got to let me have it. France says, no, I need it. You have Serbia and Rome to take. And Turkey, the human, says this is impossible, but France, the agent, actually suggests some moves that Turkey could take to do it. And Turkey gets convinced, and then the two will go on to work together in the game. So this kind of shows how you can use this, this very strong planner and then use that to control your language and also persuasively convey the actions that you want the other player to take to the player. So we entered this agent anonymously in an online diplomacy league over the summer. It ended up playing around 40 games, and to our knowledge, it was never identified as an AI, besides one mention of suspicion in a post-game Discord chat, although it had conversations for more than 70 hours with 82 unique players. We did tell all players after the games were over that it was an agent, and some of the reactions from people were interesting. They were pretty surprised. But it placed in the top 10% of players and did very well and won a weekend mini tournament. So the credit to the team for all of this. But my takeaways from this were that it's helpful to decouple strategic planning and language generation, which also kind of parallels the findings that we had in the grounding setting, ways to potentially outperform imitation learning while still cooperating with people. So it's helpful for strategy to inform language and to try language strategically. And to try to sum everything up, I think it's productive as much as we can to try to view language as a cooperative reasoning process between agents. And in the work that we've done, we found that we can improve language systems that simulate how people act by using models of people to plan and models of people's language use to plan, and then collaborate better with real people. So this work's been thanks to a ton of really amazing collaborators. These are folks who I worked with on the grounding projects, and the Fair Diplomacy team, which has people across NLP, RL, game theory, and diplomacy experts too. So yeah, thanks to all of them, and thanks to all of you for listening.
Hey, thanks so much, Dan. Really, really cool talk. So I'd love to open it up for maybe, let's say, one question, and I think then we'll have to move to the next next session.
Okay. Oh, you got one? Okay.
Sorry, thanks for a really great talk. Just out of curiosity, what are the next steps, the future things that you're most excited about in this area?
Yeah, I think one that is maybe most interesting and accessible in the short term is like adaptation to individual people that you're interacting with. So like people use language in different ways, and part of that's just a property of people. Like you may just be familiar with different terms or something like that. But I think a big way that language adaptation could be useful is kind of the common ground that you build up with a person as you get to know them, like build up a working relationship with someone where it's easy for them to understand you because you've come to be on the same page. And I think there's room to use the kinds of explicit models of people that we've developed and adapt those to individual people too. Everything's been a population level model so far, but I think through meta learning and just kind of contextual adaptation, hopefully we could try to better model individual people and adapt and better collaborate with them. And I'm trying to apply these in other domains too. I'm super excited about coding as a domain, given that base models for generating code and language are really successful now. So thinking about ways that we could also kind of view code generation and code interpretation as kind of collaborative strategic actions and reason about why people are doing what they're doing when they're interacting with these systems.
I know we're about over, but I did just have one quick question as well. So in the first part of the work, I really liked that. And one of the questions I had is, it seems like, you have this kind of like a bi-level game between the listener and the speaker. And when you're reasoning about the response of the other player, it seems like you're kind of considering like a distribution of what they may do given your instruction or vice versa. I wonder if you ever considered trying to treat it more as an adversarial game. So you're optimizing for kind of robust worst case performance. And if that had any, differences in the outcomes, if you did explore this at all. If not, then disregard.
No, yeah, we didn't explore that. I think that's super interesting. We're kind of assuming in the first part, we're assuming that the communication's cooperative. You could definitely look at viewing your communicative partner as an adversary to try to make things more robust. The closest thing I can think of is work from Percy Leong's group and like Robin Jha, who do this in the language space to try to make their models more like distributionally robust. There's also been interesting work on like trying to like apply similar reasoning frameworks that we've used to like non-cooperative communication settings, like cross-examination for a trial or something like that. And kind of the thing that people do there is you assume that the communication is cooperative, even if the underlying objectives are not. So like you want to get your point across and you're choosing things to say that get your point across, even if, the outcomes you're trying to achieve are misaligned. The diplomacy setting's kind of one instance of that, I think.
Sure. Yeah, it's interesting. I feel like maybe, if you consider, okay, there is a chance that this thing I'm saying could ambiguously be interpreted, in a really bad way. And so if you're kind of optimizing for that, as opposed to the average response or something, it'd be interesting to see how that plays out. Yeah, anyway, it's really, really, really cool work. And thanks so much for a great talk. Wish you were here to chat more about it over lunch.
Me too. Thanks a lot for having me. Hope you all enjoy the conference.
All righty. Let's give another round of applause for Daniel Fried. All right, so we're going to be transitioning here into another round of our contributed talks. So we got 3 great papers that are going to be presented in the session. 10-minute talk each, followed by a joint Q&A, similar to the first session. So up first, we have a paper titled Robust for, oh, sorry, that's the old one. We have a paper titled Scalable Multi-Agent Reinforcement Learning Through Intelligent Information Aggregation, presented by Siddharth Nayak. Okay, so there is no issue. I think you just share from the feed loop. That's possible. No, it's. The alternative management. Okay. Let me restart your browser. Yeah. Great.
Hello, everyone. I'm Siddharth, first year PhD student at MIT, and I'll be presenting my work on scaling multi-agent RL through intelligent information aggregation. And this is a work that I did at MIT and my collaborators at Stanford as well. So there's been a lot of a bunch of applications like drone delivery, search and rescue missions that require they operate in multi-agent systems, which also have a lot of dynamic obstacles in the environment, and taking into consideration all the information about all these entities in the environment is kind of important to take good decisions to control them for the task specific objective. So if you look at a navigation environment, there are a bunch of agents which are being controlled. There are a bunch of obstacles. There are also a group specific goals which these agents are getting to. like key features that we expect from multi-agent RL algorithms is like we need decentralized execution so that it can be used in a scalable fashion. We need scalability, which is also like more important when we want to like scale these systems like larger systems, like have more agents in the environment, have more obstacles in the environment, and so on. And also we need to make sure that these algorithms are sample efficient to train, so that we don't need to like train it on a bunch of like a lot of data and like train. So these are the key features that we generally expect from multi-agent RL algorithms in these particular scenarios. So I'll talk about the background and motivation and like let you guys know about like what kind of things people have tried out in prior works, and then just motivate, give an example. So prior work has basically looked into like taking into the state observations for each agent, where each observation for agent has a position, velocity, and goal associated with it. And all these other entities in the environment also have their own specific position, velocity, goal associated. So if you look at a standard multi-agent RL algorithm, it concatenates the information about all the other entities in the environment, and that goes as input to the actor network. So this input size is proportional to the number of agents in the environment. So if you're looking at a centralized training, decentralized execution paradigm for multi-agent RL algorithms, you have a critic network which takes in information from all the actors. So each actor gives its state to the critic network, and you have all of them concatenated, and that is fed into the critic network. So this is proportional to n square, which means that you cannot really scale them pretty well. And whatever setting you train it on, you have to test it on that particular setting, because the network size is fixed, and it depends on that. So prior work has basically looked into like padding them with zeros by having a max cap set, or like using LSTMs where each of those XIs are basically the time features associated in the LSTM part. What we try to look into is I talk about a motivating experiment. So we vary the information that is included in the observations for actor. We tried to 3 different information modes. One is local information mode, where it just gets its own position, velocity, goal. Then we have the global information mode, where we concatenate everything. And then we have a neighboring information mode, where we just concatenate the position, velocity, and goal of like neighboring 10 agents or like 5 agents and so on. And here are the results of the training standard MARL algorithm. We show that having global information and having local and neighborhood information, there's a big gap in like there's a big difference in like the rewards that it accumulates over an episode, which means that the amount of information that is being given as input to the networks is kind of important for these MARL algorithms. Also, in practice, we generally do not have access to global information, because you do not really have someone telling you. You'd have to set up a big communication hardware to like communicate all these information across these multiple entities. So what we tried, so this is where our algorithm comes into the picture, where we use less information and we name our algorithm informal. So our informal method is split into 4 different modules. The first one is the environment itself. So if you look at this multi-agent navigation environment, you have a bunch of entities in the environment. We create a graph out of it where each node is an entity, and these nodes are connected by edges depending on like how far they are. Each node has a feature associated with it, which is the OIs and XIJs. Which basically contains relative positions, velocities, and goals. Then we have the information aggregation module, which basically aggregates information from its neighbors using the standard graph neural network message passing networks. So in this case, we have the agent to agent edge is bidirectional, which is kind of similar to communication edge. And we have an agent to non-agent edge, which are depicted with red arrows as unidirectional, which are kind of like sensing edges. And it kind of makes sense because these obstacles cannot really communicate anything with these other entities. So we use a transformer to like model is GNN, where these weight, like each agent can associate attention weights to its neighbors according to like how important its decisions are based upon how it behaves. Then we have the graph information aggregation module. So this is just to make sure that the training is also scalable. What it does is basically takes in the aggregated information from all the agents, averages it out, and then you have the active network. So the output of the information aggregation module goes into the active network. The output of graph information aggregation goes into the centralized critic network. The good thing about this is that this active critic module can be any standard MARL algorithm. So it's just a plug and play kind of feature. We use this whole thing for training, and we just use the information aggregation module and actor module for execution. So that's the good part about it, where we don't really need to have access to the critic while we're executing stuff. So for sample complexity, we perform experiments with a bunch of standard MARL algorithms and a bunch of other baselines which also use graphs. And we show that our method is consistently has better performance whilst using lesser information in its states. Similarly, we have more baselines. If you want, we compare against more baselines in the paper, so you can refer to the paper itself. For scalability, we test on like 10 agents and test it on like a scenario where it's different than it was trained on, and we show that it performs consistently well across these methods, these scenarios. We couldn't perform these tests with other baselines because they weren't transferable because of the thing that I talked about earlier, where the network size is fixed. And if you look at this previous graph, the graph-based methods didn't really learn anything, so we couldn't really get any performance out of it. So the thing that we measure over here are rewards, number of collisions, success rates. So a major flaw of this particular work is that the number of collisions is not exactly zero, and which we think is we will be addressing that in the future work. Another future work that I'm pretty much excited about right now is the satellite environment, where we try the same information, the navigation environment. Instead of having the navigation environment, we have a satellite environment where the dynamics are totally different. They have they follow orbital dynamics, and the equation that it follows is basically nonlinear, and it's way more complex. I'd be happy to take any questions about this environment if any of you are interested in. So yeah, the conclusions are basically we introduce a graph-based algorithm for scaling to like multiple scenarios. We just use neighborhood information instead of global information, which was used by previous methods, and we get a similar sample complexity and performance. Future work is adding 6 safety constraints for guaranteeing, making sure that there are no collisions in these environments. Thanks a lot. If you have any questions, I'll be here, or I can leave offline as well.
All righty, thank you so much. And yeah, we'll be taking questions in the Q&A session after the third talk of this session. So with that, we will now welcome Dianbo Liu, who will be giving a talk about the contributed paper, Stateful Active Facilitator, Coordination, and Environmental Heterogeneity in Cooperative Multi-Agent RL.
Can you hear me, and can you see my slides?
Yep, we can hear you and see your slides.
Great. Thank you very much. Thanks everyone for coming to the talk. So this is a paper we work on for multi-agent reinforcement learning setting, and specifically for cooperative multi-agent learning problems. So we all know in many scenarios, cooperative games are very difficult. And in this study, we want to disentangle the difficulties. And we specifically focus on 2 things: coordination levels and heterogeneity levels. For coordination levels, we mean the minimum number of agents required to perform a certain task and to be rewarded. For example, 2 men carrying a sofa. And for heterogeneity levels, we mean we specifically focus on environmental heterogeneity levels, which means a different area, locational area in the environment, the transition will be different, the state transition. function will be different. Okay, in order to quantify the performance of the agents at different coordination levels and heterogeneity levels, we made our own environments, which we call Haeckel grid. And we made a total of 3 different multi-agent Haeckel grid environment. And they allow us to control or manipulate different parameters of the environment, including coordination levels and heterogeneity levels. Also, other things like the number of agents, number of rewards, and the number of walls in the environment as well. Okay, this is the first one. We call the team together. The agent needs to, which are blue or green in color, they need to step into the reward, which is the red color square, simultaneously, and the number of agents that need to take their net action simultaneously is defined as coordination level. And this is the second environment, which if an agent wants to take a treasure to get a reward, certain number of agents needs to be around within certain distance. So that number of agents around is defined as coordination level. And this is the third environment. It's very similar to previous one, except the agent who is picking up the treasure needs to carry a key, adding key in the environment. Okay, and in all of the 3 environments, heterogeneity is defined as different number of different transition functions in the environment. And in our implementation, we vertically divide the whole environment into vertical slices. And in different slices, the transition function will be different. So that is heterogeneity levels. And now I have shown you the environment we use to study heterogeneity and coordination levels. Now, then we propose an algorithm which we wish it can perform well in environment with high heterogeneity and high coordination levels. So this algorithm have 2 components. Number 1 is a shared knowledge source, which is a little bit similar to the method described in the previous talk, but in here it's slightly different. So all the agents cooperatively write into the same knowledge source via attention mechanism, and they all read from it as well, also via attention mechanism. So which means all the agents communicate with each other through this shared knowledge source. And this only happened during training. During execution, this knowledge source is gone. You only this agent do not send message to each other anymore. Okay, that's the first component, the knowledge source. The second component is a shared pool of policies. So, for example, we have 5 policies in total. There might be only 3 agents, and every step when choosing the action, the agent will do a one-hot choice of one of the 5 policy and use that policy to choose the action. So that is a pool of policy. And after training, the pool of policy will still be available to all agents during execution time. So the whole thing is centralized training and a decentralized execution scheme. So that is our overall picture of our method, which we call SAFE. Okay, in the first component, which is the shared knowledge source, and during writing, the agent will use a MLP to generate its own message and write into a limited number of slots in the shared knowledge source. So the number of slots is very small. So there are in most of our studies we have like 5, 10, 15 agents. So there is a bottleneck effects onto the image and the messages right into the shared knowledge source. So the whole communication among different agents is bottlenecked, and it is soft competition. The writing into the knowledge and the knowledge source and reading from it are all soft attention. Okay, then let's move to the second. The second component, which is the pool of policy. So we have a pool of policy, say 5 of them. They don't share parameters. they have independent parameters, and they are at each time step different agent do one hot choice of those of one from the 5 policies using Gumball softmax, and which is one hot kind of a variation of softmax should allow you to do one hot choice during execution time, and only that chosen policy will be used for action picking for that specific agent. And in every time step, different agent can use different policy, and a different time step, agent can choose different policy. It's a dynamic process. We are using this because we think on a different situation, the agent may choose to do different strategy to pick its actions, which is common in cooperative multi-agent games. Okay, it's Gumball softmax based attention for one hot choice. Okay, so those are the results. We compare our method with MAPPO, which is multi-agent PPO, and IPPO method. Actually, we also compare our method with Qplex. I didn't show the I didn't put the result into this figure. The reason being that it just generated for the rebuttal on iClear. And in the implementation, our safe method on this picture use the MAPPO backbone, which means accept how the agent communicate and the policy pool. Everything else we use the hyperparameters. We use the architecture of MAPPO. Okay, and we compare with MAPPO itself and IPPO. IPPO means independent PPO, and we compare. Firstly, we compare the performance of different methods at different level of coordinations in all 3 different environments. And you can see in general, our method outperform or match the performance of MAPPO and outperform IPPO. This is in different level of coordination, while heterogeneity level was fixed and 1. And then we look at the heterogeneity level. We look at the performance of different heterogeneity level while fixed coordination levels at 1. And you can see in general, our method outperform both MAPPO and IPPO method. And you can see as the heterogeneity level increase, especially in the 3rd environment, the other 2 method performance dropped dramatically, while our method dropped but less dramatically. Okay, similar trend was seen in compare with Qplex and also our method, safe method using Qplex backbone. Okay, so that is the presentation, and I'm looking forward to feedback to the method and the environment. Thank you very much for listening.
Great, thank you so much. So stick around for the Q&A.
Yep.
If that's right. All right, so our final talk of this group here will be by Danny Hawawi, talking about Dominion, a new frontier for AI research. Danny, are you with us? Danny, do we have you in the Zoom? All righty then. Looks like we don't have Danny with us. So we will, I guess, move into the Q&A session direct. And if Danny happens to join, we might be able to slot him in later then. So on that note, we will open the floor up to questions right now on our first 2 contributed talks. You want to start us off?
Sure. Yeah, I guess I can start us off with a question for the talk we just saw from Danville. So I was wondering if you could give some more details about maybe some of the failure modes. For example, I remember one of the figures you were just showing with coordination levels as the number of agents required to kind of cooperate was increasing. There's quite a steep kind of fall off in the effectiveness of any of the methods, right? So when two agents were required to coordinate, none of the methods were doing it.
So
I guess the question, sorry, is just did you notice any kind of common failure modes among all the methods, or did you see that there were certain things that your technique was able to kind of fix, but other things that it wasn't?
Okay, I see. If that's specific about coordination levels, so almost all methods fail and level above 2. So if you give a level coordination level 3, say 3 agents have to pick up something simultaneously to get a reward. That's very, very difficult. Almost all methods, including ours, failed. And coordination level 2, you can compare with level 1. You can see a dramatic drop in the return, episodic return, and our method can show us slightly less decrease in the performance. So that's the situation. And if you specifically want something our method can do, other method cannot do, I would say the performance was very obvious. The difference very obvious in the key for treasure environment and high heterogeneity levels, where the agent has to carry a key first before it can get a reward. Our method can show very big advantages over MAPPO, over IPPO, over Qplex.
I see. Yeah, thank you very much. It's very interesting.
Yeah. So I have a question, Siddharth, for you. So one is I think it's an intriguing idea to use kind of graph neural network to model these multi-agent interactions, particularly because oftentimes there's variable amount of agents that are in a given scene, et cetera. So one question is, does your framework require that the graph is known? Like, I know that the method works for varying definitions of graphs, different number of nodes, edges, et cetera, and that the agents are only using local information. But does the method still require that the entire graph is known? And additionally, say you were to, one agent had an incorrect understanding of the graph, meaning that they were unable to properly identify all of their neighboring agents, in which case they would be receiving lesser messages than they should be. Would that hinder performance at all?
We haven't really checked that. I guess the graph is kind of known, but we can also have scenarios where the graph gets disconnected over time. Like, you can have a bunch of subgraphs each communicating within themselves. It works well in those scenarios, but we haven't really checked out in cases where there's noise within sensing, where it's basically not able to determine whether to connect to that agent or not. And I guess it's a pretty good question to look into. Yeah, we haven't really looked into that.
Okay, cool. I had another question. So you mentioned, you're talking about the collision rate, was kind of less than ideal in the first round, and you had some ideas about how to address that by adding in safety constraints. What are your thoughts on how that would play out?
So I guess when we compared the collision rate against other methods, we had lesser collisions, other MARL algorithms. We didn't really specifically focus on having safe obstacle collisions. We just the algorithm was basically trying to maximize its reward, and we had a -5 reward for collisions. I guess one easy way to have it is have a bigger penalty for collisions, but there are a few other works which have a formal guarantee of having this safety layer added onto it. So methods control barrier certificates and so on, I think we we'll probably try to have that as the final checkpoint before executing that action in the environment. So that's what we're trying to look into.
Sure, thank you. All right, are there any other questions in the audience, either on Zoom or here in the room?
Maybe a sort of general interest question for both of you. You know, some of my lab mates work on multi-agent reinforcement learning problems, and they've found the algorithms to be quite tricky to get to work and converge. Do you have any tips and tricks, the hidden secrets for members of the audience interested in working on these things? Or the dirty secrets that got you to get your approaches to work?
Okay, so that's a very good question. Actually, during our project, we discussed with our colleagues at the MIT, Google, and Berkeley. We all realized the problem that a lot of new advanced methods require intensive hyperparameter searching. So I think that's one key. For example, I talked to one of the MAPP authors, and some of the things such as the batch size, those things, they are very important to achieve a good performance of the MAPPO. So I think tuning those hyperparameters very carefully in a scientific way is vital.
Yeah, I think I agree with him. Hyperparameter tuning is kind of really important. In our experiments, we just used standard hyperparameters which worked in their original papers, and we didn't do any hyperparameter tuning. But I guess like that's pretty important to like make things work in MARL methods. I guess like there hasn't been a lot of work that has been done on like being robust towards hyperparameters as that has been done in single agent RL. So I think it remains like a very good research direction, which people could probably, yeah, look into. So it's mostly hyperparameter tuning and probably using, trying to like build off standard MARL libraries, which have shown to like work on standard benchmarks.
I had one more question for our second speaker, Gambo. So I was really interested in this idea of a kind of shared policy bank.
Yeah.
Right. So you have these like 5 potential policies that are each agent then gets to choose from. And so I kind of missed the way that you go about training this. So on the first question is, you're assuming that these agents are acting cooperatively, right?
Yep.
Okay. And so when you're training it, does it end up kind of being abstracted back to a single agent optimization problem, and where you can kind of consider that there's some optimizing agent that's trying to act in the interest of all team members, or is there a decentralized training procedure that happens? You know, I'm wondering, you know, when you have each of these different agents and they're trying to jointly optimize the shared resource, you know, that poses some interesting ways that you can, you know, allow the agents to control that shared resource. And I think when you're talking about cooperative settings, you know, that the distinction in how you can set that up isn't as important. But as soon as you start to think about adversarial settings, your general sum, you know, there's lots of fun ways I think that could start to take play. How did you do it in your work?
Oh, you mean there might be 1 or 2 agents in the whole team dominating or bias the whole pool of policy during
exactly
training.
Yeah, how do you make it fair so that each agent has a stake in how those policies get chosen?
Oh, well, actually that's a very good question. We didn't take that into consideration. We look at the distribution of how frequent each agent use different policies. It's like it's not like a uniform distribution, but it's like a fairly every single policy got used by every single agent. So there we did not do a deep analysis about how much every agent. Every single policy was biased by each agent. But that's a very good question to think about. Yeah.
All right, I think we have time for one last question if anybody has one.
I guess I've got one.
All right, Dave.
Yeah, question for the first talk. So you were studying situations in which kind of agent I can only communicate with his neighbors, you know, J1, J2, whatever. And I guess I'm wondering if you noticed or studied the kind of relevance of specific, you know, if each agent could choose to communicate with, you know, one additional agent, for example, what's the right one to choose? Something like that. Did you kind of get any insight into those types of issues?
We didn't really look into we didn't really examine the attention weights that are learned for these different agents, but I think that's a good thing to look into in future work, because I think it's pretty important, because we're using attention layers. Why not just see how important each agent is, or each entity is in the environment its own decision. So yeah, I think it's we haven't really looked into it yet.
Gotcha.
Thank
yeah,
you.
thanks so much.
All righty, well, thanks again to our two speakers for some nice contributed talks. And I think I see Elisa here in the meeting. So David's going to comment. Oh, sorry, Nagar is going to introduce Elisa. Thanks again.
Great. Yes, Elisa is here, so I think we can get us started and save some minutes. Okay. All right, so our next speaker is Professor Elisa Pielson from Boston University. She's an assistant professor of mechanical engineering at BU. Her research interests include trust and cooperation in multi-agent systems, distributed robotics control, and socially compliant autonomous systems design. Her focus is on designing robotic systems that can interact with humans and other robots in complex dynamic environments. Prior to joining BU, Elisa was a research scientist with the MIT Computer Science and Artificial Intelligence Lab. She received her PhD from Boston University in 2017 and her BS in engineering from Harvey Mudd College. Elisa, the floor is yours, and we're excited to hear from you.
All right, thanks so much for that introduction. Let me go ahead and share my screen. All right. Here we go. So can everyone see these slides?
Yep.
All right. So I'm excited to be here virtually. Today, I want to talk a little bit about modeling semi-cooperative multi-agent interactions. Before I jump into some of kind of the detailed technical talks, I wanted to talk a little bit about who I am as a researcher, because I'm not someone who normally comes to CoRL, and some of the things that I think about and motivate my research. So something that I really enjoy thinking about, I really enjoy bio-inspired systems. So I wanted to start with a video that I think is just really cool, and it is from Blue Planet 2, if you've watched the BBC series, and it's a team of seals that are hunting tuna in the Galapagos Islands. Now, these tuna are faster in open water than the seals, meaning that in totally open space and totally open water, the seals can't catch the tuna, they can't eat. But so what they do is that as a team, they trap them against these tidal pools and push them into these coastlines where then they're more agile than the tuna themselves. And as a team, they can work together to kind of create these different traps for these tuna. And then as a team, they'll set up blocking and sort of gatekeeping and create these really rich team dynamics in this game of, really a natural pursuer evader game. And I look at this and I'm so inspired by the rich behavior in these natural systems and these rich kind of interactions. Stepping back all throughout different natural systems, from the seals chasing those sheep and sheepdog type games we also see a lot of dynamics in things like ant colony optimization, how ants are able to create these distributed bridges, and the ways that fish swarm and other kind of dolphins and whales create these bait balls where they push these schools of fish together and can capture them. And so I love reading about these different dynamics, seeing these things, and I think to myself as a researcher, how can we get these robots to exhibit these same kinds of rich, complex behavior? You know, what does it mean to have herding games and pursuer evader games in our systems, and how do we go about modeling these interactions or finding these cooperation dynamics for these teams? And so I began some of my early PhD work thinking about bio-inspired herding, inspired first by Richard Bond's PhD work in bio-inspired robotic herding. And I like to share this as some recent robot history in the field, where some of the early work in bio-inspired robot herding was looking to see if we could create this robot system. In Richard Bond's PhD thesis, not my work, his work at Oxford, in having a robot that could herd a school of duck around the environment. And I also like to use this as a great example of the difference between bio-inspired design and biomimetic design. So bio-inspired design is where we look at the dynamics that underlie nature and try to create similar types of control policies for our robots. Biomimetic design is where we try to actually recreate nature. And so this was a picture from his thesis that I am always amused by, that I think is sort of buried in the pages, where early work in herding was actually seeing if they could attach a taxidermied fox to a robot to get the duck to respond more naturally to this taxidermied fox. And it turns out that was too scary for the robot, for the ducks, and it caused too chaotic of dynamics. So they went with just a bio-inspired robot in movement, but not necessarily a biomimetic fox robot. And so we can think about this herding game. And so how do we go about taking it from this dynamic in nature to designing it for robots? And so we start and we take our sheep, and maybe we can model them with some sort of potential field flocking model. So we take those sheep and we approximate them with potential fields that they have attraction to their teammates and repulsion from threats. And then we can use that potential field model, and based on those rules, we can then create some multi-agent herding policies where our sheepdogs, so to speak, our robotic sheepdogs, then exploit those attraction repulsive potentials, and we can get desired motion out of this herd of sheep, even though we haven't explicitly programmed these sheep. We're just exploiting the dynamics. And then our robotic herders, well, we can then move these points around in 2D and 3D by exploiting these different potential fields. But all of this really relies on everything operating under these rules. And when I look at these M3 Pi robots dancing around the page and moving across, it's not as rich or it's not as interactive as the nuances we see in actual sheep herding. So it's, you know, it's one way to approximate it, but I'm still not totally convinced that this is, you know, everything that we need. This isn't truly rich and complex behavior. It's a step towards these complex interactions, but it's not maybe the most important thing. And I've also looked at, you know, pursuer evader games as well, again, inspired by those seals and tuna. You know, can we use geometric decompositions? We can exploit properties of Voronoi cells to guarantee capture of any number of evaders. But again, this is all predicated based on everyone playing by the rules that we've set forward, that so long as the system obeys this geometric property that all the agents stay within their Voronoi cells and are choosing actions based on how we decide that the environment is convex, that there aren't obstacles, you know, it seems like we continue to add these asterisks to these types of interactions. And so just kind of stepping back, we can look at these models, but really our ability to get to that complex behavior, those rich, complex interactions, really requires rich, complex models. And if we want to think about it, how do we, we can start from our simple robot models, where we can think about, we have teams of robots, maybe they're all cooperative, all equal performance, or maybe we have these malicious agents. But there's this rich spectrum in between that all equal, all cooperative, and all malicious, where we have things like performance variations, uncertainty, non-cooperative teammates or human teammates, and thinking about the different design principles or things that we need to design these systems. And so that's kind of my background, or where I like to spend my time as a researcher, is thinking about the nuance of all these other types of models and how do we go about designing these new cooperation dynamics that really give us these complex interactions. So going forward, I sort of will propose that we can broadly classify the ways we model behavior in three ways. We can take a very geometric approach. And in painting with a broad brush here, the geometric approach is where we take some property of the environment, whether we're talking about the actual environment or possibly the configuration space, and we discretize it into different planning sets or reachable sets. We also look at things like reciprocal collision avoidance, and we exploit properties about the configuration of the robots that allow us to model these interactions. I'll use the perhaps poorly named interactive model of modeling interactions, where we start to take in tools from game theory. And there's, I think, a lot of great presentations. I was able to catch the last session and topics of today, where we can use tools from game theory to model different behaviors back and forth. And then what I will, again, broadly classify as learned behaviors, where we don't necessarily prescribe a specific model of behavior, but instead use a data-driven approach to try and explain some of the nuances underlying these different behaviors. And each one carries its own strengths. So I think with geometric approaches, we have these nice safety nets on behavior. They're very fast to compute. It bounds our actions to specific regions. And so it can be a great, fast approximation. And depending on how complex our system is, it might be all we need, particularly when we're thinking about robots dealing with simple or straightforward tasks. As we kind of increase that complexity through game theoretic design, these interactive models, we can get more complex behavior, but doing so leads to a more complex and requires a little bit more insight into different types of optimization techniques. And finally, those learned approaches are those ones that really allow us to capture all the nuances if we have the sufficient data to do so. And so we can really capture an emergent behavior for a specific domain, but maybe a limitation is that how do we generalize beyond some specific domain to other approaches? So with that long introduction, I'd now like to dig into two ways we've thought about interactive models of behavior, looking specifically at combining different models of interaction within game theoretic. And so the first talk about instantiation, where we also count of other agents. And so in this, we have two robots and it thinks the other agent is doing. At the same time, we can think about that other agent that also has a belief about the world and what the purple agent is doing. And this is that sort of I think that you think that I think that you think sort of reasoning. Can we exploit this belief space dynamic into our game theoretic planner and perhaps create a richer way of interacting and also reasoning under uncertainty between agents? So this was some recent work during my postdoc at MIT, where we looked at these stochastic dynamic games. And effectively what we looked at is if we could combine belief space planning with game theory to propose this game theoretic belief space ILQG problem. So with belief space planning, we get the question of how certain am I about myself and the environment? And with game theory, we get the nice, how do my actions influence other agents' actions? And combined, what we can see is that we can get these richer, kind of more complex behaviors emerge, like hiding, revealing, and seeking information that influences the other agent's actions and manipulates their level of uncertainty throughout the world. To do this, we're going to formulate our problem using Gaussian belief dynamics. And ultimately, we're looking for the Nash equilibrium for these games that we formulate. So I'll first present kind of two examples and then talk a little bit more about how we formulate this problem. So imagine, for instance, you have a two-player game. You have this blue agent and an orange agent, and the objectives are not collaborative. So the blue agent wants to gain information about the orange agent, but the orange agent is not cooperative. It's not necessarily malicious, it just doesn't want to aid directly in the blue agent's objective. And its objective is to keep up its speed and not collide with the blue agent or any of the walls of the environment. We're going to propose a simple measurement model, which is just that light sources will reduce the uncertainty about the orange agent that the blue agent has. So if the blue agent can make observations about the orange agent, if it can make those observations under light sources, they will be better observations. And so ultimately, if the blue agent can somehow push that orange agent towards light sources, then it will achieve its goal of gathering information. And by including this belief space dynamic, including this model of the uncertainty in our game theoretic formulation, what we see is that the blue agent's policy then is going to exploit that collision avoidance property of the orange agent and herd it into the light source. So in the animations that we've shown here, we're encoding these regions, these light sources, as the lighter white regions in the inset, and the gray regions are ones that are not illuminated and therefore don't provide very helpful measurements from the blue agent of the orange agent. And so we see as it goes through that it then will push the agent into these light sources. And if we were to look at sorry about that autoplaying, that if we don't include these belief dynamics in the planning, if we were to plan it without belief dynamics, then the blue agent wouldn't know to try and manipulate the trajectory of the orange agent or go through. And we see that it would just sort of gather information, but not try to exploit these different policies. So how are we doing that?
Quick clarification.
So, yeah.
Does the orange agent have to slow down to turn?
No, so we didn't kind of, in this example, there's not a more advanced dynamic model, although we do incorporate more complex dynamics in a racing example in a few slides.
Okay, so there's no disincentive for the orange to go to the light region. It just wouldn't go there naturally unless the blue agent influences it.
That's correct. Yeah. Yeah. So as I mentioned before, we're using Gaussian belief dynamics, pretty common, and then an extended Kalman filter to update those based on our dynamics and measurement models. In our game theoretic ILQR, on the forward pass, we roll out those belief dynamics over our time horizon, linearize and quadratize the rewards. And then on the backwards pass, for each of those time steps in that horizon, we're going to formulate our Q function, solve the quadratic game between the two agents, and then propagate that value function backwards. We repeat 1 and 2 back and forth until we converge to the Nash equilibrium. So we're solving for the Nash equilibrium in this game. And because we're using this Gaussian formulation with an EKF, it turns out we get linear feedback policies and predictions and a linear complexity in the time horizon, allowing us to run this at approximately 50 hertz. And I will say that a tremendous amount of credit is due to Wilco Schwarting, the first author on this work, for kind of working out these exact formulations and the implementation. So we were very excited to kind of see this in action. But this doesn't work only for these simple toy games. And so now I'll kind of talk about how this extends to a few more complicated examples. So this also works when we have cooperative games with coupled dynamics. And so in this example, what we're going to illustrate is we've got, we're going to use the analogy of a guide dog and a blind person, which is to say that our blind person agent is an agent that doesn't, is going to be manipulated or moved through the environment based on how the guide dog leads it. And the guide dog is going to lead the blind person through a tether. And so in the animation, what you see is we have this guide dog leading the blind person towards a goal. Now, the objective of the blind person is that they want to avoid sudden accelerations. So we're encoding that objective as just penalties for really fast or jerky movements. And the measurements are really only going to be observations that it observes. And the goal is that we need to get the blind person to the goal location with a reduced uncertainty about the state such that they can properly identify the goal location once they get there. Now, the guide dog is able to reduce the uncertainty of both itself and the person if it passes through light regions. So the blind person doesn't directly gather information, but the guide dog can gather information about the environment. And so what we see is that we see this cooperative policy emerge, and we see a trajectory where the guide dog will navigate through the different regions of light, but do so in a way that minimizes those accelerations on the blind person. And overall is able to navigate that blind person agent to our goal location with a reduced uncertainty. And I'll point out, without belief-based planning, what we would see is that the dog would still navigate the blind person towards the goal region, but it would do so in sort of that shortest path, least acceleration way. And when it does so, it doesn't reduce the uncertainty. And so you could end up in a situation where the agent might be at its goal location, but can't properly identify its goal location. Again, these are kind of simple examples to try and illustrate the concepts or strengths of combining both these belief-based dynamics with this game theoretic formulation.
Hey, Elisa.
Yeah.
Quick question for you.
Yeah.
That guide dog example, and I guess maybe more broadly, but do the two agents agree on the uncertainty? In other words, like, do they share the same belief representation?
Yes, in this formulation, we're assuming that the guide dog is sharing the belief or the model of how to reduce the uncertainty.
Gotcha.
And another quick clarification, so the uncertainty reduction, is it in the objective function directly, or is it just incentivized to reduce uncertainty in order to maximize the probability of reaching the goal?
The reducing the uncertainty or having a low uncertainty is in the objective of the guide dog.
Okay, got it.
Yeah. Yeah. So, and then just to provide kind of one more quick illustrative example too, this also extends to competitive games. And so in this case, and there's further details in the paper, which is just entitled Stochastic Dynamic Games in Belief Space. But what we do is we also break some of those assumptions on kind of the perfect sharing of information. And so in this case, we're going to look at a competitive racing example where we have two cars. They have separate beliefs, so they're not sharing their own uncertainty. and they're going to go around a racetrack, and we're going to have regions along the track where the agents can reduce their uncertainty. This is like regions along the track where maybe there's additional information for the agents to gather, maybe there's additional light. For the purposes of illustration, it's areas where they can reduce the uncertainty, and then any sort of acceleration, braking, or increase in steering effort will increase the uncertainty. So we have these dynamics made where you can't just kind of maximize your acceleration constantly because you might increase your uncertainty. And in our paper, we show that by combining these game theoretic dynamics with belief space dynamics, we start to see emerging behaviors such as cutting off agents, blocking, or overtaking, where one agent will manipulate the uncertainty of the other agent. So by cutting an agent off, it's forcing that other agent to take braking action that would increase its uncertainty. And we compare it against some baseline policies where we look at a more traditional game theoretic MPC policy without belief dynamics, or a belief dynamics without the MPC policy, and show that in both cases, our policy has an improved performance and wins more races on average than these other policies alone. So a quick kind of illustration, we see that exploiting these belief dynamics allows agents to cut in front of other agents, which would cause the one agent to brake suddenly. We see blocking behavior where an agent will zigzag in front and sort of prevent that other car from overtaking. And finally, that through this information gathering, or through this idea of reducing your uncertainty in certain regions, it makes overtaking possible. And just to kind of illustrate that in a picture, what we mean by that is that if you don't have information and gathering and you have a high uncertainty about your state, then given this high uncertainty, it might be too risky to try and overtake another vehicle because you might not be certain that you could avoid a collision. And in any case through this, there are safety constraints on the vehicle and on the cars that keep them from colliding with other agents. And so we were really excited to see some of these, more nuanced behaviors. And back to kind of the theme of this talk, we noticed that taking multiple tools or trying to combine multiple ways of talking about behavior, talking about interactions, allows us to lead to more nuanced interactions. And so it's not just one approach that was the strength in this case, but it was actually the culmination or combination of these two approaches. And if I have a few more minutes, I want to spend the last few minutes talking a little bit more about folding in human teammates. And so, yeah.
Before you move on, I just had a question about this. So, what in the dynamics of this racing game, is there some reason that the tail player, the kind of player behind, is even able to pass? Like, I would imagine that if the orange player is playing optimally, then there's not really any way that the blue player could pass unless you're explicitly modeling like drafting or other phenomena in the dynamics.
Yeah, so we looked at a couple different scenarios. In this scenario in particular, we give the trailing car, so I think it starts out in this example, it's the purple car that starts from behind over the orange car. We actually give it a higher maximum speed, so it has more acceleration available, so it could be a faster car, meaning that if you were to, take the track straight out, that technically it could navigate the track faster, even with a disadvantage, which means that for the orange car to win, it would need to kind of exhibit these blocking behaviors. Does that answer your question?
That clarifies things. And then I guess I have one other question that, we can ignore this if it gets too into the weeds, but, you mentioned in the previous slide or two that you incorporate chance constraints into the game formulation. And my understanding is that you're solving this in a kind of receding horizon dynamic programming style. which implies like a nesting of the game structure. And this is something that I'm really interested in my own work. But there, I'm just curious if you find that there's any weird things that happen when you're dealing with constraints in this nested interaction, in particular due to like non-convergence of your algorithm, or if there's any special tricks that you have to do to account for those constraints when you're optimizing.
Yeah, so I will, so this could be a conversation where we talk for a long time. So I'll try to keep the answer brief now, and then maybe defer to the paper. There is a lot about how we formulate those constraints. A lot of them tend to do with the safety and the formulation of the track itself. I will say that with this, there's because of the nature of the optimization, and that you are always worried about kind of not converging, you know, within your runtime, especially for something that requires this real-time solver. It did take a lot of careful consideration how we formulate those constraints and how we implement them. And that is something that I have to give credit to the first author, Wilco, on just really being an expert in some of these particular formulations.
Awesome.
I could probably talk in more detail after this.
Yeah, I won't derail. I think that was really insightful already. And I look forward to looking up and reading more in the paper. Thanks.
Yeah, but it is, I think, a takeaway also as we talk about all these things and talk about in a workshop, you know, the strengths and weaknesses of different approaches. Anytime you have an optimization like this and are looking to converge to a solution in a certain amount of time, it does take careful consideration in the design of that problem. So that way, how you implement it with your solver. We did most of this in Casati, but just being careful about that formulation. So that way, if your solution doesn't converge in time, your robot is not stuck without knowledge of what to do. But yeah, so in kind of my final few minutes of this talk, I also want to talk about some of the ways we think about human teammates. And can we think about playing games with human teammates? And what are some of the challenges about dealing with human teammates? Well, you know, they don't always make optimal decisions. It's hard to predict their behavior. We don't have direct communication with our human teammates like we do with our other robots. And overall, humans are pretty selfish and not great teammates. And so, you know, interacting with humans and human-robot interaction is its own field within the community. And one of the ways we looked at this, and we took our very small slice, is to look at how an autonomous vehicle might need to interact with humans as it's navigating social dilemmas on the road. And what do we mean by a social dilemma? We mean situations where the collective interests are at odds with the private interests. So in this case, we can think of the unprotected left turn that an autonomous vehicle needs to make. Now, if there's human drivers coming in the opposite direction in the cross traffic, the autonomous vehicle needs to ascertain rather quickly whether or not that human driver might slow down ever so slightly to yield and let the autonomous vehicle go, or if the autonomous vehicle should wait for the human driver to pass. And if you're from a less populated area, you might think, well, maybe the autonomous vehicle can just wait until the intersection is clear. But in urban environments, in cities, that's not really practical. I think many cities have their own version of, you know, in Pittsburgh, I think they call it the Pittsburgh left. Here in Boston, we call it banging a left. All these kind of interactions that drivers must make, and for autonomous vehicles to move onto our roadways, they're going to need to act like humans as well, at least insofar as they can't create more traffic. And so these social dilemmas also exist beyond the autonomous driving realm, and we propose that we could look at modeling these human drivers by modeling aspects of their cooperation or their inclination. And there's a ton of research in social psychology and how humans think about these different social dilemmas. And one particular tool is something known as social value orientation. And what is social value orientation? Well, the classic experiment puts a person in a room and they say, okay, here's $100, now split it with a stranger. You don't know this person, how would you split that $100? And the social value orientation measures the reward to self, the amount of money that somebody might keep for themselves, versus the reward to this other person or agent in the game. And so you might see an altruistic action is that person who keeps none of the money and gives the $100 entirely to the other person. In that case, that reward to other is entirely the $100. And we represent social value orientation with this angular notation of phi of pi over 2. So that reward to other is maximized, reward to self is 0. You might think we could split that $100 50-50. And that's what's known as a pro-social decision. That's that pi over 4 notation where you're equally weighting the reward to self with the reward to other. And you might say, this person is a stranger and you've just handed me $100. I don't know why I would give them any. So you keep it all and give them none. And that's an egoistic decision where you've maximized the reward to yourself and given none to the other agent. And so what we looked at is taking these tools from social psychology like SVO, and how can we fold that in to our decision-making for our autonomous vehicle? And so we wanted to take this concept of SVO and map it into our autonomous driving framework. And we propose that this SVO can actually differentiate between those drivers, whether they'll yield or not yield. And when we take it to our autonomous driving, we'll see these altruistic, pro-social, and egoistic behaviors emerge. And additionally, we'll even see competitive behaviors where you have a positive reward to self and a negative reward to another. That's almost like in that $100 analogy that somebody manages to also steal $5 from the stranger in addition to keeping all $100. And so we can take these SVO tools, and what we propose is that it turns out in the situation of the unprotected left, that it's going to be an altruistic agent that's going to decide to yield to our autonomous vehicle, that they're going to take a decrease in the reward. In this case, your reward is not an exchange of $100, but a reward is something like time to goal, braking effort, or other ways in which we encode reward functions in our autonomous driving policies. And similarly, that egoistic agent is going to be the agent that's not going to yield for the autonomous vehicle and instead continues forward. And so I'll kind of skip through some of this quickly because I know we're kind of short on time, but effectively what we propose is that we can take this SVO, which weights a reward to self or another, and we can combine it into a best response game where we still model every agent as maximizing some individual utility, but that utility function is now going to encode both the utility of them and the utility of the other agent weighted by that SVO. And then we'll solve for the Nash equilibrium, and that will be the policy that our agents are going to take. So we'll model our humans as utility maximizing, but what that maximum utility is for every agent is going to change based on their particular SVO weighting. Further, we calibrated these reward functions for our drivers on the NGSIM data set using inverse reinforcement learning. And so just kind of hop ahead to some of our results. We show that when we include SVO predictions on different drivers in the NGSIM data set, we can improve our trajectory predictions by 25% of these different cars driving in the NGSIM data set over just a baseline prediction that treats all agents as homogeneous. And some emerging trends that we see is that those merging vehicles in the data set need to be more competitive than non-merging vehicles. This makes sense if you've ever driven on a freeway at rush hour, but it's nice to see some of these kind of sensical conclusions validated over our analysis. And so then what we do is we took this and we applied it to some simulations of a vehicle working among other agents. And so if we have some autonomous vehicle coming up on the end of a lane and needing to merge, if all the other drivers are egoistic, then that autonomous vehicle, by sensing that those drivers are egoistic, and then what I don't have time to talk about, but what we're looking at is we can predict the SVO of other vehicles by looking at small samples of their trajectory and estimating what SVO best explains their behavior, that by recognizing egoistic drivers, the autonomous vehicle knows that it needs to drop back and wait. But if it can sense or ascertain that those are pro-social drivers, they'll actually open up a gap for that autonomous vehicle to merge in, and that autonomous vehicle can take that subtle social cue of seeing that gap created and merge into vehicles, more like the nuances that we see every day when we're driving in traffic. Similarly, for that unprotected left turn, as soon as it recognizes an altruistic vehicle coming towards it, it knows to take that gap and take that unprotected left turn. So that was a very brief introduction. I'd be happy to talk more about it, but overall, the takeaway, or kind of the conclusion I'd like to say, is that as we think about creating these different systems, in order to enable these rich, complex interactions, it's going to require a multifaceted model of behavior. And I hope that by showing a few examples from my own research, I have inspired folks to think about ways we can combine different tools to create more rich and nuanced behavior. And with that, I'd like to say thank you for inviting me. And also thank you to both the funding sources and the many collaborators that I didn't have time to name directly in this talk.
Thanks so much, Elisa, for the great talk. I think you did a really good job convincing our audience what is the importance of game theory and what we need to basically advance the state of the art in robotics interactions. So I think we have time for perhaps one quick question before the lunch break from the audience. Feel free to ask questions for Elisa. Okay, so while our audience are thinking about whether they want to ask the question or not, I just have like a quick question, Lisa, from you, especially with regards to the second part of your talk when you were sort of calibrating the reward functions for your autonomous cars using the NGSIM data. And I was wondering whether you account for these interactions in the inverse reinforcement learning phase too, or you just imagine that each agent is acting in isolation and then try to recover the reward function. So can you please elaborate a little bit on that part?
Yeah. So we mostly looked at the agents in isolation in sort of creating the reward function. And in particular, our reward function is, we first kind of chose some number of parameters that we thought modeled road topology. Because it's a data set, we had access of when they ended up making lane changes, when, kind of what their start goal lane is, goal lane. And so we set that up to define start positions and goal positions for the agents in training. And then, really it's looking at determining the different parameter weights for that reward function and then testing our policy. So in this case, we weren't trying to learn the SVO during that IRL phase. Although certainly I think it's something that you could look at if you know that that's the model that you want. In this case, we were trying to show that it could improve a model over a baseline model. And instead, our SVO predictions looked at short snippet, so it only required 2 seconds of trajectory history, which we felt was a nice responsive amount of the trajectory history, and it was also something that wasn't intrinsic to the agents, so the SVO was allowed to change over the course of an interaction, which is to say that it's not that an agent is universally pro-social, but for that instant in time, its behavior is pro-social.
Interesting. And just one other quick question. How can I'm trying to think how we can extend this concept of social value orientation to more than two agents? Does the method basically capture different forms of interactions with more than two agents?
Yeah, so I think it can easily scale. So I will say not I believe it was in a recent ICRA or IROS, I apologize, but a colleague at MIT, Noam Buckman, looked more at doing pairwise SVO for other types of multi-agent games. And so we can take this idea that, you know, SVO doesn't have to just be, I am going to be pro-social to everyone I interact with, but have more of these pairwise sort of relationships. So I think that also adds a level of nuance to it as well, to say that you have maybe an allegiance between different agents versus others in groups or out groups. Yeah.
Yeah, thanks so much, Elisa. Other questions from our audience?
Question here.
Okay. Yeah. So this is actually very related to what Nagar was asking. So about this SVO idea, it's a really interesting concept. So it's, as you defined it, is defined by the relationship or the ratio between the ego reward and the other reward, right? Because you get this angle. And so I think for zero-sum games, it's a very obvious, kind of naturally defined thing. But for general sum games, it seems like maybe there's some implicit regularization about the scale of rewards, right? Because if you scale somebody else's objective by like 100, then your angle is going to significantly change. And I think this is something that shows up in a lot of other algorithmic reasonings in general sum games, right? Is that you always somehow under the hood have to assume that everybody's rewards are kind of on the same scale. And it's always this little detail that I feel like we like to brush under the rug because things get weird if you don't assume that. And my question to you is just if, you know, in your thinking about this, do you have any ways of kind of coming up with this regularization in a fair way or in a principled way for games that, you know, otherwise don't have any or kind of built-in regularization in that manner?
Yeah, that's a great question. I think the kind of a quick answer is that SVO, so it's very easy to visualize as this angular representation, reward to self versus reward to other, but it can also be represented as a kind of a weighting factor from 0 to 1. So you could have a alpha versus 1 minus alpha and still capture the same kind of principles of the SVO weighting. In terms of how we appropriately regularize rewards, I would love to know when we solve that kind of general problem. I think that's one of those things we just sort of accept as a challenge right now, is so many of these problems, we have these wonderful results, but what we don't always talk about is the amount of time we spend tinkering and tuning and thinking about what the appropriate scale is. I think when we think about simple toy problems in robotics, you know, we throw some agents in a little environment and they do a toy game, it's maybe easy to think about how to scale those rewards, but that gets very difficult and perhaps a bit too philosophical when we start to think about things like autonomous driving in city environments. How do you appropriately scale the reward of a school bus versus a passenger vehicle versus a taxi? And quickly it becomes a lot of design choices that we have to make.
Awesome. Well, I think we're getting the signal that we got to wrap it up here. So thanks again for such a nice talk. I really enjoyed it.
Yeah, thanks for having me, and enjoy.
Yeah, thanks so much, Elisa. It was great having you. Thanks, everyone. I think we are now to the lunch break. For those of you who are in person, maybe for me, it's dinner break, really. Zach, when are we supposed to be back?
So yeah, we'll be back at 3:30 for the exciting conclusion to our workshop. We have about 2 more hours, so yeah, enjoy lunch and the CoRL programming. I think even if you're online, you can also go. I think there's a talk by Google, and we will be back here at 3:30 p.m. Auckland time.
Yeah, some really exciting speakers this afternoon, so be sure to come back.
All right, see you guys later.
See you.
All righty, welcome back, everybody. Looks like people are still trickling back in the real world here, but I expect that people will start to file in as we get going. But for the sake of time and making sure that we get out of here and get ourselves to the dinner banquet on time, we're going to get started. So to start off this afternoon session, we're going to jump into more contributed talks. We have 3 great talks or great papers in this session. And to begin with, we will hear from Kashandra Gupta talking about iterative LQ games for occlusion motion planning. So Kashandra, are you, looks like you're on Zoom here. So if you want to just share screen, you can begin your presentation. Thank you.
Yeah, sure. My screen's visible, right?
Yes, your slides are there. Perfect.
Perfect. Thank you. So I get started then. Hi, everyone. I'm Kushagra. I'm a 4th year mechanical undergrad student at the Indian Institute of Technology, Delhi. And today I will be presenting our work titled Iterative LQ Games for Occlusion Motion Planning. This is joint work with David Friedrich Kyle from UT Austin. So let me motivate my work first, right? So consider the following traffic scenario where all cars or agents can see each other. So in this, any car will be able to account for the motion of other cars while planning a safe trajectory for itself, right? But what happens if a larger car comes into picture, which blocks the view of some of the cars, right? So it creates an occlusion, right? So a question of interest rises here that how is, in this picture, how is the green car dealing with purple differently than it is with blue, right? And why it will deal differently is because while planning its motion, the green car does not have access to the blue car's current state and vice versa, whilst they are in occlusion of each other, right? So this basically is the motivation of our sort of work. And what we present today is basically we're presenting a multi-agent algorithm for motion planning in environments with unknown occlusions using dynamic games, right? So getting into it, very briefly, a dynamic game will have 3 components. Firstly, the dynamics, which is telling us how the state evolves. Here, the state is the concatenated state of all n players in the game. The UIT is basically the control input of any player I at any time t. We also have a cost for each agent, and this is defined as a summation over a time horizon t. And also of importance to dynamic games is the information structure, which is basically the knowledge available to each player at any time while they make a decision, right? So that this information structure basically answers the question as to how is the control input at any time for any player determined, right? And consider what happens when an occlusion occurs, right? So the dynamics remain the same. The cost, it remains the same. What really changes is the information structure, right? So I just like to provide some brief context to understand our work. I'll briefly discuss the 2 information structures of interest that we use in our work. firstly is the open loop information structure. This basically means that in such a information structure, we assume that players only know the initial states of all other players. So any player at any moment of time will only know where all the other players started out from, right? So if it has to make, if any player has to make a decision at any point of time, the initial state is only like what they can make a decision based on, right? And the solution to this, to the Nash equilibria is basically derived using the Pontryagin minimum principle. I'll just briefly tell you what's important for understanding our work. Besides requiring the time horizon T, the dynamics, and the costs, what one needs to find an open loop solution is the initial state x0 and some terminal costs, right? And when you basically use the Pontryagin principle, what you end up getting is basically these two matrices M and M for all players for all time, and these give you with these you can sort of compute the open loop controls, right, which minimize the Hamiltonian. And what's important is that these matrices are recursively defined, right? And their base case is the terminal costs which you give basically. Similarly, the other information structure of interest to us is the feedback structure, where players know the current states of all other players. So at any time step, if any player has to make a decision, they'll know where all the other players are at. They'll know their states, right? And the solution to the feedback Nash equilibria is basically it uses the coupled HBJ equations, and besides requiring the time, dynamics, and costs to find a feedback solution, you also need terminal costs. And you assume a quadratic value function, and that is encoded via the matrices Z and zeta here. And they basically give you feedback gains and affine terms, which you can use with the states to get an optimal control, the optimal basically control, right? What's again important here is that these value functions is basically defined recursively, and the base case again is the terminal cost that you give, right? So let's just go into the method, right? Consider this: when green and purple are fully visible to each other, right? So while as they move along their paths, they have access to where the other car is at any point of time. So that naturally motivates us to say that whenever there's visibility, we'll use a feedback solution, right? We'll use a feedback information structure in our work. And the tricky part is the occlusion part, right? So what happens? How do we plan for green and blue, right? So we might not, at this point, green might not know where blue is, or blue might not know where green is. But let's say we rewind the game a bit, right? So let's say we are at a time period O1 where blue was not yet in an occlusion, but it was just about to go in an occluded state, right? So at this, from O1, we can determine basically when the occlusion started. So O1 can correspond to each player knowing, okay, what was the last known position of the other player, right? And that sort of motivates us to use an open loop information structure to basically represent occlusions, right? Because just because we go into an occlusion, if we know the state, we can sort of make an open loop game to model the occlusion part. Basically our work here, the trick is to switch between feedback and open loop, depending upon whether players are visible to each other or whether there's an occlusion going on, right? So provided that we have to use both feedback and open loop, we have to sort of make an hybrid information structure. And we think about, hey, we thought about, hey, how will a hybrid LQ game look like? So let's start by talking about the most basic case first, right? When all the occlusions are predetermined and known to us. Consider a situation where we have to plan for T time steps. And out of that, we know that for periods O1 and O3, we'll have full visibility. And for periods O2 and O4, we'll be in occlusions. X0 is where we start from, and TE, the times TEI basically determines when, basically are the times when we go from occlusion to visibility or vice versa, right? So let's see how we can solve such a game. And we solve such a game by going essentially backwards from the final time. So in this example, the final time from, if you go backwards, firstly, we've got to solve an occlusion time period. So using the open loop solution, we know that we can get the matrices M and M. Then if you go a bit back, we encounter a feedback. We encounter a visibility period. For that, we can use a feedback solution, and so on. Essentially giving us an idea of what information structure to use at what time. But our work's not done here because we've got no way of switching between these modes, or we've got no way of basically linking these the periods O1, O2, O3, O4 together. And we do that by modifying the terminal cost. So what we say is, in our method, the terminal cost for any period will be given from the succeeding period. So if you're in occlusion, the terminal cost for the open loop solution will come from the next feedback period. So that's how we link our solution. This is for the case when occlusions are known. In our complete framework, we've made a way where occlusions are not known beforehand. We accommodate general costs, and we also accommodate nonlinear dynamics. For that, we've developed an iterative LQ algorithm where we take an initial state and strategies. We essentially get a trajectory about which we define deviations. And from those, using that trajectory iterate which we have, we can get linear approximations to dynamics, quadratic approximation to costs, and on that trajectory, we can find periods of occlusions and periods of visibility, which is OJ. We use these three things, these are three components to a dynamic game. We use it to solve the hybrid LQ game I just talked about, and we basically get a new trajectory iterate, and we do this until convergence. And the solution, the converged solution, is basically the trajectory we need. Just quickly going about the results here. In our work, we include a 3-player overtaking example where a smaller green car wants to overtake a larger purple car, but there's a pink car coming in the opposite direction, and the green and the pink car are basically occluded to each other. This is a 12-state 6-input dimensions, and we've got some in the costs. We basically sort of penalize the control input. We don't want the cars to come too close to each other. We penalize the distance from the goal or from the lane center. We penalize whether the cars cross the lane boundaries. We penalize their speed and basically penalize if they reach their speed bounds. The results of our work are encouraging, and out of the 100 random initializations, 96 trajectories converged. Here's a representative converged trajectory. You can clearly see that the green car successfully manages to overtake the larger purple car, and also maintains distance and sways away from the oncoming car. Our method performs well on time and is relatively efficient with a runtime of about 7 seconds. In comparison with the purely
maybe just do your conclusions. We're running a little bit late.
So if I have to compare it with a purely open loop or a feedback solution, we can say that our method in the dots here is not as conservative. It gives much less conservative trajectories than open loop solutions, but also maintains its lane boundaries better than a pure feedback solutions. Thank you.
Cool. Thank you very much, Kushagra. And next up, we have Yishuan Jia. You online? Yishuan?
Yeah, I'm online.
Great. Okay. And you're going to be talking about autonomous multi-agent racing, strange potential dynamic games. So take it away.
Thank you. So, So can everyone see my slides?
Yep.
Okay, cool. So hi everyone, thanks for attending my talk, and I'm Yixun Jia, and I'm currently an undergrad student in the EC department at the University of Illinois. So today I will talk about our recent work, autonomous multi-agent racing using constrained potential dynamic games. This is a joint work with my collaborators, Malik Bhatt and Professor Nicole Mayer. So first of all, autonomous racing is a really nice case study, as the agents are highly interactive during races, and they have to make decisions in real time. And also they have to do so efficiently due to the competitive nature of the races. Also, they want to act intelligently in order to win the race. For example, if they're behind, they might want to take over, and if they are leading, they might want to generate some blocking behaviors. So there are multiple recent approaches on autonomous racing. There are works on using model predictive controller, which basically maximizes the progress along the track and treat other opponents as obstacles that are to be avoided. There are also learning-based planner, which mainly focus on the path planning aspect and do not really take into account the interactive nature of racing. On the other hand, game theoretic planner has also been studied extensively. There are a game theoretic planner for 2 players, and there are also recent work on game theoretic planner for multiple agents. Especially in 121's work, they developed a game theoretic planner using sensitivity-based approach, and we will compare our algorithm with their algorithm in this work. So given a model of each agent engaged in interactions, we can use ideas from game theory to reason about their behaviors. A model here can mean the dynamics and the cost structure of each agent. For example, in the slide, we have 2 agents, agent 1 and agent 2, and each of them has its own dynamics and cost, where here X is the state of agent, the superscript is the index of the agent, K is the time step, and the uppercase L is the running cost, while the lowercase s is the terminal cost of each agent. So also they are subject to a set of constraints, which I did not include in the slide for simplicity, but they are also subject to a set of constraints, such as they need to stay within the track and they need to avoid collision with other agents, etc. Assume that all agents are trying to minimize their cost. The equilibrium state of the overall system is captured by a Nash equilibrium. At the equilibrium, no agent would want to change their strategy, given that all other agents won't change their own strategy. So in terms of the notation, as we can see here, the Nash equilibrium condition, where I is the index of the agent, it simply says that if we view this gamma star as the strategy at the equilibrium, and we only change the strategy of agent I, it will only result in a higher cost of agent I. So in our case, the strategy simply means the path planned by that agent. So one nice thing about game theoretic planner is that it allows the agent to take into account other agents' possible actions and plan accordingly. But in general, solving for Nash equilibria is untractable. And one common approach is to use iterative best response. But convergence in real time for iterative best response might be tricky, and it scales poorly as the number of agents increases. Okay, so at this time, you might be wondering, okay, so autonomous racing is cool, and game theoretic planner also sounds cool. What's new here? So it turns out that there is a special type of game called potential game, where the problem of finding Nash equilibria is simplified. The idea is that if there is a function P that satisfies the equation in the slide, where I again denotes the index of the agent, and the intuition of this equation is that for each agent I, if we fix the strategy of other agent and only change the strategy of agent I, the change of cost for agent I is captured by this by the change of this function P. But note that this function P is universal. It's like this equation flows for every I. So it turns out that if there exists such a function, which is called a potential function, then the problem of finding a Nash equilibrium of the original problem simply becomes a single optimal control problem, where we only need to minimize this potential function P subject to the dynamics and constraint. Notice that here the dynamics is the joint dynamics of all the agents engaged in interaction, and the G is the vector that collects all the constraints for the agent. Also note that in order to be able to do this, we do need some symmetries, and which means that we do need the agent to share the constraint symmetrically. So now back to racing. How can we apply this idea to cast the problem of autonomous racing as an instant of a potential game? First of all, we need some assumption of other agent cost structures. Inspired by the sensitivity analysis approach from 121's work, we designed the following cost function, where P is the progress, gives the progress of the agent, and the D is the distance between two agents. The intuition here is that the first part is trying to maximize the progress because we are trying to minimize the cost. So we have a minus sign here. And the second part is trying to minimize the distance to other agent, while alpha is a parameter that we need to tune. So the idea is if the agent is behind, minimizing the distance to other agents simply encourages the agent to catch up, which is essentially the same as maximizing its progress. But if the agent is ahead, minimizing the distance to other agent incentivizes blocking behaviors. So alpha value here is like the weight given to making progress versus being more interactive with other agents. So with the cost function we designed, the racing problem does become a potential game with the following potential function. So now if we want to find the Nash equilibria, instead of iteratively solve for each agent strategy, we can simply minimize this potential function. To evaluate the performance of our method, we consider a racing scenario between two agents, where one of the agents used our algorithm and the other agent used the benchmark in 121's work. We run the simulation 100 times with different initial conditions. We measure the solve time and examine the quality of the resulting trajectory. We found that our algorithm is always winning the race. And after investigating the trajectories, we found that our algorithm was able to generate blocking behaviors around the corner as shown in the figure on the left. Here, green color is used to denote the agent that's using our method, and the blue is used to denote the agent that used the benchmark. As we can see, although the agent using our algorithm, which is called ego, enters the corner later than the baseline, it's able to push the baseline against the boundary and take over. And the solve time is shown in the right figure. As we can see, our algorithm is significantly faster than benchmark. So we also run a set of hardware experiments, but I will only show one of them here. Here, green is used to denote the trajectories of the drone that's using our algorithm, and the other two agents are using an PC controller, which treats the other agent as obstacles that moves with constant velocities. As we can see, although our drone start second, it's able to finish first. So here's the summary. So the problem we were trying to solve is path planning for multi-agent autonomous racing, and we designed a cost structure which makes the problem a potential game, which enables us to solve a single optimal control problem in order to obtain a Nash equilibrium. Our insight here is that we can utilize the coupling among agents to simplify the problem. And one possible future direction is to investigate and compare the computational complexity of iterative best response and our approach. Okay, finally, I would like to thank my collaborators, Malik and Professor Mayer, and also the reviewers who provided us with helpful feedbacks. Thanks for listening.
Cool. Thank you very much, Yishuan. So as a reminder, we'll have questions for the three authors in this session, the previous author, this one, and the next one after the next talk. So next up is Shrey Bansal. Is he online or in person?
I'm online.
All right, Shrey, good. All right, he's going to be talking about Nash equilibria in Bayes games for coordinating with imperfect humans. So take it away, Shrey.
Hey everyone. So I'm Shrey Bansal. I'm a PhD student at Georgia Tech, and I'm happy to present this work today that I've done with my collaborators, both here at Georgia Tech and also at Ohio State. Okay, so I don't think I have to convince anyone here in this community of the importance of multi-agent interactions, but here are a few examples of the different types of interaction that happen between humans and AI agents. And talking more recently, we've seen a number of AI systems that have shown impressive performance in competitive games like Go or Dota or StarCraft. Some of this progress can be attributed to the improvements in compute and the machine learning systems, but also the fact that the optimal competitor that these systems were trained for is a lower bound on the performance, and suboptimality on the part of the humanism is actually an advantage for the AI system. However, cooperative games still remain a challenge. Here, human suboptimality can hurt coordination. Also, since the different individuals have different preferences, the AI agent has to adapt to the specific agent it is interacting with. Some solutions in prior work include communication between the agents to enable the coordination, as well as using data from human-human interaction to learn models of the human behavior and then adapting the agents to coordinate with them. But there are some issues. So communication is not always available, and effective communication protocols are an open problem on their own. Collecting data can be unviable due to cost or safety concerns. And this leads us to the research question that motivates this work. So the question that we're trying to explore is, how do we enable human AI coordination by introducing priors on human behavior without assuming any access to the interaction data? In particular, we want to utilize our knowledge of how humans behave, as well as game theory, to adapt to individuals that we interact with. For this, we will use the fully cooperative game Overcooked, because it includes both strategy and motion control challenges and is even difficult for humans to coordinate it. Here we have two agents with the goal to deliver as many dishes as possible. Each agent has a discrete action set, which includes moving up, down, right, or left, a no-op, which means the agent stays still, or interact, which makes the agent pick up an onion or deliver a dish, etc. As you can see, the agents have to complete a number of high-level tasks, like delivering the onion or grabbing dishes, and they have to coordinate both at that high level, but also at the low level where they're trying to avoid colliding with each other. And in this case, when a soup is delivered, both agents receive a reward of 20, and this is the same reward that both agents get, no matter which of them delivers their soup. Okay, so let's look at a simple method for performing this task. We can train agents to solve this task by using self-play, whereby agents learn by interacting with a copy of their own policy. This method performs well, as we can see in this sample trajectory. The agents are successful in performing this task when they are paired with an agent that they were trained with. However, the behaviors that these agents exhibit are not as diverse. Here I show some rollouts of the same model starting from the same initial state. We can see some differences between the actual trajectories, but the diversity at a high level behavior is limited. And so to combat that, we next try to pair this reinforcement learning agent with a suboptimal version of the self-play agent. Here, the agent takes an action according to its trained policy with a probability P and chooses a no-op action otherwise. we showed trajectories from the agents trained with different values of P here. And then that actually shows a lot more diverse behaviors. So now that we've artificially induced diversity into the reinforcement learning model's behavior, how do we combine this to help coordinate with humans? Well, before we actually get into our approach, I just wanted to give a quick preview of why we will use game theory here. Game theory provides us with language and tools for multi-agent decision-making between rational self-interested agents, and also equilibria in game theory are solution concepts that can lead to reasonably good outcomes for all the agents. And that's why we will use it in our work. So let's discuss how we will model our problem as a normal form game. We already have learned policies for the agents, and now we can use this policy network for sampling trajectories for the agents, which are simply fixed length rollouts. Once we have these fixed length rollouts, we get with those 4 trajectories for each agent in this diagram. And then if we combine this by pairing all those 8 trajectories with each other, we get a static game, a 4x4 static game. And we can solve this game for the Nash equilibria and select one of these to determine the next action for the AI agent. Now, instead of having a single agent type, let's imagine we have 2. And in the figure, that's type 0 and type 1. And each of these has a probability associated with it. This is a form of an incomplete information game or a Bayesian game where the type of the agent is unknown. In this case, we can sample the agent type based on the probability distribution. And then once we have an agent type selected, the rest of the sampling procedure remains the same. We still sample trajectories, construct a static normal form game, and then use that to take the next action. The next question that we're trying to answer is, how do we determine the probabilities of the different action types of the different agent types that are present in our game? And here we can model it as a belief that is modeled through a hidden Markov model. And as the agent takes actions and observes its human partner taking actions as well, the distribution updates, and we can converge to a better belief of what the human's type is. Okay, so our experiment, now we get to our experiment, which includes 3 agents. One is the self-play agent, which is referred to as PPO. The PPO no-op is the self-play agent that is the reinforcement learning agent that was trained with the suboptimal self-play agent, as well as using Bayes Nash, which is our approach and includes both PPO and PPO no-op. We evaluated these agents with a behavior cloning model that was trained with actual human data. And these are our results. So the results show that while both PPO and PPO no-op perform similarly, by combining these policies in the Bayes Nash framework, we're able to perform 40% better than them. To get a little bit more understanding why the self-play model is inefficient, let's look at this example of a trajectory where the self-play agent is interacting with the H proxy. Here, the self-play agent expects the human to move down and stubbornly tries to move to the left, while the H proxy agent does not comply, leading to a long wait time and inefficient coordination. By inferring the human's type and adapting its behavior, Bayes Nash is able to avoid this kind of situation. Okay, so in summary, we were able to induce some plausible diversity in the reinforcement learning agent's behavior by training with suboptimal partners. We used game theory and probabilistic inference to coordinate by combining these multiple reinforcement learning agents. We were able to show that this improved coordination with humans without actually assuming access to data of human interaction. There are many future directions and questions that we want to address, but I just wanted to highlight a couple of them that we are looking at. And the first one is, well, what if we did have access to a small amount of data? How do we improve performance? And the second one is, how do we generalize to more agents and also to other domains? So thank you everyone for listening, and I look forward to your questions. If there's any questions that were not answered, or if you have any ideas you'd like to discuss, please drop me an email. Thank you.
Okay, cool. Thank you, Shrey, for the excellent talk. So we have approximately 10 minutes before the next speaker. So we're going to open it up to questions about the last 3 talks. That was iterative LQ games for occlusion motion planning, autonomous multi-agent racing using constrained potential dynamic games, and then this last talk, which was Nash equilibria in Bayes games for coordinating with imperfect humans. So if we have any questions online, or if you're in the audience, we can give that a mic.
I can start off with one question. So this is for the first speaker, the first talk that we had. One of the things that I saw was your method, you said converged for like 96% of the trajectory or the samples that you tried this on. I'm curious what happens when things did not converge. Like why was that, or what were those issues stemming from that caused non-convergence?
Yeah, thanks for the question. So basically these the trajectories which did not converge, what it turns out that like the initializations were like so off the mark that we didn't get anything meaningful. So the initial state wasn't feasible in itself, in the sense that it wasn't a safe driving scenario to begin with. Like it was too close. The opposite car was too close to the occluded car.
Interesting. So you're saying that the problem was essentially primal and feasible. I'm just interested because it's a very interesting setup where the information structure is actually state dependent in the game. And that's something that I think is pretty novel. I've never seen something like that. And I would imagine that you get into some weird cases where you can get into cycling or other kind of convergence issues. But it seems like those didn't show up in the experiments you ran. So that's cool. All right. Any other questions here in the audience?
I have a question. So in the final talk, you talk about doing this PPO based planning after having inferred some things with this hidden Markov module or hidden Markov model. And I was wondering does PPO plan in the history or belief space? Like, is it solving a POMDP with that hidden Markov model, or is it just kind of taking either the most likely or the expectation of your belief, over these possible hidden Markov states, and coming up with an action based on that?
Yeah, I think if I understood the question correctly, I think it's the second one where the PPO is separate from the hidden Markov model. It's the hidden Markov model is basically trying to infer the probability of which of those PPO agents is more likely given the observations. And then based on that, it just selects one of them, and that's what we use to determine what the action should be.
Okay, so the agent isn't really capable in that case of like doing information gathering, like costly information gathering actions. Like if there was something that was costly but might help it by giving like information about which agent it was playing against, it wouldn't be able to do that with the current framework.
No, you're right, it would not. That's an interesting direction, but yeah, we don't currently do that.
Okay, cool. Oh, yeah, it looks like there's a question in the chat, maybe. Oh, it's just, are the paper links for the works presented? I think we'll post those on the website.
Haruki has a question. He's raised his hand.
Oh, Haruki. Yeah. Did you have a question?
Haruki, do you have a question?
Yeah, I'm not sure, maybe.
Haruki, you're muted. We can't hear you, Haruki.
Says unmuted. Maybe he's away from keyboard or something. Okay, we still have time for one or two more questions, if anybody has one. I guess I have a question on the second talk. So it looked like you were directly for Yishuan, it looked like you were directly kind of incentivizing interaction by having this a lower, if I understood correctly, a lower distance is like a positive reward. And you kind of showed that that results in more kind of like blocking behavior or something in the drone racing. But I was wondering, what are the potential downsides of using that term in the objective function?
Yes, thank you for asking the question. So I think the one downside of this term is that if you have multiple agents, the thing sometimes become a little tricky because it tries to minimize the distance to like both agent. You know, for example, if you have 3 agents and one of them is using our algorithm, it tries to minimize like the distance to the other 2 agents, and sometimes the behavior is like it may try to stay between the 2 agents. So you do need to tune the alpha like accordingly. So yeah.
Okay. So it does. You did find it was a little bit sensitive to the value of alpha that you chose.
Yes. Currently, we need to like hand tune the alpha. Yeah.
Yeah. Okay. Cool. And then last question, I think for this session was Haruki's from online. How non-trivial is it to find or prove that a function is indeed a potential function? So I believe that was in the second talk, right? Yishuan, I think that was yours again, right?
Oh, yes. So we do have a proof in our extended work, but for this workshop, I don't think we include the proof. And in, regarding how non-trivial, I think there are like multiple conditions you can use. And the one I showed in my presentation is just like one of them.
Okay. And are these potential functions, like, do they exist for all the games that you tried, or did you have to like choose your cost function really, really carefully to, make a potential function exist?
Yeah, I think the thing is really that the part that include other agent need to be somehow satisfy some symmetric structure in order for this to work. And sometimes if the cost structure is very asymmetric, you can prove by contradiction that for this problem it cannot be a potential game, something like that.
Okay.
Yeah.
Cool. All right. Any other questions before we move on to the next invited speaker?
I can ask one last question. So for the second talk, the racing paper, so you're solving for Nash equilibria, and I missed how you're solving for those equilibria. Are you solving via like dynamic programming, and are you therefore solving for a feedback Nash, or are you solving for open loop Nash equilibrium?
So thanks for asking. So in our case, we are solving for an open loop Nash equilibrium, but we are implementing this in a receding horizon fashion with a relatively small time horizon. So it like mimics the feedback nature of, yeah.
Sure. Yeah, I just wonder because in racing, there's an incentive for leading your opponent, right? So like the relative distance, or some related cost function. Like I think you guys had not exactly that, but some similar cost on the terminal state difference and distance along track. And with like an open loop Nash equilibrium, right, the agents aren't able to comprehend that changes in their strategy will induce responses in their opponents, right? That you would require some kind of either feedback structure or like a Stackelberg information structure. And so I wonder, when you were running your experiments, is this something that you ran into as a problem, or is actually the open loop Nash formulation sufficient for capturing the strategic behavior that you think would be characteristic of competitive racing?
Thanks for asking. So I think in our hurdle experiment, it performed like relatively well because our planning horizon is like only 0.5 seconds. So yeah, but I think that's like a really interesting direction to like investigate how it's different from like feedback Nash equilibrium. Yeah, thank you.
Thank you.
Okay, cool. Let's give these speakers one more round of applause. And next, we have another invited talk that Forrest is going to introduce.
Alrighty. I am pleased to welcome Drago Anguelov. Hope I'm pronouncing your name correctly.
Close enough.
Close enough. Okay. You're kind. So Drago is a distinguished scientist and head of research at Waymo, where he's been for nearly 5 years. Formerly, he was the director of perception at Zoox. And before that, worked 8 years at Google, where he worked on stuff such as pose estimation in Street View and object detection in Google Photos. Drago also worked for 2 years at a company called Like.com. Drago completed both his undergraduate and graduate studies at Stanford. His PhD was under the supervision of Daphne Koller, but worked extensively with Sebastian Thrun. Drago has made major contributions to the field of computer vision and machine learning with nearly 90,000 citations on Google Scholar. Drago, we are so excited to hear what you're going to tell us about today.
Thank you for the kind introduction and for having me. Let's see how I can speak close enough to this. I can just do it. Yes. Okay. So, yes, I'm Drago. I lead the research team at Waymo. Some of those folks are here, contributed to the work I will be presenting. Our mission, the research team, is to leverage machine learning and push state-of-the-art in autonomous systems using machine learning. And today, suitably with the team of the workshop, I will tell you some of our work on improving models of behavior, which is key for driving on the road. Now, this laptop is not switching. Okay, there we go. Okay, so Waymo is Alphabet's autonomous driving technology company, and we focus on two categories: moving people with our Waymo One service, and moving goods with our commercial delivery arm Waymo Via, which features these big Class 8 trucks and also some delivery vans. Since October 2020, with Waymo One, we offer the world's first fully autonomous service in Phoenix East Valley, 100% without safety drivers, fully autonomous. We call this rider only. And we started fully autonomous driving in San Francisco this year. And this is a video of our first ride there, which if Zoom permits, you will see is already fairly complicated. There is this loading vehicle. There's people walking around on the street. There's double parked big truck. So we're progressing. This is just to give you an idea, and I don't know, what is it, half hertz, but on the top, you can see roughly, this is a viewer that shows pretty LiDAR clouds colored by the semantics of our perception system, which is all quite nice. And it's even nicer when you look smoothly. I think here, if you look long enough, you will see, for example, here we will execute an unprotected left turn. And, we will be reasonably assertive. We won't wait every single vehicle to pass. We will actually cut in at the right time and continue, which is great. And I think there is more scenes here. I think you guys get the idea, right? So that was just our very first ride. I think they get interesting from there. I think one thing, as much as I love our viewer, I think it's awesome. I went on a few self-driving rides myself, and when you're in the car, you see this. So there's something very visceral and cool watching the steering wheel turn and the car drive. And again, at half a hertz, it's I'm not sure if that's an experience to me, but I felt a big thrill in the beginning, and then it felt comfortable and maybe a little boring. So, keeps going for a while because we drive a lot these days. But it's a unique thing. I think we're in this, challenge for a reason. That's really exciting. And so speaking of agents and behavior modeling, the city is full of highly interactive environments. This one we've shown before. This is crowds exiting the baseball stadium. So you can see tons of people exiting and going inside the vehicles. There's vehicles all around us also. And here we need to go through some fairly narrow passageway flanked by vehicles on all sides. This is included autonomous mode, by the way, on top. And we keep going. There is letting people coming in, there's some people coming out of garages. But ultimately, if you look at this, right, we need to model and understand the behavior of these agents. And there's quite a lot of agents. If you come to this intersection, I mean, this baseball game really have a lot of people. There's hundreds of agents on the road next to us, right? And we need to process all of that and behaviors. Now, there's a lot of maneuvers and involved when we drive. I think this thing is, let's see, is it stuck again? It's stuck again. Someone should ban Zoom at these things.
There's a video optimization.
We tried. It's another Zoom.
Yeah, so here's a few other interesting scenarios. This one is just what you need to do to turn right on red. So it's unprotected red. There is all kinds of people around you. You can see vehicles, bikes, and when everybody clears, we will go. But this is we need to be able to do these maneuvers frequently and safely. Right, so here we go. We let everyone pass, including the, I think, motorcyclist. And you start getting interesting scenarios where you need to react quickly. Here, there's a bicyclist in our side of the road that just appears out of a collision instantly. And so there's interactions with that as well. One other interesting part is, so we now also do autonomous driving to the public in downtown Phoenix. And downtown Phoenix turns out to be a place of a ton of construction. I did not realize, but they're really into it. And this is us navigating makeshift construction area with need to interpret all these, poles and signs telling you where it's okay and it's not okay to go, right? And this is unrelated, not strongly related to the initial road graph. So that is us doing this. What is next? Just latest news. We got driverless permit to take people around San Francisco. So more videos will be forthcoming. Fully driverless. We started driverless operations to Phoenix Sky Harbor Airport from downtown. And we announced Los Angeles is our next ride-hailing city. And here's even a clip of Los Angeles. It's again, dense urban area, actually quite similar to parts of San Francisco. And there is, again, lots of traffic. There is double parked vehicles that we need to pass and people loading and unloading. This is, I guess, par for the course that needs to be had. So hopefully with these videos, I gave you at least some intuition at 0.5 Hertz about the complex interactive scenes that we have to deal and handle. And I think this is a core part of what makes autonomous driving an interesting domain is the rich multi-agent setting. So we need to accurately understand and model behaviors of the road participants in order to make right decisions. So that's a difficult problem, but we have a key aid. So we have a huge trove of miles and observations collected by our own vehicles, millions of miles, where you can see how people actually behave in the wild. And we can use that data and learn models of behavior that we can then use, right? And so that's a theme in this talk. And I think around this theme, I'll present some of our recent work. So I will first talk about behavior prediction, also known as motion forecasting task. There we aim to model the behavior in a supervised or open loop setting for longer periods of time. We try to forecast the distribution of where agents may go. And then I'll talk about another part of our research on agent models, whose goal is to produce a robust closed loop. And let's talk about behavior prediction. What does it look like? So many systems in this space follow the structure, which we also described in an old paper of ours called multipath. You take in representation, the world state, representing the environment around you on the road. So this is the agents, locations, past history, the traffic light states, description of the road graph is or reconstruction with like the lanes and the road boundaries and potentially signs and so on, and their relationships. And then we feed this into a deep neural network encoder, whose job is then to decode a compact prediction of the future state of the scene. So if you have n agents in the scene, for each, we will produce k trajectory hypotheses. Those can go up to several seconds in the future, with probabilities, with likelihood for each mode. And then with each trajectory is represented as a sequence of x, y, and maybe heading on fixed intervals with the associated uncertainty. And this is an example of these models in action. So this is a state-of-the-art model, maybe from a year ago or so. And you can see there is predictions up to 8 seconds in the future. We show the top 6. The more saturated colors are the more confident, the more likely ones out of the set. I mean, these are ultimately agents are non-deterministic. You have multiple options for each. So when we initially started with multipath, we were actually computer vision people, and we used the raster representation to represent the scene, which is essentially an image-like representation. So you take all the features you have and you discretize them into some image grid, and then each channel is some other semantic property, and then you can apply your favorite computer vision architectures, which are good and powerful, and so on. So we worked with this. But there is some drawbacks here. So there is an unpleasant field of view resolution quality trade-off. And so essentially, the finer you make the grid, the more expensive the compute. But the coarser you make the grid, then of course, the more you discretize the continuous entities that open perception can produce. So it's not great. And the other part that is very important for this domain, so long-range interactions are important. They occur, distances coming from afar affect you. If you apply a standard neural net architecture with 3x3 filters, typically how they're done, right? Then you need to stack quite a few layers until you have a neuron can see all the relevant signal that's needed to model long-range interactions. It's not great. So we moved to a vector input. So these are polylines, ultimately representing most of the properties and associated also with continuous attributes. So why is polylines? I mean, your past pose, you have a sequence of similar to our predictions locations. So that's a polyline. I mean, lanes can be represented as polyline, their boundaries can be represented as polyline, sidewalks, and so on. And so now you can represent things arbitrarily accurately, but there is a cost, so you need to rethink the architecture. And so we settled on rethinking architectures for 1 year or 2. And this is one that we published early this year. So maybe I'll say from last year, but this is essentially we ablated the space of options. And so essentially you can see the different types of input. For each, we ablated what is the best encoder for that type of input. So maybe agent poses are well consumed by OSDM, and maybe the road graph with something else. And then we carefully arrange how all these things are fused to produce the final embedding with some layer we call MCG, multi-cortex gating with this attention-like layer. So all of this, when it's all said and done, you get actually still a reasonably simple neural net architecture that's very performant, and at the end was state-of-the-art on the key data sets in this space, which is Waymo open motion data set and Angular's. So we were very proud of this work. I think some people in this room contributed a lot to it and worked on it hard. It required a lot of domain expertise, and it has a lot of these custom details. And so it's difficult to trade off capacity versus performance in this architecture, it's too heterogeneous. It's not simple. You need also domain expertise. And so we wanted to rethink this space. And so we took a step back and said, okay, what are the goals of an architecture space for behavior prediction? And here's some desiderata that the team came up with. So well, first you want a simple architecture. Ideally, it should be easily usable by people that don't in any way represent experts in behavior modeling. Just general machine learning people should get home with this. It should be easily tunable. So you want to span with an architecture family, low latency and high quality, and you want to have knobs to tune and achieve the full operating spectrum. So you want that to be easy. And of course, you want highly scalable architectures with that. And so then a few consequences to this ensue. So one is, let's use transformer, right? Popular, I think by now, uncontroversial in many ways, right? Widely popular in a ton of applications, and so should have great scaling properties here as well. And one of the interesting questions when you build an encoder is how to fuse modalities, and there are several approaches. So one of them is early fusion. So you just concatenate all the inputs, heterogeneous or not, and you apply cross-model attention on top. That's actually very uncommon. Most models at the time when we did this work had not done early fusion. A lot of models have done late fusion. So there, you just take each input and you apply attention just to the input itself and process it, and then you concatenate the embedding. So that's late fusion. And the team also explored hierarchical fusion, which is a combination of these two approaches. Next question is how to model the interactions in this transformer over the space, in the space-time lattice. So you have time and you have the scene elements over time. How do you attend to this? And here we built upon all the work. This was a collaboration with Google Brain called Scene Transformer. And ultimately, you can have several options. So you can have spatial attention, which is entities at the same time step. Obviously, they interact with each other. Temporal attention captures the dynamics of objects over time. And of course, you can have multi-axis attention, which attends to the full matrix. And so out of these, we made 3 different blocks that combine them in intuitive ways. So these 3 blocks were our units out of which we made the encoder, right? And that resulted in a paper called Waveformer, Motion Forecasting with Simple and Efficient Attention Networks, essentially exploring the space of choices that we outlined. And this paper is on arXiv, and it was actually submitted to CoRL and not accepted. And I personally, it's presented at CoRL anyway. I like this paper. I think it's good. So here it is. Here's what the things you will find in the paper: a ton of interesting studies, learning about the effects of all these design choices. And I'll just show you graphs like this. I'll show you just one. For more, please refer to the paper. So this is latency, right? Slower models, faster models. This is quality, better models in quality, worse. And so you can see the kind of the curves here. It shows you that if you want low latency, so the green boxes are late fusion. If you want somewhat intermediate trade-offs between latency and quality, hierarchical fusion is good. And here you have on the slower side, of course, and the early fusion is more expensive. But also what we're paying is state of the art. And this is actually with early fusion, which was quite uncommon in the architectures before. And furthermore, the state of the art is on both data sets. And this was obtained, which the team is proud of this, with a model that does not build in any special knowledge about the domain. So this is just a generic architecture. There was no knowledge built into it that's somehow special to all these inputs that come in. So that's pretty cool. We not only have this result, of course, we have the really good control over the full operating space and understanding how to build ourselves faster, cheaper models or slower and high quality. So, yeah, this motion forecasting task is great. Actually, is a workshop for architectures. And this is some results. I don't know if you can see again my favorite half-hertz video. Here's a bunch of pedestrians crossing. Here's the vehicles. Generally, the behavior is quite nice, following what you would expect in the graph. And here's another graph, somewhat unusual intersection topology with a bunch of U-turns that it's nailing. So ultimately, powerful model. And now let's talk about modeling interactions. So far, we're a bit more in architecture space. And so here is another simple scenario with what should be familiar to you, these colorful predictions. And now let's ask some questions. Even this simple thing looks a bit messy. So is this a predicted collision or not? Or maybe over there, is there a predicted collision? You can't see it with half a hertz, but right, like what's the probability? These questions are very relevant when you build a planner, right? These are things you want. So would we say these agents interacted? Maybe. By how much? Right? And so let's dig a bit into the output of this network. So far, and a lot of the traditional benchmarks in the space treat predictions as independent. So you say every agent, given the scene, there's a set of what I would call marginal predictions, right? So independently, these are the outcomes for this agent. And so they're good by themselves, but they can well represent interactions. Here's an example, agent A and B each can turn with 50% left or right. So with 25%, right, they will hit each other. And you have no way to represent in this this output the case that maybe that should be unlikely. Maybe that doesn't happen in the data and should be zero. And so that's not very good for planning. Ultimately, you want to see interactions of yourself and other agents. If you just get marginal predictions, it's limiting. So the other extreme is joint future prediction, right? So you say, oh, I'm just going to have the full probability table over all agents, right? So it's exponentially big, but now I can present everything because I have a separate entry for every possible, say for two agents, every possible outcome for the pair, which is great. I can represent maybe there's no collision there. Now the issue is what happens when the agents blow up. Actually, this output was adopted by Sync Transformer. They just handled it in a particular way. They said, okay, you have 6 futures total for the whole world, no matter how many agents. That's very limiting. I mean, you have 100 agents. If you just say 6 joint futures, that's not great. Now, how do we treat this space in a more principled way? So here comes another paper, joint future prediction, at this conference. Please check it out later. I think it will be in a poster. This is a deep network that does pairwise graphical models CoRL head. And so it captures factor joint interactions between multiple agents. So let's say here's the agents in the scene. We're going to impose an interaction graph on them. So in this case, just maybe 4 agents and a fully connected graph as an example. Then given this, we first would predict a set of marginal trajectories for every agent. These are roughly generally the outputs you expect for each agent. But this doesn't capture yet the interactions. And so then given the graph, you also form pairwise potentials. And the pairwise potentials capture the pairwise table of interactions between these marginal predictions. So essentially now you can start maximizing the likelihood. You can start to maximize the likelihood over the whole joint representation. And you can backprop it through this model and through the network and learn yourself both the features and the properties of the head predictor layers that model the joint distribution represented in this way. And so that's quite powerful because you can now actually what you can do is now the question is what is the graph? You can shift between sparse and dense graphs and study what happens. So you can have no graph, that's just the marginals, no pairwise relations. You can have the fully connected graph, which is all pairs of agents interacting. And then you can need to do loopy belief propagation. It's approximate if you want to do inference in that model, right? And then you have in between options like star graph, which has exact inference, and you can backrope in that easily. And typically, when you do a star graph, you want to center it on the AV because we have an AV-centric objective. We want to drive relative to all the others. We want to model our relationships with the others. So if you have to pick something, that's very natural. And then we have a dynamic graph too, which is it's incremental construction within the model. So if you predict the marginals for every agent, you can check what marginals overlap with others. And if marginals overlap in spacetime, they could be interacting, and then you can have a pairwise potential. So you can have a dynamic interaction graph as well. And so, of course, you can see here, this is the most expensive, and these also start becoming more approximate inference, more dependent on number of agents in the scene and so on. And here it's, of course, goes all the way to no interactions. So let's see, will this move? I'm clicking things. Okay, let's see. There we go. And so before we go ahead more, let's talk briefly about the metrics. So there is this metric called minimum average displacement error. Essentially, it's a metric adapted for multiple outcomes for an agent. So if the agent is stochastic, you give it a budget of, say, 3 or 6 guesses, and then you check how far is the nearest guess. So that's one fairly permissive way to still capture multimodality metric. And here we will show some result with a metric called joint lineage, where you essentially take the minimum outside and you say for some set of interactive agents, in our case, typically 2, otherwise things also blow up. You just take pairs of their futures and you check out of K guesses for the pairs, what's the pair that's closest. So you can't cheat there, you need to match both at the same time. And what happens? So in this joint lineage metric, you can see that these intermediate graphs, especially the star AV-centered star graph or the dynamic graph, do significantly better in pairwise prediction. This is actually our interaction challenge. We launched it specifically to push people to move beyond just marginal predictions. So check it out if you want, but it's a good way to measure how well you model interactions. And what's interesting is actually fully connected does pretty bad. And that can be many explanations, but it's tied to too many pairwise potentials, approximate inference that may or may not converge in all cases well. So there's a happy medium there that's significantly better than the default, which is the great part. And here is another metric, which is predicted overlap with the autonomous vehicle. So this is how often you have some agent overlapping your path. And of course, the scenes we have, no one hit you, so this should be 0 in theory. So lower is better. And these two models, again, do significantly better than the default, which is just marginal predictions, which is great. And last but not least, we beat the state of the art in our own interaction challenge with this work, which is not a bad thing. This is the JFT work, and it compares to Scene Transformer, which is a past work. And we had a challenge, some challenge winners from a couple of years ago. So, so that's what I wanted to say about behavior prediction models. Now let's move to agents, and I'll start with simulated agents. I think it's a bit easier to tie in the story. So, you know, simulation is an essential tool for testing how a driver handles complex scenarios, ones that you may not even want to put on the road. Also, simulation is key for validating releases in a consistent way because you can keep replaying the same scenarios. But utility of the simulator depends largely how realistic it is. So that's why we're working on building the most experienced simulator, if we can. And try we do. Now, when you think of simulator realism, a key challenge is modeling the other road users. It's not only about sensor realism, it's actually the fidelity of behaviors is highly important. And I'll show you my favorite example. If you've seen talks of mine, you've seen this before. So you have, only maybe not this way, right? So you have the sign agent, which is the position of our driver in simulation. Green was the position of the agent when it collected this scenario. And you have this obnoxious purple agent that plows straight into us because when the scenario was collected, that of course was empty space. And so we were not there, now we're there in simulation. You cannot just replay the logs and hope the outcomes are realistic, you can get with highly unrealistic collisions. Of course, those are not helpful whatsoever. And so to do better, you need agents that react realistically. And this requires closed loop control policies, which we can learn from demonstration real world data. And so to this end, we published a work this year called Symphony, Learning Realistic and Diverse Agent for Autonomous Driving Simulation. And at the core of this Symphony work, it's an imitation learning approach for agents. So at its core, it has a standard learning from demonstration algorithm. It could be behavior cloning or MGAL, but we augment it with two additions. One of them is parallel beam search, which refines the policies on the fly by pruning states that look unrealistic based for the agents using a trained discriminator. And second, we also add a hierarchical policy model, which helps produce diverse outcomes. And I'll show this just in a couple of slides in more detail. So how does this parallel beam search work? So you start at the time when the agents when you start applying a rolling policy out for the agents. So you generate an action for all agents by some policy that you learned with BC or MGAL. And then you can prune branches with higher scores of unrealism based on a discriminator. And then as you prune some, you can resample others, maintaining a certain set of diverse outcomes. And then you roll this out for as long as you want to play with scenarios. Right? And this, of course, helps. So if you do this, your collision rate and off-road time you go off-road decreases significantly compared to the baseline. But actually, it hurts diversity of the outcomes. And we introduced this metric called curvature Jensen-Shannon divergence that captures that. So what is this curvature Jensen-Shannon divergence? Essentially, you look at this data set of log behavior in blue and agent behaviors reproduced by a policy. And you see how often you drove straight mostly or right, left at various angles. And so it makes a histogram of these arcs and their shapes. It turns out that, say in this case, the agent preferred driving straight a lot more, but is undersampling right turns and left turns. So how do we recover the diversity? And that's where hierarchy comes in. So we have two models. So first, there's a goal generating policy. At the moment you want to let the agents go, you produce essentially a route for every agent given a model, and that route is held fixed. And the route is essentially a collection of road graph segments. So it's some geometry that you want to follow long term. Then conditioning on this route, the policy executes the steps trying to follow the route and of course maintain realism and so on. And so what that happens to do is it helps with the diversity because you can sample routes realistically matching the true distribution. And it does happen to fix the curvature JFD. So now you get basically the best of both worlds when you combine these two additions to the pure imitation learning approach. And here's some examples. So in red is like the baseline agent without research and hierarchy. And this is probably, I think it's behavior cloned agents in red. And they just both plow ahead into each other, while in the other case, the agent on the top yields until the relevant other agents cross the intersection and all the resume. Here is another example. So again, red agent is the baseline non-symphony agent, and it goes in some wild sojourn plowing into vehicles. But in Symphony, again, the interaction is realistic, and one of the agents waits for the other to pass. Let's move on to planning agents. So this is a work from IROS, and it essentially follows up on the previous work. So this is essentially us exploring how far can you go with an imitative agent for planning. And so the idea is exactly like the agent I showed you, the hierarchical MGAL agent. So you pick a route, and then you condition on this route, and you train an MGAL policy for the agent, right, in closed loop. And that ultimately is applied for the duration of the rollout, right? This MDL policy, ultimately, our model, the conditional part of the model is trained with two losses. One is behavior cloning, and one is the MGL loss, which is closed loop loss. You're rolling out futures and scoring them with the discriminator and back propagating through the motion model, which is differentiable to learn behaviors robust to closed loop. And so theory predicts that adding this MGL loss will yield benefits, and we affirm this now in practice experimentally, right? But first I'll show you an example. So this is planning agent trained with behavior cloning. So you still have a route and condition on it, but then you train just predictions to be close every step. And so you get stuck in this narrow example and we cannot proceed. In contrast, our agent that combines MGL and BC losses successfully proceeds through this fairly complex narrow area and continues on its way. So we evaluate these policies with logged agents and conditioning on the expert followed route. So whatever the expert followed in the demonstration, we condition on that and see how well they'll execute this. And we measure here the policy success rate. So success rate is if you didn't collide and you did not go off-road ultimately in these scenarios. And you can see that our best policy that combines MGL and behavior cloning significantly dominates behavior cloning and slightly dominates MGL. However, I mean, there's a bit of an issue evaluating this policy on the same goals achieved by the expert. This could be overly optimistic performance estimate because there could be spurious correlations you're not discovering. Ultimately, you're getting a lot of hints based on the route and following exactly the log behavior of agents. This, for example, cannot tell you, oh, you know, can it follow if I gave it another route? Could it follow it or not? Okay. So that's exactly what we started testing. It says here is we're testing it with a route passing across the intersection while the expert policy turned on the right. So this is one example. And of course, when you do these things, you also want to turn on interactive agents. So now we're testing on novel routes with interactive agents. And you can see here, the gap is significantly bigger, right? So it shows that this BC plus Gale combination has significantly better generalization ability, and that there is still some gap between novel routes and the expert route a little bit still. But overall, yields quite well-performing agents. We also continued the studies of our model further, which led to a paper in this conference. So this is a short spotlight. I encourage you to go attend it in December 18th and learn more from the direct author, Ellie. Essentially, the question we ask ourselves is, okay, so how do these models perform at the range of examples? Easy, medium, or very hard, right? How do these policies compare on those? Well, where do you get these labels for the examples? Well, you could just label them manually, but what we also did is on separate data, we trained the classifier, and this classifier is trained so that data contains undesirable outcomes where, say, the expert resulted in close to collision and or close to off-roading. And so we trained to classify those. And so we produced this classifier, and now given this classifier, how can you use it effectively? It essentially tells you what are the difficult examples, the ones that are likely to not succeed. And turns out in this paper that just with 10% of the examples and the appropriate, using the classifier outcomes appropriately, we can significantly improve the performance of the model. So you can move from, even with 10% of that, you can move from a baseline of over 3% and a quarter failure rate to below 3. And you can also furthermore do it across all, you can beat the baseline across all the bins of difficulty with certain schedules that we pick. So to learn more, please refer to the spotlight. I will talk one last thing, which is work from NeurIP's autonomous driving workshop we presented a couple of weeks ago, which explores the relationships between imitation learning and reinforcement learning. And so this method is built on the intuition of this work explores the intuition that imitation and reinforcement learning offer complementary strengths, where, I mean, imitation increases realism and ultimately removes the need for complex reward design. But reinforcement learning can improve robustness, especially in the more data low regimes, right? Because there would be fewer examples there to imitate. And so in this approach, we combine the benefits of both imitation and reinforcement learning by crafting laws that combines them. Right? And so how does this work? On examples in distribution, we apply two losses, reinforcement learning loss and imitation loss. And on examples out of distribution, we apply reinforcement learning, like storyboard loss. And ultimately, the way this is implemented, we call this simple method VC-SAC. And it's a modification of software critic where we add an imitation term for the examples that are in distribution. And reward function is kept very simple. It's just there is a penalty for collision and off-road in the outcomes. And so what happens? I think you can see here, this is again results, this is familiar from the spotlight. These are examples ordered by difficulty. This is the most difficult ones. And you can have this SAC is in orange here. And you can see that it, on the more difficult spectrum of examples, it's more robust than the MDL agent, which we just talked about. It's purely imitative for behavior cloning. And those particularly tend to do badly at the top 1% of difficult examples. And VC-SAC is stronger there. Now to dive in slightly more into the results. So when we train with all the training data, you can see that in this is evaluating top 1% hardest, top 10% hardest, top 50% hardest. VC-SAC typically performs, has a lower failure rate. Yeah. But MDL beats it when you take into account the bottom 50% easiest examples still, because there we have a lot more examples as classified as difficult model. And if you take just the top 1% difficult examples and train the model, this is essentially the low data regime where you have a lot less training data. Now, the imitation term, of course, becomes a lot less effective. At this point in the low data regime, reinforcement learning looks a lot more desirable. Now it's better across all ranges, but that wasn't exactly true as the data sets go. And so maybe a little bit of intuition here. So that is MGAL, comes quite close to a vehicle where a pedestrian just exits, which is not optimal. And here, VC-SAC provides additional clearance around. By the way, some of this robustness, just want to point out, comes at the cost of progress. So it may be more robust, but the progress is significantly less. All right. And there is even on top some cost of progress. And you can see some of this. It learns to be more cautious and drives around some of the more problematic cases, as opposed to staying in lane here. And there is a vehicle sticking out and it tries to brake, almost succeeds, but not quite. That's MGAL. And here it's early on mitigates it by changing lanes to the right. And so there's still a lot of interesting things to explore at the intersection of imitation learning and reinforcement learning. You guys may be familiar with the Waymo Open Data Set. We have provided at least some data for imitation learning. That's 100,000 scenarios of interactive examples that we released. And so, and of course, this data set has a bunch of other things. We keep improving it and evolving it. Please check in occasionally to see what else we put in, but I think it enables research of the kind I just showed, and more. And so that was my talk. Thank you very much for attending. And if you want to see a lot more of our papers, first, we have 4 papers at this CoRL, so please check them out. Second, at waymo.com research is a lot more of our papers. Things that we have explored that I did not have time to present today. Please encourage you to check it out. Thank you.
Thank you so much, Jakob. That's a very, very interesting talk. We're a little behind on time, so we have time, maybe 2-3 questions, and then we'll move on. All right.
Yeah, thank you for a very interesting talk. You presented some method for prediction and then for planning, but I'm curious, what is the relationship between the two? Like how much your improvement on prediction will improve the planning?
So I would say that, I mean, this we did not directly study, right? So here we studied aspects of the problem. We did not study, for example, what's the best way to integrate prediction with planning. I think this type of model, like George Fitch's prediction, is interesting. I think generally I would say that aggressive enough planner or assertive enough planner needs to be able to model not only marginals, but also reactions to the plans you do. So you need to build one that has this property, right? JFP is maybe one way to think about doing something like it, but this we have not covered, right? I think that's still to be explored academically and potentially, I mean, in industry, everyone has their own solutions.
My question is maybe not directly related to this work, but when you started presenting the earlier slides about your achievements, how you're implementing actually autonomous cars on the roads, I remembered that I mean, back in the day there were issues with night vision and bad weather vision, and the video, for instance, one of them showed the car driving very well at night among those baseball fans. How do you deal with that right now, with these issues?
So, I mean, there is a ton of interesting problems to solve, especially in the production system, right? I have not touched on the majority of them in this talk. I think when we do research, we try to abstract the experimental setup to something that really validates and shows the gist of these approaches and how they compare. I think generally, right, like you need to do, I mean, weather poses a lot of challenges. A lot of them are on perception, but also on behavior, right? For me to comment further, I think goes beyond research that we have published. But I think a lot of this works ultimately need to inform a larger system, right? So they're just design studies of some kind, putting it all together in a coherent way and mitigating all the, I mean, whether, you know, you can call it emergency vehicles, gestures by people, guiding you. There is a very large amount of features that the system needs to have. And it's hard to provide research that studies all of it. So, you know, yes, the Waymo driver handles it, and we have a large team, and we're hoping with our research to inform certain decisions, but ultimately it's really a lot of the key work is into building a coherent system out of it.
So I have a question about the kind of combination of imitation learning and then reinforcement learning when you get to out of distribution situations. It seems to me that, you know, I guess, so your kind of solution that you presented, as I understood it, was we, you know, do imitation learning while we're in distribution and then reinforcement learning once we go out of distribution. But in order to do that, you still have to have a transition model that your RL agent was trained on. So like, to me, is it just pushing it down the road a little bit? Like, or is there something special that I'm missing? Like, because it's still kind of in distribution.
So in distribution in this case means, I mean, you have the exact example and there is, you know, exactly in this step what the agent did. So train with it and force the model to always give you that with high likelihood, right? That's one version about distribution. The truth is there's still the room to explore, because I showed combinations like BC and say rewards, right? And I showed combination of BC and MGale. I did not show BC and MGale and rewards, how to trade all of these things, right? So there's more to do. I think generally one thing when you think, where do you get your policy CoRL in the first place? Well, in our case, when you have imitation data, you can very happily pre-train, and it's a very good policy initialization, right? So then you need to just fine tune it, practically speaking. You don't need to start from scratch, right? And I think that's not a challenge we have. We have the data to bootstrap ourselves just fine.
Well, I guess maybe take this example, like, so I guess in the model that the reinforcement learning agent was trained on, does it have people getting out of cars suddenly? Like
yeah, it would have the same type of data as we trained it on. I mean, ultimately, a lot of these examples that I showed, they're produced by a perception system.
Yeah.
Right. So as you drive through the scene, it reconstructs the scene as you went through it. And we do the best job we can out of this automatically. And those reconstructions will have pedestrian camera with the car just fine, right? So it's not just something that occurred that you could never have seen.
Okay. So I guess the advantage of reinforcement learning is that it generalizes better, because you're generalizing, like, you don't have to have an exact combination of all of the things
it's
seen
helpful
in your
with,
data.
Disentangle causality, and also ultimately, right, in a pure imitation approach, you hope not to discriminate or to just match states. Here, when I define just two simple rewards, but I very explicitly said, don't do these two things. That's very key information that you can use.
Yeah.
Right. So it's complementary in the next one. Now, the challenge is once you have 100 rewards, how do you trade them all? How do you mix this with the discriminator, right? But at least up to a point, some rewards are very straightforward and they belong there, right? I believe.
Got it.
So on a similar note, you drew this nice curve, right, where you have one domain, imitation learning dominates, and as you come down into this long tail, you find that reinforcement learning is more robust in these kind of very low data regimes. You keep going, right? The old school way of trajectory optimization requires no data, right? But I got to know, is trajectory optimization dead?
It's not necessarily that. It's one market need. Actually, trajectory optimization is one reasonable way to define a set of costs, and they preserve ultimately physical trajectory in ways that some of these rewards don't, right? So they're actually complementary in some way. I mean, you can think of that as another way to define the rewards. Sure. And you can backprop for that. There is a lot of things, right? So now it's up to the system designer to study this, hopefully with more benchmarks. These things can be explored. We don't have to just have those two rewards.
Nice. Well, I think we're behind on time, so we're gonna cut it there. Drago, let's give him another round of applause for a great talk. Thank you. Look forward to catching your papers. All right. Oh yeah, okay. So for our last final session of the day, we have two contributed talks, maybe a third, three contributed talks. I'm going to go to this mic. Hopefully, yep, no feedback there. Okay. So up first, we're going to hear from Donkey Kim on game theoretic perspectives on active equilibria, preferred solution concept over Nash equilibria. So, Dong, if you are in the chat, in the Zoom call or in the room.
I'm in Zoom call now.
Okay, wonderful. All right, take it away.
Thank you so much. Let me share the screen. Can you guys see my screen?
Yep, we can see.
Perfect. Let me hide. Okay, so let me begin and talk. There's a time I have to. All right, let me begin. So hello guys, how are you? Thank you so much for attending this talk and listening to this presentation. My name is Donggi, I'm from MIT. I'm today here to give a talk about game theoretical perspective on active equilibria, a preferred solution concept over Nash equilibria. So one of the main challenge in the multi-agent reinforced learning is so-called non-stationarity, which says it is not easy to learn optimal poses due to the presence of non-station poses of other simultaneous learning agents. I'd like to give some example about this. So let's say we're playing the iterative rock, paper, scissors. On the top, you see the agent policy. It turns out that it's initialized to play the paper the most. And we have the opponent, and it turns out that the opponent is playing the rock blank. And because paper wins rock, me as an agent is happy. So I maintain my policy in playing the second game. But it turns out that this is not a good policy to do. It's because the opponent changed its policy from rock to scissors. And that is because opponent is also a learning agent, is also a smart agent. What it means is that the agent receives the negative reward in playing the second game because the agent failed to consider the opponent's non-station behavior. What this is telling us is that it is important for us to consider non-stationarity. So in the further paper, which is our recent nearest paper, what we did was that we have the further framework, which considers the learning dynamics of the other agents and trying to influence their future poses toward desired behavior from its perspective. I'd like to give an example about this. On the below, we see a payoff table playing Bauer-Stravinsky. On the right, we see the learning dynamics playing this game. It turns out that there are two Nash equilibria for this game. The first one corresponds to A, receiving 2 for agent I, 1 for agent J. There is the other pure Nash equilibrium where there's B, B equilibrium where the agent I is getting 1 and agent J is getting 2. So there are two Nash equilibria. And what further agent is trying to do is that even though the joint policy has initialized on this side, the further agent is trying to influence the other agent's learning dynamics so that they can converge onto the A, equilibrium, which is better from its perspective. If it turns out that if every agent is trying to do this, in a sense that if every agent is trying to maximize its long-term rewards by influencing the joint converged policies, we show in the paper that this resulting multi-agent system can reach to a new solution concept, so-called active equilibrium. And in the paper, we show that this solution concept is general, such that the standard Nash equilibrium corresponds to the special case of the active equilibrium. But it is unsure that the benefit, even though the active equilibrium is general compared to Nash equilibrium, the benefits of active equilibrium is unsure. So the objective of this workshop paper is to take the initial step of understanding these benefits of active equilibria compared to Nash equilibria. And we should try to show this based on some example games, including the personal dilemma, which has a social dilemma aspect, Bauer-Stravinsky that has the multiple equilibria aspect, and the periodic game, which has the inherent non-stationarity in terms of the environment. The main contribution of this workshop paper, what we show is that if the game structure has social dilemma property, multiple equilibria, or highlights non-stationarity, then active equilibria can perform better than Nash equilibria is the main contribution. And because this paper talks about active equilibria, which is fairly new concept, I'd like to give some background what it means by the active equilibrium here. So our problem statement is actually based on the active Markov game. As you see, is the active based on Markov game. And let me first describe what Markov game is. So Markov game is describing is how the joint action, as a notation-wise, is the agent I's action and the other agent's action, and altogether is a joint action. And Markov game is describing how the joint action is affecting the environment based on the state dynamics of moving next state, also next state to the on and on. What active Markov game does is extending the Markov game by considering that the joint coming from the policy, where policy is parameterized by the data IP, And similar to how the state is transitioning, the agent I policy parameters are updated according to the update function of UI, going from the current policy parameters to the next policy parameters according to the transition. The important part here is a joint update function is a function of the agent I's action, which affects state transitions and rewards. So what this means is that agent I can actively influence future pulses by changing its own behavior. So this active Markov game is capturing the active influence aspect. And since this active Markov game is new, a lot of question has been where do systems converge onto, and they correspond to they converge onto the activity equilibrium. To define activity equilibrium, there are some set of questions we want to answer: how to characterize convergent behaviors based on station K-periodic distribution. We also describe what's the desired objective, which is based on active average or objective, and also lastly, what's the solution concept, which corresponds to activity equilibrium. So we define this station K-periodic distribution, which is a station distribution over the state and the data with respect to period K, and this satisfies the property that if we compute the time average expectation starting from R, this corresponds to the same expectation if we start from the next element, which corresponds to R plus 1. But the point here is that this periodic distribution can generalize from station fixed point convergence, meaning the Nash equilibrium, to potentially fully non-station convergence. And we can use this to compute, to define the objective, which can be defined as the active average or objective, where each agent is trying to find the optimal policy parameters and optimal update function that maximize its average reward, where we can use the station K per distribution here, and this actually corresponds to the average reward formulation, where each agent is considering its average reward while accounting for the converged pulses as the time goes to infinity. And if it turns out if everyone does that, in a sense that we can find the active equilibrium where there is a joint policy parameters with associated updated function where no agent can further optimize their average reward. In the paper, we show that active equilibrium is general, such that the Nash equilibrium corresponds to the subset of the active equilibrium. So we show that active equilibrium is general, but generality should come with a cost. And the people may wonder when is active equilibrium may have find a better solution concept than Nash equilibrium, and try to show this based on those games: Persian dilemma, Bar-Starvitsky, and a period game. So let me first begin with the Persian dilemma. So let's say we consider playing the finite repeated game of Persian dilemma where the horizon given is as a 2. It's known that in this finite repeated game, the only Nash equilibrium is the mutual defection, where at any time set t, the joint action is to do defection. But we can actually find the mutual cooperation based on active equilibrium. It turns out that if we find the initial policy beginning from CC, and if the update function for each agent is capturing the following, then we can actually find the mutual cooperation, where the active equilibrium actually include T-periodic strategy in the update function, where deviation parity is embedded in the joint update function, so the active equilibrium can achieve mutual cooperation in this social dilemma game. Similarly, in a Bauer-Stern-Bisky, we see that in a Nash equilibrium are deficient in a such that the pure solution concept of conversion B, B or S, S is unfair in a sense that only one agent is consistently doing better than the other agent. And the mixed solution is inefficient as the all player receives the lower reward than doing the pure solution concept. But in terms of the active equilibrium, what we find is that the following solution of the active equilibrium is actually can find more efficient Nash equilibrium where we can achieve 1.5 as average reward. So what this implies is that we can actually find much better reward compared to the Nash equilibrium. We also note that we achieve the same performance as a CoRL equilibrium, but without needing the mediator, but based on the independent action choice in the active equilibrium. The last part is the periodic game, such as if you assume the period K is 2, such that in the odd time step, the even time step, the payoff tables are iterating. What this implies, the periodic game is implying is that the environment itself is non-stationarity, is what the periodic game is implying. In this periodic game, we also find that Nash equilibria achieve the suboptimal performance, but achieving the 1.5, 1.5. But in the active equilibrium, because active equilibrium can actually consider non-stationary dynamics post-convergence based on the update function, we found that active equilibrium can achieve a higher reward compared to the Nash equilibrium. In a sense that the learning of non-stationary equilibrium, as in the active equilibrium, has benefit over stationary equilibrium when game itself is non-stationary. So to conclude this paper, yes, this is the last slide. So to conclude, what this paper does is we try to close a gap in understanding the benefits of active equilibria compared to Nash equilibria is the main contribution of this paper. And there are more details in the paper, and thanks for listening.
Wonderful. Thank you so much. It's a very interesting concept. So for those of you new this afternoon, the way that we do this is we'll do our questions at the end of this 3-paper session. So now we'd like to ask Tyler Becker to present the paper Imperfect Information Games and Counterfactual Regret Minimization in Space Domain Awareness.
All right. Can everybody hear me? See my screen?
Yep.
Excellent. All right. Yeah. So I'm working on game theoretic sensor tasking with my advisor, Zachary Sundberg. So as a quick motivation, suppose we wanted to maintain custody of some maneuvering spacecraft. What people have done and what you could do is use some predictive model of what the opposing satellite could do and then keep a running state estimate of it. So the question then is, how do we model the opponent's maneuvering strategy? And then the following question there is, what happens if we're wrong about the opponent's strategy? As a motivating example, we could say there's some intruding satellite in a circular orbit around Earth, and it's tasked with surreptitiously making some maneuver. On the other hand, we have a ground station with a limited scanning budget that's tasked with catching the satellite as it makes a maneuver. Ground station gets positive reward for catching the satellite. Satellite gets a positive reward for making a maneuver without being caught, and this is zero sum. And so if we consider this kind of cardiotic reward structure, where at 0 degrees in this orbit, the satellite gets 0 reward for not being caught and making a maneuver, and at 180 degrees, we get satellite gets a lot of reward for making a maneuver and not being caught. And so a reasonable deterministic strategy, if we were to go by deterministic strategies, would be for the ground station to just cover all the high value zones as much as possible. And that's the strategy you get here. And the question then is, what's the worst that could happen? And of course, the satellite could then counter the strategy by some purely exploitative strategy, that is to make maneuvers in all regions that are not covered by the ground station. And the question is, how do we account for the possible responses of the satellite? And that is with game theory, of course. And so we can formulate it as an extensive form imperfect information game and solve it with counterfactual regret minimization. We're an extensive form game essentially here, where we just have an extensive form game of rock, paper, scissors, where player 1 starts in this first information state, and then player 2, despite it being sequential, now has to reason about all possible actions that player 1 could have taken. And counterfactual regret minimization is essentially just repeatedly playing actions with a probability that's proportional to the regret and not having played that prior. And then the average of these strategies is what converges to a Nash equilibrium. And so if we do that, we can get the strategy on the right, where the length of these bars, the length of the blue bars indicates the probability that a ground station will scan in a certain region. Red is the probability that the satellite makes a maneuver in that region. And you can see, if we move away from deterministic strategies, we can effectively spread a budget, a limited budget, over a larger region via some probabilistic spreading, if you will. And so we can compare the performance of these two strategies, where on the y-axis, we have the satellite score, which is roughly proportional to the amount of times it gets away with a maneuver via a maximally exploitative strategy. We can see that reasonably with this pure strategy at around a budget of 9 or 10 scans, it essentially fills up the entire orbit, and it's a trivial solution, in which case the satellite is unable to make maneuvers anymore. But we can cut the budget required to drop the satellite score down to 0 in half, where we only require about 5 budgeted sensor observations to be able to push the incentive of the satellite making any maneuvers down to 0 entirely, because we're doing this probabilistic spreading over the entire space. And so ideally what we want here is we want to scale to larger problems that are less proof of concept-y. And so the ideal way to do this, you would think, is to use neural networks and go to deep counterfactual regret minimization, where as opposed to tabulating everything, you're maintaining a neural network that's mapping information states I to regrets and information states I to corresponding regret matching strategies. And the allure here is that we could use Monte Carlo counterfactual regret methods, where we have this game tree on the right, where you take Monte Carlo samples throughout the tree. Once you are finished with these samples, then you can do typical Monte Carlo. You can do counterfactual regret minimization over these sampled nodes. But the problem then, of course, is that you're only updating the nodes that you've visited via this Monte Carlo sampling routine. And so ideally, you'd be able to update more. And if your tree is larger and larger, and given that we're trying to expand the size of these games, you're only going to be visiting small subsections of the tree. And so the allure of deep CFR, of course, is then that despite sampling a small subset of this tree, you can regress over the regrets that you've received and the strategies that you received over here. And via this regression, you can extend what you've learned of the visited nodes to the nodes that you've never visited. And so ideally, theoretically, it should be more sample efficient. But of course, it doesn't come up without its problems, where now, as opposed to something that would take on the order of microseconds at each iteration, now takes minutes, and that's being generous, where we now have to train neural networks from scratch to be able to regress over these regrets. And it works reasonably well for small network sizes. So for 20 neurons, we can see that our convergence metric in this case is exploitability drops reasonably low, but because it's not terribly expressive, it doesn't go any lower. But immediately as we go to a hidden layer size of 32 neurons, given all other hyperparameters the same, it's completely non-convergent. And so we can diagnose this. We can look at the loss function and say that it's a weighted quadratic, and we can solve it manually at each step, and we can get a relative loss of the neural network. And this is purely for diagnosing the problems. And if we plot this this hypothetical lower limit on the loss, we can see that, okay, if we have a network that is sufficiently expressive and we train it for long enough, then of course we're going to hit that lower limit. But given that we're training these networks multiple times over, thousands of times over, we want to be able to do that with as small a network as possible and training for as few iterations as possible. And so with this, this new convergence metric, we can either cut things early, cut the training early if we've hit the convergence metric early, or cut things early if we know it's never going to converge and the network is insufficiently expressive. You can see that if this relative fitting error is low throughout all training iterations, then we can see exploitability does indeed drop to 0. But on top of that, we want to scale to larger games. Deep CFR necessitates what's called external sampling, where me as the tree traverser, I want to expand all of my actions. But I randomly sample from the opponent's actions. And given this exhaustive sampling of my actions, the number of network queries is now exponential in the depth of the tree. The reasonable way to go forward there is to use outcome sampling. With outcome sampling, we randomly sample from both my actions and both the opponent's actions. And now the network queries that we have is linear in the depth. And given that we're working linear in the depth, now the time required to complete these operations, given the game depth for outcome sampling, roughly linear, external sampling, large increase, exponential increase in time. But of course, by no free lunch theorem, we're receiving sparser samples, and therefore they are higher variance. And deep CFR was already unstable. Now with these higher variance samples, it is extremely unstable. And so how do we reduce variance? We go to baseline variance reduction, where now, as opposed to just taking these raw Monte Carlo samples, we are bootstrapping subsequent Monte Carlo samples with previously found value estimates. And we can see on the right that this does have a statistically significant effect on the exploitability versus time, where the solid lines are the non-bootstrap methods and the dashed lines are the bootstrap methods. And so now, given that we have this this method that's amenable to larger games, we can extend it to what we call the orbit change game. Where in the orbit change game now, a satellite starts in a circular orbit around Earth. Its goal is to reach some desired orbital parameters. And now, as opposed to just moving through discrete zones in the sky, it can move through a continuous space. And now the goal of the ground station is to determine the goal region of the satellite by intermittently querying its position, again, given a fixed budget. And so we can see
we're gonna have to ask you to wrap up.
Oh, sure. Okay. Yeah. So this is what the stochastic strategy of the satellite looks like. On the right, we have how it performs relative to a best response. And we can see that the best response is performing poorer and poorer, meaning that we've achieved a Nash equilibrium. Finally, as the last steps where we want to extend this, we want to push this to larger games, continuous games, in which case we're using PPO. And ideally, we want to fix the whole problem, which is a state estimate, but that's difficult in games. And so the idea currently is to put state estimation into the action space. Thank you.
Thank you very much. Very interesting. All righty. So we have one last talk. Danny, I see you in the chat. If you would like to quickly run through your talk from earlier,
Cool.
I'd love to have you.
Gonna share my screen. 1 second.
We're gonna have to keep this to a really strict time window here because we're now actually...
Yeah, absolutely. So yep, our project is Dominion, and we propose this as a new frontier for AI research. So games have been a substantial thing in AI. For example, Deep Blue, AlphaGo, and state-of-the-art in Texas Hold'em. And the really important thing is that these games have served as a test bed to push boundaries of AI research, as well as understand how agents might potentially cooperate in multi-agent games. So I'm going to tell you a little bit about Dominion. So to continue this tradition, we examined the tabletop game Dominion. And basically, it's a game that has 350 cards and 10 are randomly selected. And the objective is to own the most victory points. And there are certain phases during each turn where a player either plays actions or makes decisions to buy further cards. And the game ends once 3 piles run out or the province victory card pile runs out. Okay, so why is Dominion interesting to study? So each game is different. There are a lot of different 350, choose 10 possible different games. And so the key part of playing Dominion is adapting one's inductive bias of how to play the specific cards on the table. It has a small state space, so unlike other games like Atari, where each pixel is a dimension, Dominion usually has 17 to 25 different cards that are only in a few different positions. And each game is relatively short, consisting of 15 to 40 turns with less than 100 decisions per game. So this gives the opportunity to solve interesting problems and study these multi-agent interactions without having high computational resource requirements entailed by other games. So Dominion has a large community, and one of the most popular ways to play Dominion, especially during COVID, is the Dominion online web server. The developers have saved 2 million game logs, which you can see what it looks like on the right. And other than the usefulness of this data for training agents, we can also get some higher level statistics about the game to further drive insight on potential strategies. So Dominion fundamentally has 2 phases, an action phase and a buy phase. And our work focuses on implementing the buy phase. So in 2014, Matthew Fisher proposed a representation that enables one to specify their buy policy into a compact heuristic. He dubbed this as the buy menu. And essentially, it's an ordered list of tuples that specify which cards you should buy and the amount you should buy them in. And this was such a useful heuristic that we were able to cast most of the best known heuristic bots in terms of a buy menu. So yeah, in order, and so the question then becomes, well, how do we learn the best by menu policy? And Matthew Fisher proposes provincial, which is a coevolution algorithm that consistently mutates its by menu to develop better and better policies. So in addition to the data that we provide, we also take in a code base written by this person named Benzix, and we massage it to be able to define agents, specify policies, and basically simulate the game. And we implement a simple RL-based buyer bot using Rainbow DQN. And yeah, it takes in a game state representation, asks an action mask, and returns which card to game. So this table below shows that our bot essentially beats the existing state-of-the-art, which was provincial, as well as a plethora of proposed heuristics based off the strategies that people have tried. And our intention with this bot is not to break new ground in the field of RL, but we want to show that recent developments in RL can easily outpace the current state-of-the-art in Dominion. Cool. I wanted to keep this under 5 minutes, and it seems like I'm on track. So as far as future work goes, we only learn the buy policy, but we want to also learn an action policy. And we want to do further analysis on the game logs from the games that we talked about earlier. And we also want to train a state-of-the-art agent to see if they actually can beat the top Dominion players. Thank you.
Thank you, Danny. I appreciate you keeping it brief.
Yep.
Interesting work. Luckily, I got to read your paper.
Cool. Cool. Thank you. Appreciate it.
So I think we have, I know we're over, so we'll see if there's any burning questions that folks want to ask.
Maybe 2 questions?
Yeah, 2 quick questions. If not, then we can turn it over to Zach to give a quick closing remark, and then we'll be on our way to dinner.
All right. So first of all, thanks everyone for coming to our workshop. Let me see if I can.
And thanks for sticking around.
Sure. Yeah, thanks for sticking around till the end. We really appreciate it. I'll just share a few of my takeaways and summary thoughts, and then we can get off to lunch or dinner. I thought these were kind of the takeaways that I got out of today. So first of all, there's a lot of factors in our game structures that are really important, like information structure, play order, the frequency, partial observability, which equilibrium concept you use. These are all super important to choose correctly because they'll affect the outcome of the game. We also saw that modeling interaction is important in a lot of real world problems, from space domain awareness to autonomous driving. And we got some strong evidence that this is something that we should keep looking into. Game theoretic formulations can yield really complex interactive behaviors. So we saw like some cool demonstrations of like blocking in racing games, and different complex behavior that can emerge from actually really simple problem formulations. And then one thing that was surprising to me is how useful, and this is kind of a optimistic, I guess, outlook, is like how useful resolving ambiguity through things like rules and natural language communication and collaboration are useful in a surprisingly wide range of settings. So even in, I think the diplomacy, zero-sum game setting, or where there are winners and losers, like you don't often want to deceive your opponents. You usually want to kind of collaborate and be truthful. And then the final thing that I was kind of striking to me is the diversity in the different approaches. So there's very little overlap between the approaches that people gave in the talks. So I thought that was kind of cool. And also diversity in applications. We had, like societal level machine learning algorithms, all the way to kind of space domain awareness, air traffic planning, autonomous driving, racing, and natural language processing. And then I thought of a few maybe things that we should think about moving forward based on these talks. So one is that, with the diversity of approaches, there also becomes the challenge of communicating between different ways of looking at things. So there are a lot of different formulations and a lot of kind of differing language on how we talk about those. So if we can come up with unified ways to talk about these things and build off each other's work, I think that'll be good. The second thing that I saw that we should work on moving forward, I think, is bridging the gap between theory and real applications. So we had a few talks that were very focused on kind of realistic applications, and then we had a lot of very theoretical talks that kind of worked on small kind of toy problems. But I think there's still a big gap to close between those two. And then finally, we've talked a lot today about rational agents, but in the real world, like you almost never know the reward functions, the utility functions. So we have to be able to figure out how to combine data with these kind of rational agent concepts. So those are my takeaways. Again, thanks everyone for coming. Thanks to my co-organizers for helping us put this together. Thanks for attending online and staying up late if you were in a different time zone. And with that, we'll break for dinner and enjoy the rest of the conference. Thank you.